When considering the broad sweep of astronomical history, there's no better place to start than the beginning, the actual beginning of space and time. 20th century astronomers such as Edwin Hubble discovered that the universe is expanding by observing that large-scale structures like galaxies are all moving away from each other in any direction that we look. This means that, in the past, the universe was smaller, and that, at some point in the distant past, everything started as a single point of space and time, a singularity. Years of careful observations by the Hubble Space Telescope and other facilities have revealed that the universe was born in an explosion of this singularity about 13.7 billion years ago. Cosmologists and astronomers, who specifically focus their research on the origin and evolution of the universe, have rigorously tested the details of the Big Bang theory with decades of astronomical observations, laboratory experiments, and mathematical modeling. These studies have taught us a lot about our universe's early history, which is impressive. Within the first second of the universe's existence, the temperature dropped from 1,000,000,000,000 degrees to only 10 billion degrees. And all of the universe's present supply of protons, hydrogen atoms, and neutrons formed out of this primordial plasma. The same nuclear fusion process that still occurs today. Deep inside stars formed helium and other light elements from hydrogen by the time the universe was only 3 minutes old. Creating space and time in a single instant, 13.7 billion years ago, is mind-boggling. What caused the explosion? What was there before the Big Bang? Cosmologists tell us we can't ask that question because the Big Bang created time. It's also humbling to realize that the most abundant element within each of our bodies, hydrogen, was created in the very first second that ever was. We're ancient. Recombination era. The universe's early years were a time of intense heat, pressure, and radiation. The primordial light of highly ionized atoms and subatomic particles bathed all of space, interacting, colliding, decaying, and recombining at millions of degrees. This period in cosmic history is often referred to as the radiation era. By the time the universe was about 10,000 years old, the expansion of space and the decay of many energetic particles had cooled the cosmos to only about 12,000 kelvins. Kelvins, or K, are a measure of the temperature above absolute zero. This was an important threshold because, as the universe continued to cool, the total energy from heat and ionizing radiation became less than the total so-called rest mass energy of matter itself. Physicist Albert Einstein's famous equation E = mc2 illustrates this. Still, for hundreds of thousands of years longer, the universe was essentially just an opaque, dense, high-energy soup of constantly colliding ionized protons and electrons. However, as the expansion and cooling continued, the radiation energy decreased in comparison to the remaining mass energy. About 400,000 years after the Big Bang, the temperature dropped to only a few thousand kelvins, low enough to capture electrons, dionize into stable hydrogen atoms, and form multiple hydrogen nuclei into the universe's first molecules, hydrogen gas, or H2. This period in the universe's early history is known as the recombination era. The cool thing about recombination is that it allowed the universe's remaining radiation, mostly high-energy photons and other subatomic particles, to decouple from matter and thus travel relatively unimpeded through space. The universe grew colder and darker over the next few 100 million years, which cosmologists have dubbed the Dark Ages. Today, we can still detect the residual 3 Kelvin glow of the joyously freed radiation energy of the early universe, known as the cosmic microwave background. First stars. Every dark age ends with a renaissance, and the universe's early history is no exception. Cosmologists believe the so-called Dark Ages lasted about 100 to 200 million years. After this time, molecular hydrogen and other molecules formed during the recombination era began to clump together gravitationally, perhaps due to turbulence effects, but no one knows why. The clumps of gas acted as seeds, gravitationally attracting more gas, making the clumps grow bigger and bigger until they eventually became enormous clouds of hydrogen that started to grow warm inside from the increasing pressure of the surrounding gas. Give a cloud a nudge, say from the gravitational pull of another nearby cloud, and it will move and eventually start to spin. At some point, maybe 300 to 400 million years after the Big Bang, the temperatures in the centers of some of these huge, slowly spinning clouds of gas grew to be millions of degrees, as in the first 3 minutes after the Big Bang. The temperatures and pressures inside these spherical clouds became high enough to fuse hydrogen into helium, and the first stars were born. The Dark Ages were over. The first stars, which were sometimes referred to as population 3 stars by astronomers, were more than quirky local phenomena. Perhaps 100 to 1,000 times more massive than our Sun, these enormous stars exerted a significant influence on their stellar neighborhood, radiating prodigious amounts of energy into the surrounding clumps and clouds of hydrogen, externally heating them and freeing the electrons captured at the beginning of the Dark Ages. This time is known as the era of reionization, because the universe once again began to glow, not from the light and heat of creation, but like today, from the light and heat of the stars. In this supercomputer simulation, ionized hydrogen bubbles, blue, and molecular hydrogen clouds, green, form the first organized, large-scale structures in the early universe, eventually collapsing to form the first stars. Milky Way. Astronomers define a galaxy as a gravitationally bound system of stars, gas, dust, and other more mysterious components, see dark matter, all moving collectively through the cosmos as if they were a single object. Once the first stars had formed, it was only a matter of time, not much time in fact, that many of them would inevitably become attracted by each other's gravity and form clusters. Then clusters of clusters, and eventually huge congregations of stars orbiting their common center of gravity. Our own Milky Way galaxy consists of an estimated 400 billion stars. It has a structure typical of the so-called barred spiral galaxies seen throughout the universe. See spiral galaxies. A diffuse spherical halo of older stars, star clusters, and 2 smaller companion galaxies surrounds the Milky Way, which features a crowded central semi-spherical bulge of stars surrounded by a flatter, spiral-shaped disk of stars, including the Sun, gas, and dust. It's an enormous structure, nearly 100,000 light-years, the distance light travels in a year, or about 1 billion miles, wide, and 1,000 light-years thick in the disk. Our Sun is about halfway out from the galactic center, and 1 galactic year orbit takes about 250 million Earth years. Astronomers still need to find out the exact formation date of the Milky Way. The halo of the oldest known stars in the galaxy is about 13.2 billion years old. The oldest stars in the disk are younger, about 8 to 9 billion years old. Despite the apparent early formation of the basic structure, the different parts of the Milky Way likely formed at different times. In creation myths, the bright whitish band that dominated their night sky awed our ancient ancestors, who often imagined it as a river of light and life. Though we now know that we are inside a massive, choreographed gathering of stars looking out, it's still easy to find awe in the scale and majesty of our home galaxy. Solar nebula. Star formation is a messy process. As giant molecular clouds collapse, almost all of the cloud's gas and dust eventually fall into the central protostar. A tiny fraction of the gas and dust remains in orbit around the forming star, and as the whole system spins and cools, that residual cloud of debris slowly flattens into a disk of gas, dust, and, further from the star, ice. During this phase of star formation, all young stars start with an accompanying disk, often called a solar nebula disk. The nebula from which our own Sun eventually formed probably started collapsing about 5 billion years ago, though the exact timing is uncertain. According to observations, Sun-like stars typically take about 100 million years to form, whereas nebula disks form around young stars in only about 1 million years. Once formed, the disk undergoes rapid changes as tiny dust and ice grains collide, stick to each other, and grow into marble-sized particles, a process known as accretion that computer models indicate takes only a few thousand years. These small particles collide with others, sometimes sticking together, and the process appears to continue in a poorly understood runaway fashion until, within perhaps only a few more million years, planetesimals, kilometer-sized clumps of dusty, icy, rocky, and metallic grains, and then asteroids 100,000 kilometers in size have formed. Solar nebula disks are short-lived. Most dust accretes or disperses within 10 million years. It's too warm to condense close to the star, so the planetesimals are mostly rocky and too small to hold on to much gravitational gas. Further out, ice and dust can accrete into larger planetesimals with enough mass to accrete huge amounts of gas, eventually growing into giant planets. Exactly how such messy beginnings lead to such elegant planetary systems, and in such little time, is currently a topic of much debate and speculation among astronomers. Violent proto-sun. Starbirth, like childbirth, can be an intense and messy event that requires a lot of energy. Even before they get hot and dense enough to start the nuclear fusion of hydrogen into helium, newly formed protostars can emit huge amounts of energy as they gravitationally contract during their 100 million year gestation period. Some of these baby stars funnel their energy into the solar system-sized jets of gas, dust, and charged particles, which may be collimated and heated by strong magnetic fields from the star, material falling in from the associated nebula disk, or both. Astronomers have identified many examples of violent jets of material being emitted from very young protostellar objects, often called T Tauri stars after the prototype example. The star T Taurus is very similar to what astronomers believe the young Sun was, suggesting that our star went through a similarly short and violent period of intense jetting and other high-energy activity before it started to stably fuse hydrogen and settle down into its long, relatively quiescent life on the so-called main sequence. Some of the solar system's worst materials, the ordinary chondrite meteorites, may preserve evidence for whether the Sun underwent such a violent early T Tauri phase. These rocks, which occasionally fall to Earth, are the oldest known solids in the solar system, and they help to determine the Sun's age and the timescale for the formation of the planets. These meteorites often contain large percentages of chondrules, small spheres of mineral grains that were once molten droplets of rock before cooling and accreting into larger grains, planetesimals, and asteroids. The energy source for chondrule melting in the early solar system is unknown, but high-energy outbursts and jets from the young Sun are possible. The deeper and more accurately astronomers peer into space, the more evidence they find for jets and disks around newly formed stars, suggesting that these features are crucial to star formation. A violent youth may be a normal, essential part of a typical star's life cycle. Birth of the Sun. For about 100 million years, the temperature and pressure in the central region of the solar nebula grew dramatically until they passed a threshold where hydrogen atoms were so tightly packed that they underwent nuclear fusion, becoming helium and releasing some energy as light and heat. Thus, our Sun was born. We tend to think of the Sun as special, and rightly so. The Sun is critical to the creation and continuing survival of all life on our planet. It's harder to think of the Sun as typical, average, or even mundane, but in many ways, it is. Our star is one of more than 10 billion trillion, one with 22 zeros after it, stars in the known universe, all of which appear to be the natural result of matter, mostly hydrogen, interacting with gravity at high pressures and temperatures and releasing enormous amounts of energy into their surrounding space. Stars are truly the engines of our universe. Once stars are born, they live relatively stable lives and die, often in relatively predictable and sometimes spectacular ways. The Sun is no different. It will keep fusing hydrogen into helium atoms for another 5 billion years. When the hydrogen runs out, the Sun sheds its outer layers, engulfing the Earth and other inner planets, and fuses helium in its core. When the helium runs out, the Sun slowly fades to a white dwarf and then dims to a cinder. Astronomers have deduced that in our Milky Way galaxy, about 1 to 3 new stars are born each year, and about 1 to 3 old stars die each year. If we extrapolate to all known galaxies and do a little math, that means that something like 500 million stars are born, and 500 million stars die each day in the universe. It's a staggering and humbling thought that should make us appreciate every one of these precious days even more in the life of our star, the Sun. Mercury. All the planets in our solar system formed around the same time, about 4.5 billion years ago, as the solar nebula cooled and tiny grains condensed, collided, stuck together, and eventually grew into a small number of big objects. In the warm zone close to the Sun, the planets were rocky. Beyond the now line, they were rock, ice, and gas mixtures. Mercury is the closest of the so-called terrestrial planets, with a diameter of 3,032 miles, 4,880 kilometers. Earth's diameter, by comparison, is 7,926 miles, 12,756 kilometers. Mercury orbits the Sun at an average distance of only 0.38 astronomical units, or AU. 1 AU, 93 million miles, 150 million kilometers, average orbital distance from the Sun. Mercury is the Roman name for the Greek god Hermes, the fleet-footed messenger. The planet was aptly named. Even the ancients knew that Mercury takes only 88 days to complete a circuit in the sky, which we now know represents its orbital period around the Sun. Mercury is a small world of harsh extremes and curious enigmas. There is no atmosphere, and temperatures range from only 90 kelvins in permanently shadowed craters near the poles to more than 700 kelvins above the melting point of lead in the harsh midday sunlight. Earth-based radar observations indicate that there may be ice in those polar craters. Mercury has a very high density and a large iron core spanning 75% of its radius. The core might be partially molten, explaining Mercury's weak magnetic field, 1% as strong as Earth's. Images from the 2 space missions that have encountered Mercury, Mariner 10 in 1974-1975 and Messenger in 2011-2015, reveal a heavily cratered surface and some evidence of ancient volcanic activity similar to the M-moons. Perhaps most surprisingly, the planet preserves a network of large tectonic thrust faults, scarps, indicating that Mercury may have been molten early in its history and shrank by a few percent when it cooled. Venus. It's fun to ponder the relative importance of nature versus nurture in determining the origin of personalities and characteristics. Twins, for example, make great case studies. Well, the same is true for planets, and one of the best examples to consider is Venus, a near twin of Earth in some ways, but profoundly different in others. Venus is about 5% smaller than Earth and has about the same density, meaning it is a rocky, terrestrial planet like ours. Both planets have atmospheres, and Venus even orbits in the same general neighborhood of the inner solar system as we do, at an average distance of 0.72 astronomical units compared to Earth's 1.0. But that's where the similarities end. Venus is barely spinning, taking about 243 Earth days to spin once on its axis, backward. The Venusian atmosphere is much thicker than ours, with 90 times the pressure at its surface. That thick atmosphere sports violent upper-level wind speeds of more than 218 miles, 350 kilometers, per hour. It is almost entirely carbon dioxide, with only scant traces of nitrogen dioxide, oxygen, and water in the atmosphere. The carbon dioxide molecule is transparent to visible light. Still, it is exceedingly good at trapping heat radiation, like a greenhouse, causing the surface of Venus to be very hot, more than 750 kelvins, or about 300 degrees hotter than an oven. Astronomers are trying to understand how Earth and Venus ended up with such radically different surface conditions. Understanding carbon dioxide may be the key. Earth's oceans dissolve carbon dioxide, trapping it in rocky carbonate minerals. Any ocean on early Venus, slightly closer to the Sun, would have evaporated away, leaving no way to remove carbon dioxide. Venus is a case study of carbon dioxide gone wild, and it is a prime example of how studying other planets can help us understand what may be in store for our world. Earth. Our home world is the largest of the terrestrial planets, and the only one with a large natural satellite. Geologists say the rocky volcanic world has separated its interior into a thin, low-density crust, a thicker silicate mantle, and a high-density, partially molten iron core. It is a planet with a thin nitrogen-oxygen-water vapor atmosphere, buffered by an extensive liquid water ocean and polar ice cap system, all of which participate in large climate changes on seasonal to geologic timescales, according to an atmospheric scientist. To a biologist, it's heaven. Earth is the only place in the universe where life exists. Indeed, fossil and geochemical record evidence shows that life on Earth began almost as soon as possible, when the late heavy bombardment of asteroids and meteorites quieted. Earth's surface conditions appear to have remained relatively stable over the past 4 billion years, which, combined with our planet's favorable location in the so-called habitable zone, where temperatures remain moderate and water remains liquid, has enabled life to thrive and evolve into countless unique forms. A few dozen moving tectonic plates, floating on the upper mantle, divide Earth's crust. Exciting geology, earthquakes, volcanoes, mountains, and trenches occurs at the plate boundaries. Most of the oceanic crust, 70% of the surface area, is very young, having erupted from mid-ocean ridge volcanoes a few 100 million years ago to today. Only a few hundred impact craters remain on our surface due to its youth, a stark contrast to the battered face of our neighbor, the Moon. The high amounts of oxygen, ozone, and methane in the atmosphere are signs of life that alien astronomers studying our planet from afar could detect. Indeed, these gases are exactly what astronomers are looking for today among the panoply of newly discovered extrasolar planets. Could there be additional Earths awaiting discovery and exploration? Mars. We may have to go no farther than the next planet to find out if life exists, or ever existed, beyond Earth. From ancient times, when many saw Mars as a cosmic incarnation of the Roman god of war, to the 20th century, when many imagined the planet to be the abode of Percival Lowell's desperate canal builders, Mars has seemingly always been a subject of fascination. Mars is a small planet, about half the diameter of Earth, and only about 15% of its volume. For further reference, Mars's surface area is about the same as that of all the continents on Earth. On average, the planet orbits about 50% farther from the Sun than we do. The thin Martian carbon dioxide atmosphere, only 1% as thick as Earth's, cannot trap much heat, so the surface is cold. Daytime temperatures near the equator rarely rise above the freezing point of water, and nights near the poles routinely drop to the freezing point of carbon dioxide, 150 kelvins, or about 190 degrees deep. Today, Mars is a dusty world in a deep freeze. Yet spacecraft images, meteorites from Mars, and other data over nearly 50 years have shown that Mars is the most Earth-like place in the solar system, besides Earth itself, and that during its first few billion years, the red planet may have been a much warmer and wetter world. What happened? Possibilities include gradual cooling of the planet's core, solar wind, or catastrophic impact destruction of the atmosphere. Determining how and why the planet's climate changed dramatically is a hot research topic. 3 or 4 billion years ago, we learned enough about Mars to know that parts of the surface and subsurface were habitable to life. The next 50 years of Mars exploration will be about expanding the search for habitable environments and discovering if any were, or still are, inhabited. Main asteroid belt. About 4.5 billion years ago, small rocky and metallic building blocks known as planetesimals quickly assembled into terrestrial planets from the solar nebula's slowly cooling, warm inner regions. Each growing planet wept up planetesimals along and near its orbital path, generally clearing out their orbital zones until the lack of new material to sweep up set a limit on the growth of these rocky worlds. However, the strong gravitational influence of nearby Jupiter continually thwarted and disrupted the accretion of planetesimals and their growth into larger planets beyond the orbit of Mars. Influence made collisions between planetesimals more energetic, minimizing the gentle collisions and allowing them to stick together and grow. In the Mars-Jupiter zone, close encounters with Jupiter ejected many planetesimals. Thus, instead of a large planet in the region between Mars and Jupiter, we have a rather diffuse disk or belt of small rocky and metallic asteroids, the main asteroid belt. Astronomers estimate that there might be more than 1 million asteroids larger than a half mile, about a kilometer, in the main belt. The orbits, positions, and general characteristics of more than 500,000 of these are known, including the most massive two, Ceres and Vesta. These two, plus the asteroids Pallas and Juno, account for more than half of the total mass of the entire main belt. Asteroids aren't just randomly located, though. Gravitational pull has cleared out many gaps in the main belt, see Kirkwood gaps, and some groups of asteroids travel together in families that may represent the disrupted and slowly scattering remains of once larger objects. J-Jupiters and Trojan's asteroids are two large groups of small bodies trapped in special orbits, where J-Jupiters and the Sun's gravity balance each other. Small pieces of impact-shattered asteroid interiors fall to Earth all the time. We call them meteorites. And their ages and compositions provide an enormous amount of detailed information about our solar system's timing, formation, and evolution. On August 14, 2006, a computer-generated plot overlaid the inner solar system, extending to Jupiter's orbit, the outer blue circle, with the Sun at its core. Asteroids in the main belt are colored white. Orange dots are the Hilda asteroid family, and green dots are Jupiter's Trojan asteroids. Jupiter. Our solar system comprises the Sun, about 99.8%, Jupiter, about 0.1%, and everything else. Jupiter is truly the king of the planetary realm, with more than twice the mass of all the other planets combined. 63 known moons and a series of faint rings orbit this colossal world. Jupiter's diameter is 23 Earths across. If it were hollow, more than 1,000 Earths would fit inside. Partly because of its enormous size and its orbital position at the inner edge of the outer solar system, around 5.2 astronomical units, Jupiter is the fourth brightest object in our night sky after the Sun, Moon, and Venus. Jupiter is also luminous because its visible surface comprises bright clouds. Indeed, no surface is visible on Jupiter or any other giant outer planets. Everything we see is a cloud or haze made of exotic and sometimes colorful chemical compounds like methane, ethane, ammonium hydrosulfide, and phosphine. Winds traveling several hundred miles per hour twist the clouds into horizontal belts, and giant Earth-sized storm systems, such as the Great Red Spot, have churned for hundreds of years. Below the clouds, Jupiter's pressure and temperature increase dramatically, but the chemistry is, on average, much simpler. Jupiter is about 75% hydrogen and 25% helium, just like the Sun. If the solar nebula had been bigger and Jupiter had formed with about 50 to 80 times more mass, it would have become a star. Jupiter's formation has had a major influence on the architecture of the solar system, perturbing the orbits of other giant planets, preventing a planet from forming in the region of the main asteroid belt, and gravitationally scattering asteroids and comets on orbits that caused impacts with other planets in the late heavy bombardment. Jupiter even flung some objects entirely into the Kuiper belt or out of the solar system. Today, Jupiter is a gravitational magnet, occasionally drawing in small bodies such as Comet SL9, which split up and smashed into its cloud tops in 1994. Saturn. There might be no more enchanting experience for a fan of astronomy than viewing Saturn and its glorious rings through a small telescope. The scene is almost surreal, a shimmering, egg-shaped orb hanging against the blackness of space, and girded by what seems like an incredibly delicate, thin disk of material, almost twice as wide as the planet itself. It is truly one of the sky's gems. Saturn is the second largest of the gas giants, more than 9 times wider and nearly 100 times as massive as Earth. The famous ring of Saturn is the flat disk that circles the planet's equator. Composed mostly of ice, the ring system is probably at most 22 to 33 yards, 20 to 30 meters, thick. No one knows whether the rings of Saturn are an ancient, primordial feature or a relatively new feature, perhaps formed from the catastrophic breakup of a former icy moon. 62 known moons, hundreds of smaller moonlets embedded in the rings, and billions of ring particles, ranging from the size of houses and cars to specks of dust, accompany Saturn. Saturn's largest moon, Titan, is larger than Mercury and is the only moon in the solar system with a thick atmosphere. Clouds and haze bands are fainter and less colorful than Jupiter's, although the atmosphere's composition is similar. Perhaps the biggest chemical difference between Saturn and Jupiter is that, for reasons not fully understood, Saturn has a little less helium relative to hydrogen, making it less solar than Jupiter. Another mystery is why the wind speeds on Saturn are much higher than on Jupiter or anywhere else in the solar system, more than 1,120 miles, 1,800 kilometers per hour in some places. Detailed studies of Saturn and Jupiter by the Pioneer, Voyager, Galileo, and Cassini spacecraft show us that not all gas giants are the same. As we discover more gas giants among the extrasolar planets, those worlds too are likely to be both lovely and enigmatic. Uranus. Unlike the first 6, our solar system's 7th planet was unknown to the ancients. The English astronomer Sir William Herschel discovered Uranus in 1781 through telescopic observations. Many other astronomers had observed Uranus as early as 1690, but they mistaken it for a star due to its extremely slow motion across the sky, an 84-year orbit period. Because Uranus has an average orbital distance of about 19 astronomical units, Saturn, the next closest planet to the Sun, has an average orbital distance of about 9.5 astronomical units. Its discovery instantly doubled the size of the solar system. At 4 times the diameter and 15 times the mass of Earth, Uranus is classified as a giant planet, but it is much smaller than its planetary cousins, Jupiter and Saturn. Still, the atmosphere of Uranus contains mostly hydrogen and helium, and methaplanet causes the planet's distinctive blue-green color and hazes in the upper atmosphere. Storms on Uranus are rare, and the cloud and haze bands are usually quite faint. However, Uranus has a different planetary composition from Jupiter and Saturn. It has significant amounts of ice and rock in its deep interior. Uranus, and Neptune, exhibits a significantly higher ratio of ice and rock to gas than Jupiter and Saturn, thereby qualifying the planet as an ice giant rather than a gas giant. As discovered by telescopic observations and the Voyager 2 flyby in 1986, Uranus has 5 large and 22 smaller moons, all dark and icy. The planet also sports about a dozen thin, dark, icy rings, possibly formed from a relatively recent breakup of one or more small moons. Uranus's unusual spin axis tilts on its side by about 98 degrees relative to the ecliptic, the plane of Earth around the Sun. A grazing giant impact or a close encounter with Jupiter long ago may have caused Uranus's unusual axial tilt. Whatever the case, it is yet another of our solar system's mysteries. Neptune. If Earth and Venus can be considered fraternal twin planets, then Uranus and Neptune are more like identical twins. Both are residents of the deep outer solar system, with Neptune out at 30 astronomical units, taking approximately 165 Earth years to orbit the Sun once. Both ice giants are about the same size and mass. Neptune is slightly heavier at 17 Earth masses, and both have a similar composition, about 80% hydrogen, 19% helium, and trace amounts of methane and other hydrocarbons. As it does on Uranus, methane gives Neptune its beautiful azure color. Neptune, like Uranus, is another ice giant world with a modest number of icy satellites, 13, and a system of dark, icy rings. From telescopic measurements, data from the 1989 Voyager 2 flyby, and laboratory studies, astronomers have deduced that Neptune's atmosphere extends about 10 to 20% of the way to the planet's center. Then, as pressure and temperature increase, higher concentrations of water, ammonia, and methane form a hot liquid mantle. Astronomers call this zone icy because it is iose. The molecules are thought to have originally come from the mostly icy outer solar nebula planetesimals that were part of Neptune's building blocks. Some astronomers even think of this zone as a water-ammonia ocean, and computer simulations suggest that a rain of diamonds falls through it to the planet's core of rock, iron, and nickel. Astronomers find it puzzling that the ice giants reside in the far outer solar system, because there may not have been enough solar nebula material at those distances to form them. One explanation is that they formed closer to the Sun and slowly migrated out, gravitationally nudged by Jupiter and Saturn. We think of the solar system today as stable, running like clockwork, but when the planets were forming, it was much more violent and chaotic. The Kuiper Belt and Pluto. Most of the rock and ice from the solar nebula that didn't do the young Sun eventually went into building Jupiter and, to a lesser extent, the other big planets of our solar system. However, some leftover building blocks, such as the small 0.66 miles, 110 kilometers, rocky planetesimals in the main asteroid belt that Jupiter prevented from growing into full-fledged planets, and similar icy ones beyond Neptune that were too far apart and too rarely collided to grow into large planets, remained. This latter class of so-called trans-Neptunian objects is of special interest, partly because the first one ever discovered is also the most famous, Pluto. Pluto is a small, icy and rocky world in an elliptical orbit between 30 and 50 astronomical units, AU. It only accounts for about 20% of our Moon's mass and 35% of its volume. Yet it has a large icy moon, Charon, along with at least 4 smaller icy moons, and a thin comet-like atmosphere of nitrogen, methane, and carbon monoxide. Since the early 1990s, astronomers have discovered many more Plutos and Neptune orbiting within a donut-shaped disk called the Kuiper Belt, named after the Dutch-American astronomer Gerard P. Kuiper. Beyond the Kuiper Belt, where small icy bodies formed in the zone between about 30 and 55 AU, another scatter disk consists of icy bodies that formed closer to the Sun, but Jupiter's gravitational encounters flung them out to between 30 and 100 AU. More than 1 through 100 trans-Neptunian objects are now known. As it became clear that there are huge numbers of Pluto-like objects in the Kuiper Belt and scattered disks, the International Astronomical Union demoted Pluto and other similar objects in 2006 to dwarf planet status. A space mission has yet to visit Pluto, the last well-known body in our solar system. That will change in 2015 when the New Horizons mission flies past Pluto and its moons, revealing them as new worlds rather than just fuzzy points of light. Birth of the Moon. Earth is unique among the terrestrial planets in that it has a very large natural satellite. But where did our Moon come from? Astronomers have considered many possible ideas. One idea is that the Moon formed in orbit around our planet simultaneously, and in the same way that Earth formed, by the accretion of rocky and metallic planetesimals condensed out of the warm inner solar nebula. Another hypothesis is that the early molten Earth was spinning so fast that a blob of it shed off, fissioned and went into orbit, forming the Moon. Another hypothesis suggests that the Moon originated from a different location in the inner solar system, which Earth then captured. These ideas competed for supremacy until the Apollo missions brought moon rocks and other information back to Earth, revealing that they needed to fit the actual data about the Moon. The co-accretion model predicted that the Moon would have the same basic age and composition as Earth, but it does not. The Moon has a much lower density, much less iron, and appears to have formed 30–50 million years after Earth and other planets formed. Fission caused the early Earth to spin too fast, and the capture model suggested that there was no way to dissipate all the energy a free-flying Moon would have lost into orbit. Planetary scientists proposed the giant impact model in the 1990s, suggesting that a Mars-sized protoplanet could have struck the early Earth obliquely in a giant impact, melting enough of Earth's iron core mantle to launch it into orbit, where it would cool, accrete, and eventually form the Moon. The Moon's composition, density, and age matched the models. Indeed, the giant impact model is still the best explanation for the origin of our Moon. Late, heavy bombardment. Throughout geologic history, a veritable rain of asteroids and comets has hammered all the planets, including Earth, and the rate of impact in the early days of the solar system was many orders of magnitude higher than it is now. Earth lacks the record of that early cosmic impact history due to younger volcanic deposits covering most of our planet or erosion from wind, water, and ice. The surface of the Moon, on the other hand, is much more revealing, and the huge number of lunar impact craters and basins provides a stark reminder of just how battered Earth's Earth must have once been. One of the major legacies of the Apollo missions is the ability to determine the absolute ages of specific impact cratering events using radioactive dating of lunar samples. The research reveals the dates of significant lunar impact events: 3.8 to 4.1 billion years BCE, a surprising discovery, considering that all the major planets formed around 4.5 billion years ago. Many planetary scientists believe that the simplest explanation is that the Moon, and by inference, Earth, went through intense impact cratering about 400 to 700 million years after their initial formation. The cause of this relatively brief spike in what was an otherwise decreasing rate of impacts is unknown, but some have speculated that Jupiter's nudging, the same nudging that influenced the putative migration of Uranus and Neptune, and that likely propelled the trans-Neptunian objects out into the Kuiper Belt, may also have diverted some asteroids and comets into the inner solar system. If true, the resulting cataclysm certainly wreaked havoc on the terrestrial planets, and no doubt had a profound influence on the development and stability of life in our home world. Life on Earth. No one knows exactly how, when, or why life first appeared on planet Earth, but we know that almost as soon as it could, it did. We infer that the oldest signs of life on Earth are chemical evidence, not fossils, because all known life shares a common chemical architecture. Specifically, certain biogeochemical processes and reactions common to all life on Earth, reactions involving certain amino acids commonly associated with DNA or RNA, for example, create recognizable patterns in the isotopes of carbon and some other elements. In essence, life prefers to use and create certain materials and anomalous chemistries, such as the occurrence of extra carbon, 12, 12C compared to carbon 13, 13C, in some 3.8 billion-year-old rocks from Greenland, provide circumstantial but controversial chemofossil evidence for life very early on our planet's surface. The earliest known fossil evidence of microbial life on our planet dates back approximately 3.5 billion years. Simple organisms like blue-green algae build up layers of ancient stromatolites, rocks, and mineral structures to preserve it. Stromatolites still form in places such as Shark Bay in Western Australia, making them among the oldest life forms on our planet. Recent studies of the very earliest period of Earth's history, the Hadean, 3.45 to 3.8 billion years ago, provide evidence that oceans and continents may have formed much earlier than previously thought, and that conditions may have been suitable for life just a few 100 million years after our planet formed. 3.8 to 4.1 billion years ago, the late heavy bombardment may have killed off earlier life forms or frustrated their flourishing attempts. Whatever the case, soon after Earth cooled, the oceans formed, the late heavy bombardment ended, and Earth became stable enough to support life. It thrived and began to expand into so many niches, which is remarkable. Now, astronomers, planetary scientists, and astrobiologists are searching for evidence of life on other Earth-like worlds. This is a cross-sectional view of a stromatolite fossil. The reddish layers are believed to be the fossilized remains of ancient blue-green algae, some of Earth's oldest preserved evidence of life. This piece, from the Ord Range of Western Australia, is about 2.4 inches, 6 centimeters tall. Cambrian explosion. The first life forms to emerge on Earth were simple, single-celled microbes that could tap into chemical and thermal energy sources in the environment of early Earth. Single-celled organisms, occasionally organized into colonies like those found in stromatolites, dominated Earth's first 3 billion years. However, the diversity of life on Earth began to dramatically increase around 550 million years ago, a phenomenon known as the Cambrian explosion. As a result, many of the ancestors of today's plants and animals appear relatively early in the fossil record, geologically speaking. Biologists are actively debating possible reasons for Earth's sudden and dramatic life diversification at the Precambrian-Cambrian boundary. Biologists are also trying to understand the reasons for many rather sudden, drastic decreases in species and species diversity in the fossil record. The most dramatic occurred at the boundary between the Permian and Triassic geologic periods, around 250 million years ago. About 70% of all land species and 96% of all oceanic species died off over a span of perhaps only a million years, a period informally called the Great Dying and the mother of all mass extinctions. It took more than 100 million years for the diversity of life on Earth to reach pre-Permian levels again. And climate change could have triggered such a massive loss of life on Earth, although many believe that the rapidity is difficult to explain. Alternatively, a catastrophe such as a large impact event or an enormous volcanic outpouring, which may also have triggered other climatic and geologic catastrophes, could be responsible. Biologists, geologists, and astronomers are still searching for clues. The Permian extinction 250 million years ago decreased Earth's species and diversity of life. The view from Yavapai Point across the Grand Canyon exposes nearly 2 billion years of Earth's record for detailed study, 65 million BCE. Dinosaur killing impact. A father and son geologic team, Luis and Walter Alvarez, and their colleagues found what they believed to be compelling evidence that the impact of a large asteroid on Earth likely caused the extinction of the dinosaurs and many other species about 65 million years ago. The key was the discovery of a thin layer of sediment worldwide enriched in the rare element iridium and dating to what is now defined as the boundary between the Cretaceous and Tertiary geologic periods, often abbreviated as the KT boundary. Iridium is a metal in the platinum family that often bonds with iron in rocks and minerals. Most of Earth's iridium sank into the deep mantle and core when it formed. Hence, a globally distributed, iridium-rich crustal deposit of the same age is quite an anomaly. According to the Alvarez hypothesis, the iridium came from a large metal-bearing asteroid that impacted Earth and vaporized, dramatically changing the climate and wreaking havoc on many plant and animal species. The impact lifted vaporized rock and dust into the atmosphere and set off large-scale fires that added soot and smoke, blotting out the sun and lowering global surface temperatures for years. Although the impact was not as significant as the Permian-Triassic extinction, the KT boundary decimated species that rely on sunlight and photosynthesis, thereby destroying the foundations of many other predator-predatory ancestors. The event didn't severely disrupt some species, such as mammals and birds capable of burrowing or subsisting on insects, carrion, or other non-Werentud chain staples. When the dust cleared, literally, the survivors could expand into niches they couldn't occupy. Scientists are constantly testing the hypothesis that an asteroid impact killed off the dinosaurs. Other geologic and climatic effects, such as a dramatic sea level drop or massive volcanic rock eruptions, that occurred around the same time, but before the hypothesized impact, may have contributed to the environmental conditions that wiped out so many species. Homo sapiens. Homo sapiens is a relatively new human species on Earth. Our earliest appearance in the fossil record dates back only about 200,000 years, according to African archaeological sites. Fossil evidence shows that Homo sapiens coexisted for a time with our closely related subspecies, the Neanderthals, and that evidence for Neanderthal traits disappeared from the record around 30,000 years ago. We are a persistent lot, excelling at survival with tools, language, long memories, and hard-won experience. Our history and evolution reflect a curiosity and a desire for more intangible nourishment of the soul, which may explain why music, dance, and art have been such an important part of the human experience. I remember seeing the 17,000-year-old Paleolithic cave paintings from the Dordogne region of France, and being amazed that our ancestors could make time for art amid what must have been a constant struggle to stay alive. However, they should have paid more attention to animals, plants, and other mundane things on a daily basis. Many archaeologists now believe that some of the dots, lines, and perhaps even animal figures were representations of constellations or other features of the night sky. If so, these are the oldest paintings on Earth and sky maps created by the world's first explorers. The human race's emergence is a minor milestone in the history of astronomy. We are, after all, just one species on one planet, orbiting a typical star in a fairly ordinary part of an average spiral galaxy. Our planet may be one of the billions capable of supporting life, and we could be one of the countless sentient species among the stars. But we might also be the only intelligent, self-aware, technological species and civilization in all the cosmos. That latter possibility is humbling, daunting, and perhaps even scary. Still, it reminds us that we should indeed celebrate as truly extraordinary the appearance of a species that, through its achievements, provides a way for the universe to know itself. Arizona impact. We know that asteroids and comet impacts have slammed the Earth throughout history. We need only look at the record of the late heavy bombardment preserved on the ancient airless surface of our celestial neighbor, the Moon. Given the erasure of impact craters on our planet via the constant erosion of wind and water and the continuous renewal of the seafloor through plate tectonics and volcanism, it's no wonder it took terrestrial geologists a long time to realize the importance of impact cratering as a geologic process on Earth and other terrestrial planets, moons, and asteroids. One of the best natural laboratories for that realization is the Meteor Crater, the Barringer Crater, or the Canyon Diablo Crater, just east of Flagstaff, Arizona. The crater is about 1 to 200 meters, 3,900 feet wide, and 170 meters, 557 feet deep. Up until the 1960s, geologists heatedly debated the origin of this feature. In the 1890s, G.K. Gilbert, one of the first advocates for the impact origin of the circular craters on the Moon, argued that the lack of significant debris from the impactor meant that an explosive volcano formed the crater. In the early 20th century, mining engineer Daniel Barringer purchased the crater and spent years drilling in vain for what he believed was a giant buried iron meteorite from an impact event. Finally, geologist Eugene M. Shoemaker, who had studied craters created by the US government's program in Nevada, confirmed the crater's origins impact feature, based primarily on the discovery of certain forms of quartz minerals that could only form in the high-pressure, high-temperature environment of an impact rather than a volcano. Since then, Scientists have recognized more than 200 other impact craters on Earth, most larger but significantly less preserved than meteor crater. Impact Physics Lab and computer studies now reveal that impactors, in this case, an approximately 164-foot, 50-meter, iron-rich asteroid traveling at more than 6 miles, 10 kilometers per second, always completely vaporize on impact, resolving the question about the lack of debris in the crater's surrounding area. Birth of Cosmology. In Greek, cosmos means the universe. Thus, our modern word cosmology refers to the study of the universe's nature and evolution. In the classical context, a society's cost is a reflection of its worldview, or the way it views its origins, purpose, and future. Civilizations throughout human history have created and nourished their cosmologies through creation stories, mythology, religion, philosophy, and, most recently, science. We often hear, or read, such platitudes about how humanity has always looked to the stars, or how our distant ancestors must have pondered the heavens in this way. While it's fun to spectate, it's impossible to understand what prehistoric people thought, because by definition, there's no history. That's one reason the oldest archaeological artifacts depicting or representing astronomical themes are so important. They provide real data to understand how ancient people viewed the universe. The oldest preserved evidence of a civilization pondering the heavens comes from the Sumerians, in their partial star maps or pieces of crude astronomical instruments that some scholars believe date to 5,000 and 7,000 years ago. Even the scant fragments of information from that time reveal significant sophistication in the Sumerians' understanding of the motions of the sun, moon, major planets, and stars. Perhaps this is not surprising. The Sumerians built the first city-states, supported by a year-round, non-migratory population that cultivated crops. Knowing how to read the sky translated directly into knowing when to plant, irrigate, and harvest. A stable food supply gave them time to invent writing, arithmetic, geometry, and algebra. Sumerian cosmology was the first to make gods of heavenly bodies, a practice later inherited by Babylonian, Greek, Roman, and other cosmologists. Sumerian cosmology also espoused the idea of many heavens and earth in a decidedly non-geocentric universe. Surprisingly, this world resonates with modern cosmological thinking, as reality appears to be a universe without a center and brimming with many earths, ancient observatories. While ancient peoples were aware of the sky, large-scale, often astronomically themed monuments did not appear until the Bronze Age, about 3,600 BCE. The most famous of these is the prehistoric monument of Stonehenge in southern England, which is just one of many ancient stone circles, burial mounds, and other earthwork structures worldwide with cultural, religious, and astronomical importance. Stonehenge's cobblestones are impressive, especially the 25-ton lintel stones perched atop the 13-foot, 4-meter, 50-ton standing post stones. Modern experiments and simulations have shown that building such structures was possible using Neolithic and Bronze Age tools and methods. Neither magic nor architecturally gifted aliens were required. Still, it must have been near the limit of the available technology to build such unprecedented structures. It also appears to have been an impressive feat of prehistoric design. Some archaeologists have interpreted a detailed examination of the orientations of the site's various sites, post holes, pits, paths, and ridges, as evidence that Stonehenge was an astronomical observatory, designed in some ways as a giant sundial to mark the passing of the seasons and to calculate the specific dates of the winter and summer solstices. Archaeologists and astronomers widely agree that they designed the basic alignment of the monument with the paths of the sun and moon in mind, despite the details of its use being the subject of active research and debate. Other examples of prehistoric astronomical observatories include the Newgrange and Maeshowe burial mounds in Ireland and Scotland, respectively, aligned so that only the rising winter solstice sun fills their inner tombs with light. solar-aligned trilithons and passage mounds in Portugal, and the stacked Taula stones on the Spanish island of Minorca. As far back as 5,000 years ago, the civilizations that built these remarkable monuments left no written records about themselves, their traditions, or their beliefs. However, they left lasting records of stone and earth, revealing how much they must have valued their knowledge of the heavens. Egyptian astronomy. The Great Pyramids of Giza are a monument to the technological and labor management prowess of ancient Egyptian civilization. They are also testaments to the designer's astrologists' skills, which figured prominently in Egyptian society and religion 4,500 years ago. Because of Earth's spin and processes, or wobbles like a spinning top, in 2500 BCE, Polaris was not the North Star. Indeed, much like the skies near our south celestial pole today, there was no bright star near the north celestial pole in those days. To the pharaohs, astrologers, and commoners, the sky at night appeared to spin around a vortex-like dark hole, thought to be a gateway to the heavens. In ancient Egypt, this gateway was about 30 degrees above the northern horizon. Therefore, they carefully aligned the pyramids to the north, and a small shaft led from the pharaoh's main amber to the outside, pointing directly into the center of the gateway. If the plan was to join the gods in the afterlife, why not go in through the main door? Egyptian astrologers significantly contributed to developing a sophisticated and well-established calendar system during the construction of the pyramids. A new year was defined by the first sighting of the brightest star in the sky, Sirius, Sopdet to the Egyptians, just before sunrise in midsummer. They divided the year into 12 months, each lasting 30 days, and added 5 extra days for worship or parties to create a 365-day year. They also knew, after carefully observing and recording star positions on different dates, that they needed to add an extra day every 4th year, a leap day, to keep their calendar synced to the motions of the sky. They tracked the pre-dawn rising times of several bright stars in order to schedule major religious festivals and prepare for the Nile's annual floods. The pyramid shape may even represent a facet of ancient Egyptian cosmology, as some myths claim that the god of creation, Atum, lived within a pyramid that, along with the land, had emerged from the primordial ocean. The Great Pyramids of Giza were the largest human-made structures in the world for nearly 4,000 years. They were burial grounds for the pharaohs, as well as astronomical pointers to the presumed gateway to the heavens at the North Celestial Pole. Astronomy in China. Interest in and use of astronomy developed independently in cultures around the world. Chinese astronomy's roots date back to the prehistoric and Bronze Ages, according to archaeological evidence of star and constellation names preserved in ancient burial sites. The early Chinese, like other civilizations before and since, were deeply aware of the cycles and motions of the sun, moon, and stars. Each major dynasty of early China recruited astronomers to create intricate solar and lunar-based calendar systems. They were diligent and thoughtful in their astronomical observations, carefully recording evidence of changes in the sky, including solar and lunar eclipses, sunspots, the motions of the planets, and the appearance of new comets or supernovae. Astronomers today still use unique records kept by Chinese astronomers from the Xia, Shang, and Zhou dynasties, about 2100 to 250 BCE, for historical astronomical research. Chinese astronomers developed new and accurate instruments for observing the heavens, including large celestial globes and armillary spheres used to map the stars and constellations and track the motions and brightnesses of planets, guest stars, Chas comet, and novae. Until the 17th century, Chinese astronomers used more sophisticated versions of these instruments to develop theories of planetary motion that rivaled those developed by Western astronomers like Tycho Brahe and Johannes Kepler, using similar methods. The early Chinese had several complex cosmological models of the universe. Some models envisioned the heavens as a dome or celestial sphere, as in early Western cosmology, while others viewed the heavens as infinite and somewhat chaotic. Before it was fashionable in the West, some early Chinese astronomers deduced that the moon and other celestial bodies were spherical. The potential clash with the prevailing worldview of the Earth as flat didn't seem to be a problem because the emphasis of early Chinese astronomical studies, consistent with the prevalent concepts and practices of Confucianism, was on careful observations of the way the universe was, or at least appeared to be. Earth is round. Pythagoras, 570–495 BCE. We take it for granted. The Earth is a beautiful blue spherical marble set against the blackness of space. But without the recent benefit of going out into space and looking back, someone had to advance the idea that the Earth might be round rather than flat, as it appears to anyone on the ground. According to many accounts, that person was Pythagoras of Samos, a 6th century BCE philosopher, mathematician, and part-time astronomer from Greece, also famous for his Pythagorean theorem in geometry. One evidence that the Earth is round is the curved shadow of the Earth cast onto the Moon during a lunar eclipse, such as the one observed in Greece. The argument Pythagoras and his followers made for a spherical Earth was indirect, based on various observations. For example, sailors traveling south from Greece reported seeing southern constellations higher in the sky the farther south they went. For example, expeditions that departed for destinations along the African coast south of the equator reported that the sun shone from the north rather than from the south, as in Greece. Observing lunar eclipses provided another important piece of evidence. When the full moon passes directly behind the Earth relative to the sun, the Earth's curved shape is visible as it eclipses the moon. It is a matter of debate whether Pythagoras himself actually discovered that the ear is spherical, or was simply the most outspoken and famous advocate of what was becoming relatively common wisdom among educated people in early Greek civilization. Regardless, Eratosthenes' experiments would prove the issue in about 250 years, and nearly 2,500 years later, the first astronauts to leave Earth orbit, aboard the Apollo 8 mission, would share with the world the first glorious photos of our beautiful spherical blue marble in space. Our precious blue planet is a sphere of rock and metal, covered by a thin layer of air and, in many places, liquid water. To our distant ancestors, it wasn't obvious that the world was round. Greek geocentrism. Plato, 427–347 BCE. Aristotle, 384–322 BCE. Ancient Greece established several important legacies that strongly influenced Western civilization for thousands of years. Two of the most prominent thinkers of the classical era, the mathematician and philosopher Plato and his student Aristotle, who mastered almost all of the arts and sciences of the day, primarily shaped a cosmological worldview. Modern Western philosophy and science, including physics and astronomy, owe their basic foundations to Plato and Aristotle. The basic focus of ancient Greek astronomical thinking, and science in general, was to seek mathematical and physical explanations and models for observed phenomena. Turning to the geometry and trigonometry pioneered by Pythagoras for solutions was natural. Plato used geometry to divide the universe into two realms: the fixed sphere of the Earth and the nested, constantly moving spheres of the Sun, Moon, 5 known planets, and known stars, all of which revolved around a motionless Earth. To the region of the cosmos beyond the sublunary sphere, the region between Earth and the Moon composed of the basic elements earth, water, air, and fire, Aristotle added the element ether, which he believed constituted the rotating heavenly spheres that contained the stars and planets. This geocentric view of the cosmos was a major feature of Greek cosmology. Furthermore, the quest for symmetry and simplicity implied that the heavenly spheres should move in uniform circular motions or combinations, an interpretation consistent with much of the available astronomical data. However, Plato's model explains all of the observed motions of the sky. During the Roman Empire, Egyptian astronomer Ptolemy expanded the concept of perfect circular motions. Later, astronomers would challenge it until the 17th century, when the observational and theoretical work of Copernicus and Kepler officially put the geocentric model to rest. Western astrology. Ptolemy, along with Alexander the Great, 356–323 BCE. Astrology is the belief that the positions and motions of the sun, moon, planets, and stars at a person's birth or other significant moments influence or predetermine human and earthly matters. Most of human history's civilizations have adopted some form of this belief. Some scholars believe that the roots of Western astrology extend back to the earliest records of Sumerian cosmology in the 6th millennium BCE, when priests turned to the celestial sphere for signs that might help them to ascertain the will of the gods. See Birth of Cosmology. However, astrology transformed into what we recognize today. The Greeks transformed astrology from what had been an attempt by priests and kings during Babylonian times to understand the heavens' role in the success of the upcoming crop season, a potential war, or some other stately affair to a very personal enterprise, deriving the horoscopes of individuals, from kings to commoners, for events ranging from the historical to the mundane. A key force in the development of astronomy was Alexander the Great was a Greek king who studied under Aristotle and created and ruled over an expansive empire from northern Africa through the Mediterranean and Middle East. Alexander established the world's foremost learning center at the Great Library of Alexandria in Egypt, where the practice of horoscopic astrology began. The Egyptian astronomer Ptolemy, in particular, established the 12 classic zodiac constellations over the next few centuries and defined the planet's basic functions and roles in all science fields, from astronomy to medicine to zoology. Ptolemy's geocentric, astrology-driven cosmology would influence and dominate Western astronomical thinking for over 1,300 years. Belief in astrology is an easy notion to dismiss in the modern world. And yet newspapers still carry daily horoscope columns. Many people still flock to modern-day astrologers, or at least to astrological websites, for advice and so-called predictions about their futures. Maybe it's all a bit of fun, but something in human nature must thirst for this perceived order in the universe. Sun-centered cosmos Aristarchus, 310–230 BCE. The geocentric model of Plato and Aristotle permeated ancient Greek thinking about the cosmos. And why not? Everyone could see that the sun, moon, and stars rotated around the Earth. Scholars added another piece of supposedly irrefutable evidence. The moon went through phases consistent with orbiting our planet. Why wouldn't anything fly off the surface if the Earth rotated on its axis? None of the stars showed any observed parallax or shifting of position relative to other stars that they would show if the Earth were moving in its orbit. Case closed. There were doubters and skeptics, however. Aristarchus, an astronomer and mathematician from the Greek island of Samos, was the earliest on record. He challenged his esteemed Greek colleagues' nearly 200-year-old common wisdom by making detailed naked-eye observations of the sun and moon and trying to interpret them in a geocentric context, man's eye. Still, understanding the human eye limited his methods. Nevertheless, he deduced from geometrical calculations that the sun was at least 20 times farther away than the moon. The actual value is 400. He then deduced that because the sun and moon have about the same apparent angular diameter in the sky, the sun's size must be at least 20 times larger than the moon's and 7 times Earth's. Thus, according to his reasoning, the sun's volume was more than 300 times the volume of the Earth. The actual value is about 1 million. He must have found it absurd that a giant sun would bind itself to a relatively tiny planet like Earth rather than vice versa. He naturally advanced the idea that the Earth and other planets orbit the sun, and that the stars are so far away that we cannot observe parallax. Aristarchus's universe was much larger than anyone had described before. Like most revolutionary ideas, most of Aristarchus's colleagues ridiculed and disdained his idea of a sun-centered cosmos. 250 years later, Ptolemy's geocentric teachings and writings effectively crushed the idea. Aristarchus had planted a critical seed of doubt that would germinate in the 16th century. Eratosthenes measures the Earth. Plato, 427–347 BCE, Aristotle, 384–322 BCE, and Eratosthenes, 276–195 BCE. The Greeks generally accepted that the Earth is round, at least as far back as Pythagoras' time, but estimates of its actual size varied widely. Plato had guessed the Earth's circumference to be around 44,000 miles, 70,000 kilometers, corresponding to a diameter of about 14,000 miles, 22,000 kilometers, and Archimedes had estimated a circumference of about 34,000 miles, 55,000 kilometers, and a diameter of 109,000 miles, 17,500 kilometers. To make a more accurate determination, Eratosthenes, a mathematician, astronomer, and the third chief librarian of Alexandria, devised a simple experiment akin to treating the Earth as a giant sundial. Eratosthenes had learned that at noon on the summer solstice in the southern Egyptian city of Syene, the sun was almost exactly overhead, at the zenith, so posts in the ground did not cast any shadows. He also knew that in his city of Alexandria, in the north of Egypt, posts in the ground cast small shadows at noon on the summer solstice. He made some measurements and determined that the sun was a little over 7 degrees south of the zenith in Alexandria. This corresponds to about 1/50th of the circumference of a circle, so he surmised that the circumference of the Earth was about 50 times the distance between Alexandria and Syene. With a distance of about 5,000 stadia, the stadium was an ancient Egyptian and Greek unit of measure, between Alexandria and Syene, he estimated the circumference of the Earth at about 250,000 stadia, or 25,000 miles, 40,000 kilometers. Assuming that one stadium was about 175 yards, 160 meters, from Eratosthenes yields a circumference of about 25,000 miles, 40,000 kilometers, which is essentially the correct answer given the various uncertainties and assumptions involved in the measurements. Many people consider Eratosthenes the father of geography, having coined the term. He was the first to determine the Earth's size accurately. His method is also a fabulous example of the power of a simple, well-timed experiment. Archimedes once questioned levers. "Give me a place to stand, and I will move the Earth." Eratosthenes could easily have retorted, "Give me a few sticks and some shadows, and I will measure the Earth." Hipparchus, 190–120 BCE, is a stellar magnitude. Some stars are bright, others are dim. Anyone looking up at a clear night sky can determine that. But until the middle of the 2nd century BCE, no one had tried to quantify just how bright or dim it was. Hipparchus, the Greek astronomer and mathematician, established the first comprehensive star catalogue. Hipparchus decided to assign the stars a brightness using a scale of magnitudes that ranged from 1, for the 20 brightest stars, to 6, the faintest stars visible to the naked eye, with each step in the scale corresponding to stars that he judged to be half as bright as the previous step. Modern astronomers still use a brightness scale based on the original from Hipparchus, with some tweaks. In the mid-19th century, they redefined the magnitude system, making each step formally brighter or dimmer than the next by a factor of 2.5. They expanded the scale beyond 6 steps and linked it to the brightness of the bright star Vega, which is defined as having a magnitude of 0. We assigned negative magnitudes to extremely bright stars, planets, the Moon, and the Sun. At the same time, we pushed the maximum magnitude limit toward 30 for extremely faint stars, visible only with the world's most advanced telescopes. It seems odd that dimmer stars have higher magnitudes, but astronomers have gotten used to a system that's been around for over 2,100 years. Hipparchus invented trigonometry, discovered the precession of the Earth's spin axis, and obtained the most accurate measurements of the bright stars' relative positions, astrometry, to date. In recognition of his stellar, literally and figuratively observing skills, a 1989 orbiting space astrometry satellite was named in his honor. First computer. Sometime near the end of the 1st century BCE, a Roman ship carrying a large supply of ancient Greek artifacts sank in the Mediterranean off the coast of the Greek island of Antikythera. 2,000 years later, in 1901, divers came across the wreck and discovered, among the artifacts, the corroded remains of what may be the world's oldest computer, now known as the Antikythera mechanism. At first, archaeologists thought the mechanism might have been a mechanical clock because of its dozens of small gears. The artistry, comparable to mechanical clockwork in 17th century Europe, would have made this an amazing find in its own right. However, decades of cleaning and additional study revealed the device to be much more than a clock. It seems to have functioned as a sophisticated mechanical astronomical computer and calendar, capable of determining the past and future positions of the sun, moon, and planets in the sky, predicting eclipses, and displaying the moon's phases. It is the oldest, by 1,500 years, example of an orrery, a clockwork-like planetarium model of the solar system, superbly designed and built. The discoveries about this device are remarkable on so many levels. They reveal an extremely precise and detailed knowledge of planetary motions by the ancient Greeks, including subtle variations in the moon's velocity each month. The flawlessly functioning mechanisms indicate the construction of numerous devices, and their compact size implies their intended portability. In 1901, an ancient Greek shipwreck yielded one of the surviving fragments. In the modern world, we are accustomed to the close connection between technological advancements and scientific discoveries, so it should not be surprising to learn that this was also the case in ancient Greco-Roman times. Still, it is both humbling and jarring to discover evidence from a single artifact that a civilization was far more technologically advanced than we had thought before. Julian calendar, Julius Caesar, 144 BCE. Like other past civilizations tuned into the skies, the Romans developed a calendar system with strong astronomical connections. Originally designed in the 8th century BCE, the Roman calendar system caused constant confusion due to its amalgamation of elements borrowed from the Greeks and their predecessors. For instance, the year consisted of 10 months, each consisting of 30 or 31 days, totaling 304. However, the system ignored the remaining 61+ days required for an actual trip around the sun, referring to them as winter. A later change added 2 new winter months, January and February, but still came to only 355 days total per year. The high priests occasionally added a leap month to keep the calendar up to date with the seasons. Still, adding extra days to a given year was often arbitrary and politically motivated. The situation got so dizzy that many ordinary Romans had no idea what day, year, or month it was. The Roman calendar system was so confused when Julius Caesar came to power in 49 BCE that he ordered a reform that would align the calendar more with the motions of the sun than with the affairs of men. Julius Caesar added days to some of the 12 months, bringing the total number of days in a year to 365. He also decreed that every 4th year he would add an extra leap day to the end of February, making the average length of the year 365.25 days, close to the actual length of a solar year, 365.242 days. Caesar's reform of the calendar took effect on January 1st in the year 45 BCE, or to the Romans, 709 years after the founding of Rome, after the priests had to make the year 46 BCE 445 days long to try to fix all the problems that had accumulated before the reform. The Julian calendar worked well for a long time because it was only 0.608 days, about 11 minutes per year, which is different from a true solar year. By the 16th century, however, those 11 minutes per year had contributed to a significant shift between the calendar and solar years. Therefore, a further adjustment, known as the Gregorian calendar reform, was required to synchronize the calendar with the seasons. Ptolemy's Almagest, Ptolemy, 168 AD. For nearly 700 years, c. 300 BCE 400 CE, the Great Library of Alexandria in Egypt was the academic center of the world. The most famous Greek and Roman scholars we celebrate today, who pioneered mathematics, astronomy, or other fields, either visited or worked there, overseeing an amazing collection of hundreds of thousands of scrolls and books. The Egyptian mathematician and astronomer Claudius Ptolemaeus, Ptolemy, published the Almagest, the most famous book in classical astronomy, around 150 years ago. Ptolemy was a big-picture scientist. He mastered a variety of astronomical instruments and made important observations. Still, his greatest skill is culling and synthesizing the work of his predecessors over the previous 800 years to assemble a new comprehensive view of the cosmos in a single book. The Almagest had 13 separate sections, which included a detailed description of Ptolemy's geocentric cosmology, expanding on the ideas originally proposed by Plato, Aristotle, and others, and describing the orbits of the planets as moving in small circular paths, epicycles, that in turn are moving on larger circular paths, deferents, with the Earth at the center. The system was complicated, but fundamentally the stars and planets traveled only on perfect spherical or circular paths, with beauty and symmetry that fit the available data and likely appealed to Ptolemy as befitting the work of a perfect creator. The book also included what he referred to as handy tables to calculate the risings and settings of planets and stars, as well as chapters covering the general motions of the sun, moon, and planets, eclipses, precession, and observing tools. Hipparchus's star catalogue and the stellar magnitude system were the basis for a massive, for the day, catalogue of over 1,000 stars, a tube system. Sadly, Ptolemy's big-picture view of the solar system was wrong. However, because it was still so remarkably good at describing and predicting the motions observed in the sky, the Almagest and its geocentric depiction of the cosmos would remain the definitive source of astronomical information for over 1,000 years. Observe guest star in Chinese. Ancient Chinese astronomers were meticulous observers of the skies. Historians have noted that cadres of full-time, court-appointed civil servants, rather than individual scholars, often conducted official Chinese astronomy research, demonstrating a much more systematic and thorough approach to surveying the skies for changes than their Roman, Greek, or Babylonian counterparts and predecessors. Therefore, the Chinese observed and documented any new occurrences in the sky, incorporating these observations into the imperial dynastic records, many of which remain intact today. A prime example was the sudden appearance of what they called a guest star in the southern skies in the year 185. Chinese astronomers recorded this appearance as a notable event in the surviving annals of the Eastern Han Dynasty, 25220 CE. Despite the lack of drawings, modern astronomers were convinced that the Chinese had made the first recorded observations of a supernova. Modern optical, radio, and X-ray telescopes trained on that location reveal a semispherical gaseous nebula called RCW-86, which appears to be the expanded remains of that stellar explosion from more than 1,800 years ago. This is a modern view of the remains of supernova explosion 185. Ancient Chinese astronomical drawings, still preserved today, recorded many other guest stars. Among the most interesting are drawings that show objects with a bright, round head and one or more feathery or spiky tails. The Chinese referred to these objects as broom stars, and today many interpret them as bright comets with long gas and dust tails. Prominent comets observed by Chinese astronomers in 240 BCE and 12 BCE, as well as 141, 684, and 837 CE, are all likely to have been observations of the same comet, eventually recognized in 1682 as the 76-year periodic Halley's Comet. The careful, methodical skywatching and record-keeping of early Chinese astronomers have proven to be a rich treasure trove of data for studies by both historians and astronomers. Ariabatiya. In India, as in most other early civilizations, the roots of astronomy closely influenced the development of religion. Astronomical knowledge formed the foundation of early calendar systems that established dates for Hindu religious observances or seasonal planting and harvesting. Just as in the West, advances in instrumentation used by clerics and early astronomers for charting the positions of the sun, moon, and stars led to the development of more sophisticated cosmological schemes for explaining and predicting the motions of the sky. Aryabhata, a mathematician and astronomer, was the first of the great thinkers to make lasting contributions to the development of astronomy in India. He was the author of the oldest surviving Indian treatise on math and astronomy, the Aryabhatiya, published around the year 500. Aryabhata essentially summarized all mathematics in verse format in the Aryabhatiya and included convenient new scene tables for trigonometric calculations. In the astronomy sections of the Aryabhatiya, Aryabhata explained eclipses as the logical result of shadows from the Earth or the Moon, rather than the work of sky demons. Using some of his newly developed spherical trigonometry calculations and eclipse measurements, he calculated the Earth's circumference to an accuracy of less than 0.2% of its actual value, significantly improving upon Eratosthenes' previous best estimate of the Earth's circumference 750 years earlier. The most revolutionary aspect of Aryabhata's thinking was his claim that the Earth is not fixed in space, but spins on its axis, and that the stars in the celestial sphere are fixed in space. The Indian cosmology of Aryabhata's time was definitively geocentric. At the same time, his own accurate calculations of planetary positions relied on orbits and epicycles similar to those in Ptolemy's Almagest. Aryabhata was the first to advocate elliptical rather than circular paths for the planets. There are also suggestions in the Aryabhatiya, debated by scholars interpreting the original language and meaning, that Aryabhata believed in a sun-centered cosmos. However, like Aristarchus in Greece, such radical heliocentric ideas would take over 1,000 years to catch on in India. Finding Easter. Many of the world's religions celebrate special feast days and other holidays on dates that vary depending on the season, moon phase, tumult of a particular star, or some other astronomical circumstance not fixed on the calendar. This meant that the priests, monks, or other religious leaders responsible for determining the dates of these events in advance often had to be trained in, or at least be up to date on, the latest astronomy and mathematics. The calendar position of Easter, the Christian celebration of Christ's resurrection, is perhaps one of the most confusing of the world's major movable religious holidays to determine. In theory, Easter occurs on the first Sunday following the full moon after the spring equinox. In practice, however, predicting the date of the full moon or moon equinox was so confusing that astronomers of the Middle Ages invented a special word to describe calculating the calendar date of Easter each year: computers. In the early Middle Ages, many types of computers were in use, each with a different Easter date. A monk named Bede of Jarrow, hailing from the Kingdom of Northumbria in what is now part of northern England and Scotland, proposed a standardized computer in the early 8th century. He described and widely circulated it in his books, On Time and On the Reckoning of Time. Bede's computers and his education in astronomy led him to discover that the date of Easter repeats in a 532-year cycle made up of 19-year lunar and 28-year solar cycles. Finally, he could predict the date of the most significant Christian holiday of the year. Bede's computing skills and prowess as a historian and theologian earned him the nickname Venerable Bede. His writings were also influential throughout the Middle Ages because they clarified many other practical solar, lunar, and tidal calendar calculations. He even dabbled in calculating the Earth's age based on the Book of Genesis. He came up with 3952 BCE, not far from the 4004 BCE estimate popularized in the 17th century by the Anglican Archbishop James Ussher. Early Islamic astronomy. Habash al-Hasib, c. 770-870, Muhammad ibn Musa al-Khwarizm, c. 700 850, Muhammad ibn Jabir al-Harran al-Batan, c. 858-929, Abu al-Rayhan al-Barun, 973-1048. In medieval Islam, a several century-long burst of genius and creativity in the arts and sciences is responsible for much of astronomy and mathematics' modern language and methodology. Scientific development stagnated in Europe during this period, so it was primarily the Persian and Arab worlds that became the heirs to the Greco-Roman legacy of astronomy and mathematics. Among the many early Islamic astronomers and mathematicians who made important new contributions were Al-Khwarizmi, who founded modern algebra, al-Jabr or completion in Arabic, and developed new methods for calculating the positions of the sun, moon, and planets. Al-Hassab, who calculated the best estimates yet made for the diameter and distance of the moon and moon diameter of the sun, and compiled his observations in the Book of Bodies and Distances. Al-Batan, who refined results from Ptolemy's Almagest and developed new methods of timing the first appearance of the moon's moonsant. And Al-Barun, who invented new astronomical instruments and observing methods, and who, along with several other Persian and Arabic astronomers, hypothesized that a sun-centered model of the solar system could fit the available observational data as well as the widely accepted Earth-centered model. Indeed, the work of these and other medieval Islamic astronomers influenced Renaissance Western astronomers such as Brahe, Kepler, Copernicus, and Galileo, leading to the eventual overthrow of Ptolemaic geocentrism in favor of heliocentric cosmology. Furthermore, almost all noted astronomers and mathematicians of early Islam worked as teams in the world's first research groups, part of the world's first system of state-run observatories and research institutes. Islamic scientists have achieved significant advances in astronomy and other fields thanks to this collaborative environment, which is the foundation for most science practices today. Andromeda sighted. Another important early astronomer from the Arab world was Abd al-Rahman al-Sufi of Persia, modern-day Iran. Like most other astronomers of the Middle Ages, Al-Soph was aware of the major aspects of classical Greek astronomy and cosmology, including Ptolemy's Almagest, which he translated into Arabic. He and others sought to expand on Ptolemy's ideas and synthesize them with new observations and theories from early Arabic astronomy, the Book of Fixed Stars, a landmark work. Al-Soph's book was essentially a detailed map of the stars in the 48 then-known classical Greek constellations, using star data based on Ptolemy's older catalogue in the Almagest and Hipparchus's stellar magnitude system, but refined or corrected using his and other newer observations of stellar brightness and colours. The Book of Fixed Stars uses the Arabic names for the bright stars in each constellation. We still use many of these star names, including Altair, Betelgeuse, Deneb, Rigel, and Vega today. In the section of Al-Soph's book devoted to the constellations Andromeda and Pisces, he notes a little cloud detected among the major stars. Although he could never have known it, Al-Soph is widely believed to have made the first recorded observation of the Andromeda galaxy, the nearest, about 2 million light-years distant spiral galaxy to the Milky Way. Also known as Messier Object 31, Andromeda is nearly 8 times larger than the full moon. The moon is extremely faint, so it takes excellent eyesight and patience to detect. Al-Soph was also the first to detect other faint star clusters, nebulae, and clouds, including one of the Milky Way's faint elliptical companion galaxies in the southern skies. 550 years later, Europeans prominently noted and popularized this object, naming it the Large Magellanic Cloud, following Ferdinand Magellan's voyage around the world in 1519. Experimental astrophysics. Ancient Greek scholars had predominantly philosophical or theoretical interests in science, especially astronomy. In contrast, the Arabic style of astronomy and mathematics that came to dominate the Middle Ages was more focused on inventing new instruments or methods, acquiring new observations, and using the data to develop new ways to address practical religious or other societal needs. This way of thinking was new. Observe, record, analyze, interpret, hypothesize, and repeat. It proved to be very effective, and it is the root of the modern scientific method. A few prominent Arab and Persian mathematicians around the turn of the first millennium CE laid the foundation for this new, observationally focused approach to understanding the cosmos. Abd al-Hassan ibn al-Haytham was a Muslim physicist and mathematician who specialized in many fields and advocated experimentation and critical tests of prevailing theories rather than reliance on speculation or natural philosophy. He was a critic of Ptolemy. In his book of Optics, he wrote, "In all we do, our purpose should be balanced, not arbitrary, the search for truth, not the support of opinions." Around the same time, the Persian scholar Abu ar-Rayhan al-Biruni, another expert in a wide range of physical and social sciences, advocated a similar approach to experimentation in astronomy and other fields, introducing new approaches such as repeat experiments and analysis of random and systematic errors in derived results. "I do not shun the truth from whatever source it comes," he wrote in his comprehensive canon of science, Kitab al-Qanun al-Masad. In many ways, al-Haytham, al-Biruni, and many other such polymaths of the Middle Ages were the world's first scientists, passionate about observation and discovery across a wide range of fields, skeptical of so-called truths that could not be verified, and intrinsically self-critical. For more than 1,000 years, such traits have served scientists well. Mayan astronomy. Europeans and Asians were not the only ones studying and practicing astronomy in the prehistoric and Middle Ages. Indeed, a rich astronomical tradition had emerged in Mesoamerica, going back to at least 2000 BCE, in complex and advanced indigenous civilizations like the Maya, Olmec, Toltec, Mississippian, and other related cultures. However, these civilizations left behind few written records, partially due to the loss or destruction of many during later European conquests. For the Mayan civilization, peaking from c. 2000 BCE to 900 CE, only 4 surviving books are available to assess the level of scientific knowledge of this once dominant Mesoamerican culture. The Dresden Codex, named after its current archive, is one of those books from the late period of Mayan history, shortly before European contact. It provides fascinating and revealing evidence that Mayan astronomy had reached a level of advancement and sophistication comparable to that of the Greeks, Arabs, and other early societies. The Dresden Codex is part history and part mythology. Still, it is mostly a series of detailed astronomical tables for charting and predicting the motions of the Sun, Moon, Venus, and other known planets. After deciphering the glyphs and numeric symbols, archaeoastronomers determined that the 74 pages of illustrated tables track the cycles of Venus, which repeats its pattern of rising and setting every 584 days, and the Moon, 8 moons repeat every 25,377 days. The Mayans, who recognized the various repeating eclipse cycles with much higher precision than their Babylonian and Greek counterparts, could also use the tables to predict eclipses. They could also predict lunar and planetary conjunctions with great accuracy. With such precision, centuries of careful, detailed observations and sophisticated instruments must have been required to know these periodicities in the heavens. Once they discovered the cycles, the Mayans could use the tables to predict the heavens forever. What did the Mayans do with this information? Much remains a mystery, but historians have identified many potential religious, agricultural, social, and even military events and traditions tied to their astronomically derived calendar system. Daytime star observed. By the end of the early Middle Ages, several societies had flourishing or nascent communities of astronomers and mathematicians tuned into the heavens. When a new star suddenly and dramatically appeared in the Taurus constellation in 1054, many of those societies took notice. Chinese astronomers first recorded the appearance of a guest star on July 4th. Persian, Arab, Japanese, and Korean observers corroborated their observations, and Native American Anasazi artists even recorded the event in rock paintings. The Europeans, still mired in the Dark Ages, didn't record the event. Chinese observers saw the new star during the day for 23 days and at night for 653 days, until it faded away. At maximum brightness, it was estimated to be around magnitude 6 or 7, brighter than everything in the sky except the sun and moon. We now know that what these medieval astronomers had observed was a supernova, the violent, catastrophic explosion of a massive progenitor star about 6,300 light-years from Earth that ran out of fuel for nuclear fusion and collapsed in on itself, releasing an enormous amount of gravitational energy that expelled the star's outer layers into space at enormous speeds, perhaps as high as 10% of the speed of light. 18th century astronomers first detected the crab-shaped emission nebula of ionized gases heated by the explosion's shockwave, more than 650 years after the supernova faded from view. In the late 1960s, radio astronomers discovered that the compressed core of the original star had become a rapidly spinning, 30 times per second, neutron star or pulsar that is probably only about 12 miles across, but has a mass of about 1.5 to 2 times that of the Sun. Early astronomers' careful records of this event helped establish the previously unknown link between supernovae, emission nebulae, and neutron stars. Desfire. The slow emergence of Western Europe from the Dark Ages coincided with the founding of the world's first universities, in Bologna and Oxford, near the end of the 11th century. The creation of more higher education institutions necessitated the need for scholarly works to serve as textbooks for students. Printing books in medieval Europe was expensive and cumbersome, so only a few standard textbooks proliferated in certain fields. The English monk and astronomer John of Sacrobosco published a tract named De Sphæra around 1230, which became Western Europe's first standard astronomy textbook. Sacrobosco taught at the University of Paris and believed strongly in Ptolemaic cosmology. Much of De Sphæra is a summary and review of the Almagest. However, the text also incorporates more modern ideas and discoveries from Arabic astronomy, a developing field of experimental astronomy that was far more advanced than European astronomy in the Middle Ages. In addition to its review of Ptolemy, De Sphæra also included illustrated definitions of the celestial spheres and circles, likely intended for use as a tutorial for students learning how to use an armillary sphere, reviews of rising and setting times and circumstances for bright stars and the Sun, and descriptions of the motion of the Sun and planets using Ptolemy's epicycle and deferent model. Sacrobosco made it unambiguous that the Earth is a spherical body and provided accurate explanations for solar and lunar eclipses. If a medieval book bestseller list existed, De Sphæra would have been on it for hundreds of years. Between the 13th and 15th centuries, many copies underwent hand transcription. Hundreds of manuscripts still exist today. And following the appearance of the first printed edition in 1472, more than 90 editions saw printing over the next 200 years. Reading was required in university astronomy classes well into the 17th century, according to historians. Large medieval observatories. It is easy to think of astronomical observatories as modern-day inventions. Enormous domes on high mountains, giant telescopes, and high-tech computer equipment. The concept of the observatory as a research institute and a shared access facility for teams of astronomers, however, can trace its roots back to the first observatories established in the Islamic world and China in the Middle Ages. The Margay Observatory in northwestern Iran was one of the first major observatories in the world, established in 1259 by Mongol ruler Hulagu Khan, grandson of Genghis, and directed by his court astronomer and mathematician Nasser al-Din al-Tusi. Maragay housed a huge library of more than 40,000 books, and Al-Tis led a team of astronomers and students to perform observations and calculations of planetary motions and Earth's precession, which Copernicus and others would later use as key inputs for a new heliocentric cosmology. Around the same time, Hulagu's brother Kublai Khan established the Gaocheng Astronomical Observatory, as the first facility in China. In the early Yuan dynasty, 1279–1368, astronomers made observations of the sun and planets. They used an enormous stone sundial to reckon time and more accurately determine the length of the year. The Timurid astronomer and mathematician Ulugh Beg established a university and observatory in Samarkand, in what is now Uzbekistan, in 1420, inspired by the destroyed Marghe. The Samarkand Observatory, later named Ulugh Beg Observatory, included early astronomical instruments such as astrolabes and armillary spheres, as well as a giant stone sextant tranche meridian circle with a radius of 131 feet, 40 meters, carved into the mountainside, the largest of its kind in the world, for accurately measuring the positions of the sun and stars. Astronomers at Ulugh Beg updated Ptolemy's and Alsof's star catalogues to account for precession, enabling consistently accurate predictions of eclipses and other celestial events. Early calculus. Astronomical research in India through the Middle Ages was initially based on the early findings and writings of Aryabhata and other mathematicians and astronomers. It was ultimately expanded by the creation of dedicated research and teaching groups like the Kerala School of Astronomy and Mathematics, founded in the 14th century by the mathematician Madhavan of Sangamagramam. Madhavan and subsequent Kerala mathematicians like Nilakantha Somayaji developed mathematical methods of estimating the motions of the planets based initially on geometry and trigonometry, and later on newly developed techniques for modeling complex curves and mathematical shapes using combinations of functions. Parabolas, hyperbolas, and ellipses were among these shapes. Their work on ellipses proved particularly relevant to astronomy, as it validated Aryabhata's earlier conjecture that elliptical orbits could describe the planets' paths. The new mathematical methods developed in Kerala focused on a series of functions, which were early versions of calculus, predating the European development of calculus some 200 years later by scientists like Isaac Newton. Nilakantha's work, Aryabhatiyabhasya, a commentary on Aryabhata's Aryabhatiya, published around 1500, further demonstrated that a rotating Earth and a partially heliocentric solar system provided a more accurate way of fitting the planetary orbits. In his model, Mercury, Venus, Mars, Jupiter, and Saturn all orbited the Sun, but the Sun orbited Earth. The 16th century Danish astronomer Tycho Brahe adopted a similar model, and some aspects of Nilakantha's model align with the fully heliocentric cosmology that Polish astronomer Nicholas Copernicus proposed in 1543. The West may have previously underappreciated the contributions of the Kerala school and perhaps of Indian mathematics and astronomy in general. It's evident that the Kerala school, and perhaps Indian mathematics and astronomy in general, should be considered among the shoulders of giants who supported the later discoveries of Copernicus, Newton, and others. Copernicus's De Revolutionibus. After nearly 1,000 years of stagnation, the Renaissance in Western Europe was truly an awakening of art, music, culture, and science. The establishment of universities in Bologna, Oxford, Cambridge, Paris, Padua, and other locations, along with the introduction of astronomy advancements by Arabic, Chinese, and Indian scholars during Europe's Dark Ages, and the reintroduction of Greek and Roman works, paved the way for the flourishing of European science. The first, and in some ways most important, Renaissance scientist to take that stage was Nicolaus Copernicus, a Polish canon. His uncle, who was also his patron, was a bishop, doctor, lawyer, economist, and part-time astronomer. As a community leader in Frombork in northwestern Poland, Copernicus assumed many legal, administrative, and economic responsibilities as his nominal vocation. But he also made the time to conduct astronomical observations and analyze his data, to read classical and contemporary astronomical literature, and to meditate on problems that he had ever since he was a student at Krakow and Bologna, with what he regarded as the overly complex geocentric planetary orbit model of Ptolemy's Almagest. By 1514, he was circulating the basic outline of an alternative paradigm, a solar system with the sun fixed at the center, the Earth and the other planets spinning on their axes and orbiting the sun, and the moon orbiting the Earth. But it wasn't until just before he died in 1543 that he finally published his theory as De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres. The book and its sun-centered thesis generated little interest or controversy at the time. It would take more than 50 years, along with the supporting observations and interpretations of Brahe, Kepler, and Galileo's telescope, to make it apparent that De Revolutionibus had started what became widely known as the Copernican revolution in cosmology. Brahe's Nova Stella, Tycho Brahe, 1546–1601. For astronomers before the 17th century, making the best possible naked-eye observations of the motions of celestial bodies meant having the best possible equipment and the keenest possible eyesight. Except for some Chinese astronomers, only some recognized the value of numerous, consistent, and systematic observations of the heavens to maximize the accuracy of their data. Perhaps the Renaissance astronomer and Danish nobleman Tycho Brahe was the best Western practitioner of this brute force approach to reducing errors in measuring planetary motions. As a teenager in 1560, Tycho witnessed a solar eclipse which ignited his passion for astronomy. His family's wealth and connections allowed him to pursue that passion and build world-class observation facilities. He immersed himself in cosmology, but subscribed neither to Ptolemy's geocentric theory nor Copernicus's heliocentric view. Rather, his careful observations of new comets and a new star that appeared in 1572, Tycho coined the term nova, convinced him that the fixed stars were not fixed, and that they and the planets did not move along the transparent crystalline spheres that the Ptolemaic and Copernican systems posited. His cosmologic model was similar to that of Nilakantha's from the Kerala school, a geo-heliocentric hybrid in which all the planets except Earth orbited the Sun, and the Sun and Moon orbited Earth. Tycho set the standard for high-quality observations of planetary motions using the best instruments, a near-continuous data set over many decades, and a thorough description of the uncertainties in his data. Theorists coveted his measurements, and he was particular about his choice of collaborators. I eventually chose to work with Johannes Kepler, as his amazing data set led to Kepler's discovery of the fundamental laws of planetary motion. Tycho was as eccentric as he was thorough, losing part of his nose in a duel, replacing it with prosthetics of copper or silver, and partying himself to death at the age of 54. Gregorian calendar. Most of us think of a year as 12 months or 365 days, and we don't give it much more thought. However, every 4 years we receive a reminder that the duration of one trip around the Sun is closer to 365.25 days. This is why the Julian calendar reform of 45 BCE mandated adding February 29th as a leap day every 4th year to keep Caesar's calendar system synced with the Earth's motion around the Sun. The Julian calendar assumes a year from the vernal equinox to the vernal equinox. 365.25 days turned out to be too long by about 11 minutes per year. The actual value is about 365.24237 days. This mattered little during the Roman Empire, but 1,500 years later, the calendar date deviated more than 10 days from the solar or seasonal date that Caesar had assigned. The spring equinox, as determined by astronomers, was occurring around March 11 instead of March 21. This meant the Easter feast was drifting back into winter, which the Catholic Church disliked. A fix was needed. Julius Caesar's 45 BCE calendar reform required a revision. The Roman Catholic Council of Trent decided to modify Caesar's calendar so that instead of 1 out of every 4, 0.25 years being a leap year, it would now be 97 out of every 400, 0.2425 years, established by designating only every century year, divisible by 400 as a leap year. So the years 1700, 1800 and 1900 were not leap years, but the year 2000 was. Pope Gregory XIII issued the new Gregorian calendar plan on October 15, 1582, after correcting the 10-day drift on October 4, 1582. In wide global use today, the modern Gregorian calendar stays true to the Earth's orbital position for better than 1 day out of every 7,600 years, good enough for the foreseeable future. However, the Earth's spin slows slightly over time because of tidal friction, so the day's length slowly increases. As a result, since 1972, the International Earth Rotation and Reference System Service, there is such a service, have occasionally added official leap seconds to the world's atomic clocks to keep them in sync with our planet's slowly changing spin and thus the slowly changing apparent solar time. Mirror variables. Astronomers of the 16th century knew that a seemingly ordinary star would occasionally flare up and dramatically increase in brightness, what Tycho Brahe had termed a nova. But no one had ever observed a star brighten, dim, brighten and dim again. That's what the Dutch-German pastor and part-time astronomer David Fabricius discovered in his observations of the star Omicron Ceti, also known as Mira, in 1596 and again in 1609. In 1638, the Dutch astronomer Johannes Holvarder discovered that Mira was a periodic or pulsating variable star lasting about 330 days. When Fabricius discovered Mira, a magnitude 3 star dimmered quickly within a month or so, surpassing the human visual limit of magnitude 6. Later, astronomers monitoring Mira telescopically saw it brighten to magnitude 2 and dim to magnitude 10, a factor of over 1,700 in brightness. We now know that Mira is a puffed-up red giant star about 350 times bigger than the Sun. If Mira were in our solar system, it would extend out to Mars' orbit. Its pulsations are part of normal stellar evolution for relatively low-mass stars near the end of their lives. Nearly 7,000 stars are now known to exhibit pulsations like this, with periods ranging from around 100 to 1,000 days, collectively referred to as Mira variables. In 1923, scientists discovered Mira in a double-star system with a smaller white dwarf companion known as Mira B. Recent Hubble Space Telescope and Chandra X-ray Observatory images show that Mira B is gravitationally pulling gas off Mira A and into a solar nebula-like disk that may be accreting planets. Mira is a dying star, but it may give life to new planets in its death throes. Fabricius and his son Johannes are also credited with being the first astronomers to observe sunspots systematically and use them to discover that the Sun rotates, as predicted by physicist Johannes Kepler, and has a rotation period of about 27 days. Astronomers have discovered that Mira has star spots, similar to sunspots, which may be associated with strong magnetic fields in the star's outer layers. Bruno's book, On the Infinite Universe and Worlds, is fascinating. His 16th century peers did not widely accept the heliocentric view of the solar system promoted by Copernicus in 1543. Although the idea that the Earth was not the center of the universe was inconsistent with the scriptures of the 16th century Roman Catholic Church, Copernicus, a church canon, was, ironically, never the focus of much controversy regarding his views. Others would soon inherit that controversy, however. One of Copernicanism's earliest and most vocal advocates was the late 16th century Italian philosopher, astronomer, and Dominican friar Giordano Bruno. Bruno appears to have been an outspoken advocate of several unorthodox and controversial views about science, religion, and natural philosophy. While not known for particular observations, skills, or discoveries, Bruno eventually believed in non-geocentrism, far more extreme than Copernicus had espoused. In his 1584 book, Dell'infinito universo e mondi, On the Infinite Universe and Worlds, Bruno postulated that Earth was just one of an infinite number of inhabited planets orbiting an infinite number of stars, which are just suns like our own. To the Church, advocating such a plurality of worlds was mildly heretical. Bruno made it wholesale heresy with other brash demotions of the central tenets of Christian theology, such as the non-centrality of even God in his infinite universe. The Inquisition persecuted him for over 15 years, leading to his eventual arrest, trial, conviction, and burning at the stake in Rome in 1600. It is tempting to romanticize Bruno simply as a scientific martyr fighting for the truth against a dogmatic regime, especially because some of his ideas about cosmology and the plurality of worlds have turned out to be right. But others before him had held views at odds with the Church, as did others of his contemporaries, most famously Galileo, without suffering as drastic a fate. Bruno's demise may have been less about his Copernicanism than his aggressive style and passion for outspoken criticism of authority and so-called common wisdom. The earliest astronomical telescopes. The popular myth is that the Italian astronomer Galileo Galilei invented the telescope. While it is true that Galileo Galilei invented an astronomical telescope of unprecedented resolution for his time, he used it several years earlier to make discoveries that firmly established the heliocentric nature of the solar system. Its basic principles and components date back to antiquity. The earliest telescopes were so-called refracting instruments because they used combinations of concave and convex glass lenses to bend and magnify, or diminish, in the case of the earliest microscopes, the field of view. The knowledge that curved, transparent surfaces could magnify images was known to the Egyptians in the 5th century BCE and to Greek and Roman scholars. People believed that China or the Arab world invented glass lenses for spectacles to correct bad eyesight in the 11th century or possibly earlier, and introduced them to the West in the late 1200s. Making spectacles was widespread in late medieval and early Renaissance Europe. In that environment, at least 3 Dutch craftsmen and lens makers may have independently invented devices between about 1604 and 1608 that we would call telescopes. Hans Lippershey, Zacharias Janssen, and Jacob Metius designed simple nested tubes, spyglasses, containing 2 lenses that would yield 2x3x magnifications of a small field of view. The Dutch granted Lippershey a patent for his version, leading to his frequent citation as the telescope inventor, although the true history remains actively debated. In 1609, simple spyglasses began selling quickly in Europe. Since the design was relatively simple and lenses were fairly easy to procure or grind, astronomers like Galileo, Thomas Harriot, and others began tinkering with and enhancing the invention and pointing it upward. Galileo made several versions of increasing power. His telescope of late 1609 achieved a magnification of about 20x, allowing him to see details of the heavens that no one had previously observed, and to change astronomy forever. This 19th century painting by French artist Henri-Julien Détouché, 1854-1913, depicts Galileo presenting an early version of his newly invented astronomical telescope to the Duke of Venice, Leonardo Donato, in 1609. Galileo's starry messenger. Revolutions often begin with a single pivotal precipitating event from which an entire movement emerges. In the case of the scientific revolution, a movement that continues to this day, the single event was arguably the publication of a small treatise called Sidereus Nuncius, Starry Messenger, in 1610, by the Renaissance Italian physicist, mathematician, and astronomer Galileo Galilei. The Starry Messenger changed the history of astronomy. Galileo constructed one of the first, and at that time, the best, astronomical telescopes, and used his instrument to observe the heavens in unprecedented detail. He was the first human being to see and track Jupiter's satellites, and he realized that not all planetary bodies orbit the Earth. He was the first person to see the phases of Venus, and thus to know that it must be orbiting the Sun and not the Earth. He was the first to realize that the Moon has mountains, craters, and valleys, and is not a perfect celestial sphere. Galileo's observations and subsequent interpretations in Starry Messenger directly refuted Aristotle's and Ptolemy's geocentric cosmology. They provided compelling evidence, though not proof, of Copernicus's sun-centered cosmology. To Galileo, however, it was proof enough. He continued to make observations with successively more powerful telescopes, recording the disks and features of the planets and resolving the Milky Way into countless densely packed stars. His telescopes allowed him and other contemporaries, who confirmed and expanded on his work, to see stars as faint as magnitudes 8 or 9, more than 15 times fainter than those visible to the naked eye. Galileo's phases of Venus. He had powerful supporters in the Roman Catholic Church, who initially supported his discoveries. But as Giordano Bruno's execution had shown, the Church eventually regarded Copernicanism as a threat. The Church spared Galileo, but forced him into house arrest for the last 9 years of his life. Galileo's January 8, 1610, drawing depicts Jupiter's 4 bright satellites, with the red arrow highlighting Io's position that night. When Galileo first trained his telescope on Jupiter on January 7, 1610, he noticed what he described as 3 fixed stars, totally invisible by their smallness. The stars were right next to Jupiter, 2 on one side and 1 on the other, all in a straight line that passed through the center of Jupiter's disk. Imagine his amazement when he saw 4 tiny stars the next night instead of 3, all along the same line. As he watched over the next few weeks, the little stars moved relative to the planet. It didn't take long for him to spot the pattern. They were orbiting Jupiter. Galileo had discovered 4 new worlds, the first known moons of another planet besides ours. He earned the right to name them because he was their discoverer. In a politically astute move, he named them the Medicean stars after his patron and funding source, Cosimo II de' Medici. Other contemporary astronomers hated the idea. The German astronomer Simon Marius, who claimed to have discovered the moons before Galileo, proposed names from Greek mythology: Io, a nymph Zeus seduced, Europa, Ganymede, and Callisto. Galileo hated other naming options and eventually started calling the moons Jupiter the Firm through I-4. Astronomers used those designations well into the 20th century, but Marius's more romantic naming scheme finally stuck. We now collectively refer to them as the Galilean satellites, honoring their discoverer. Io, pronounced I-O, is the closest of Jupiter's 4 large moons, with an orbital period of about 42 hours. 7 space missions, Pioneers 10 and 11, Voyagers 1 and 2, Galileo, Cassini, and New Horizons, have now studied it up close, revealing it to have a diameter of 2,275 miles, 3,660 kilometers, slightly larger than Earth's moon, and a surprisingly rocky density of 3.5 grams per cubic centimeter. The biggest surprise was Voyager 1's discovery of active volcanoes on Io, which cover the moon's surface with red, orange, and black sulfur and silicate lava, and their thin sulfur dioxide atmosphere. Strong tidal forces cause constant eruptions on Io, making it the most volcanically active world in the solar system. Europa. Galileo's January 8, 1610. Drawing depicts Jupiter's 4 bright satellites, with the red arrow highlighting Europa's position that night. Another small star that Galileo discovered orbiting Jupiter is Europa, named after a princess who loved Zeus, the Greek version of the Roman god Jupiter. Galileo had seen Io and Europa together as a single star on January 7, 1610. By the next night, they had moved enough for him to distinguish them as 2 objects. Europa is the second closest Galilean satellite to Jupiter, and it takes about 3.5 days to orbit the giant planet. Galileo developed a method to accurately predict the movements of Europa, Io, Ganymede, and Callisto, and proposed to use the relative positions and timing of their occasional eclipses as a natural celestial clock to determine longitude. Explorers like Lewis and Clark successfully used Galileo's method, which the Italian-French astronomer Giovanni Domenico Cassini verified in 1681. Observations from the 7 robotic space probes that have visited the Jovian system reveal that Europa is the smallest of the 4 large moons, with a diameter of 1,150 miles, 3,140 kilometers, slightly smaller than Earth's moon. We can estimate a planetary body's mean density by dividing its mass, which we determine by how much the body bends the trajectory of a passing space probe, by its volume, which we determine from photographs. We interpret Europa's density of about 3 grams per cubic centimeter as mostly rocky despite its icy surface. That surface was extraordinarily smooth, young, with very few impact craters, crisscrossed with intersecting reddish cracks and streaks, and broken up into many fractured and jumbled plates that appear to have moved tectonically relative to each other. Up close, the surface is reminiscent of sea ice. Indeed, several lines of evidence point to a deep liquid ocean on Europa under a relatively thin, icy crust. The possibility of another ocean in our solar system, warmed by tidal energy and protected from Jupiter's harsh radiation, raises the prospect that Europa may be another abode for life. Ganymede. Galileo's drawing from January 8, 1610, depicts Jupiter's 4 bright satellites, with Ganymede's position that night highlighted by the red arrow. The third of Galileo's newly discovered moons of 1610 is Ganymede, named after the mythological prince, cupbearer of the gods, and lover of Zeus. Ganymede is the only moon of Jupiter named after a male figure. Ganymede takes a little more than 7 days to make one orbit of Jupiter. When Galileo and other astronomers worked out the precise orbits of Io, Europa, and Ganymede, they noticed something very interesting. For every single orbit of Ganymede, Europa orbits exactly twice, and Io orbits exactly 4 times. Astronomers describe the satellites as being in resonance. The discovery of the 4-2-1 orbital resonances of the 3 inner Galilean satellites spurred a mini-revolution among mathematicians and physicists, trying to understand and explain how those resonances came to be. The French mathematician and astronomer Pierre-Simon Laplace worked out key explanations, and in honor of his achievements, we now call these kinds of 3-body situations Laplace resonances. Researchers have discovered that orbital resonances create gaps in the main asteroid belt and Saturn's rings, and they are also present in some newly discovered extrasolar planets. Many robotic spacecraft have also closely studied Ganymede, revealing it to be the largest moon in the solar system, measuring 3,275 miles, 5,270 kilometers, in diameter, even larger than Mercury. The 1.9 grams per cubic centimeter density suggests that Ganymede contains a significantly higher relative percentage of ice than Io and Europa. Brighter, more ice-rich grooves and ridges on Ganymede's surface, potentially the result of past tectonic activity, appear younger than the darker, more heavily cratered terrains. Ganymede is the only moon in the solar system with its own weak magnetic field, indicating that the interior has differentiated into a crust, mantle, and molten iron core. Perhaps most interestingly, the magnetic readings, salty surface minerals, and evidence for past water eruptions into some grooves and ridges could all be consistent with a deep underground layer of liquid water. Yet another ocean. Inside Ganymede, Callisto. Galileo's January 8, 1610. Drawing depicts Jupiter's 4 bright satellites, with the red arrow highlighting Callisto's position that night. Callisto is the farthest of the Galilean satellites from Jupiter, named after another Greek mythological nymph and lover of Zeus. Galileo first trained his astronomical telescope on the giant planet in early 1610, discovering Callisto and Jupiter's other major moons. Callisto is the farthest from Jupiter of the 4 major satellites, taking almost 17 days to complete one orbit. As a result, it does not participate in the resonances that characterize the orbits of Io, Europa, and Ganymede. For more than 350 years after their discovery, astronomers couldn't learn more about Callisto and the other Galilean satellites. Starting in the 1960s, however, it became possible to use spectroscopy from ground-based telescopes to determine their surface compositions. We discovered that water ice dominated the surfaces of Callisto, Ganymede, and Europa, while sulfur dominated the colors and spectra of Io, which was dry. Spectroscopy from more recent space missions has further revealed the presence of carbon dioxide and sulfur dioxide ices on Callisto and Ganymede, and hydrated sulfate salts on all three icy moons. These missions have also allowed for the determination of Callisto's diameter, 2,995 miles, 4,120 kilometers, 25% larger than our moon, and density, 1.8 grams per cubic centimeter, mostly icy with some rock, as well as the mapping of its surface features. Callisto is the most heavily cratered of the Galilean satellites, preserving giant impact basins from the late heavy bombardment of the early solar system, and suggesting that it has had the least internal activity or resurfacing history of the four. However, data from NASA's Galileo Jupiter mission suggests otherwise. The orbiter suggests that there could be a layer of liquid water, an ocean deep beneath the scarred, icy crust. However, Callisto lacks the tidal flexing and heating that the other moons experience from their resonant orbital interactions or proximity to Jupiter, leaving the heat source responsible for Callisto's potential subsurface ocean a mystery. Orion Nebula discovered. The universe is full of atoms and molecules that sometimes form into gas, dust, and rock in strange and beautiful forms. Astronomers can search for and catalogue the universe by finding places where the gas and dust are so warm and dense that they glow in the dark. These places are interstellar clouds, the wispy, nebulous, filamentary remains of dead and dying stars that are, at the same time, the cocoons and nurseries of new young stellar embryos. When stars die in nova or supernova events, they eject their outer layers of hydrogen, helium, and other materials into deep space. Energy from nearby stars, or the explosion that ejected them, can often ionize these ejected remains. Ionized gases in interstellar clouds emit light and heat, allowing astronomers to observe and characterize them using spectrometers and large telescopes. The most famous interstellar cloud in the sky is the Orion Nebula, a fuzzy patch of light visible to the naked eye just below the three stars in Orion's belt. While some archaeological evidence suggests ancient Mayan astronomers noticed the nebula, French astronomer Nicolas Claude Fabry de Peiresc first recorded observing it in 1610, though he never reported it. Christian Huygens and Charles Messier rediscovered it in 1656 and 1769, respectively. Modern observations have revealed that the Orion Nebula is the closest interstellar cloud to us, at only 1,340 light-years away. Its composition is surprisingly complex and includes hydrogen, carbon monoxide, water, ammonia, formaldehyde, and simple precursors to amino acids. Interstellar clouds are also places where new stars are born, as pockets and clumps of gas and dust slowly accrete and collapse under their gravity. Just as the Orion Nebula formed from previous generations of local stars, a giant solar nebula cloud of gas and dust formed our solar system and perhaps others in our local neighborhood. The three laws of planetary motion. While there is significant overlap, astronomers today can be generally characterized as either observationalists, those who primarily collect data from telescopes or space missions, or theorists, those who primarily try to develop models or theories to explain existing observations. Most astronomers, and astrologers, from antiquity through the Middle Ages, were observationalists who dabbled in theory. Theoretical astronomy had been primarily considered the realm of philosophers, not physicists. The Renaissance German mathematician, astrologer and astronomer Johannes Kepler changed that paradigm and arguably became the world's first theoretical astrophysicist. Kepler worked with data from others, most notably Tycho Brahe and Galileo, in his quest to develop a single, unifying model of the cosmos. Deeply religious, Kepler believed God had designed the universe in an elegant geometric plan, which he could reason through careful observations. Kepler believed in Copernicus's heliocentric cosmology, and that a sun-centered solar system was consistent with biblical writings. Kepler's book Astronomia Nova, New Astronomy, 1609, described the orbits of Mars and the other planets as elliptical, not circular, first law, and asserted that the planets change speed in a way that allows them to sweep out equal areas in equal time as they orbit, second law. Later, in Harmonices Mundi, Harmony of the Worlds, 1619, he showed that a planet's orbital period squared is proportional to its average distance from the Sun cubed, P2A3, third law. Kepler's patience and persistence finally revealed the harmony he sought among the worlds. Kepler's laws gained widespread appreciation when astronomers confirmed their accurate timing, predictions during eclipses and planetary transits. This was when Isaac Newton discovered the natural consequences of a universal law of gravitation in 1687. Johannes Kepler struggled to find divine perfection in the orbits of the known planets by trying to match them with the shapes of the so-called perfect solids, i.e., cube, tetrahedron, pyramid, octahedron, icosahedron, and dodecahedron, in this illustration from his book Mysterium Cosmographicum, 1596. Venus transits the Sun. Astronomers describe a transit as an event in which one celestial body passes before another from the observer's vantage point. A solar eclipse, for example, is the Moon's transit across the Sun's disk. Galileo and other astronomers used transits of the Galilean satellites across Jupiter's disk to refine orbital predictions and derive an observer's longitude on Earth. When Venus occasionally transits the Sun, Johannes Kepler realized that observers on Earth could use parallax and trigonometry to determine the distance between Earth and the Sun, known as an astronomical unit, or AU. Aristarchus, Ptolemy, and Arabic astronomers estimated the AU of the Sun to be about 20 times farther than the Moon, or about 5 million miles, 8 million kilometers away. However, because Venus's orbit tilts by a few degrees relative to Earth's, Venus's transits are rare, occurring less than once a century. In 1032, the Persian astronomer Abu Ali ibn Sina observed a Venus transit. Kepler predicted a transit for 1631 and a near miss for 1639. The 1631 event was absent from Europe. Still, English astronomer Jeremiah Horrocks used revised calculations to predict and successfully record the Venus transit of December 4, 1639, using the data to estimate the AU as about 60 million miles, 96 million kilometers. Although his calculation is 35% less than the actual value, 93 million miles, 150 million kilometers, Horrocks instantly made the solar system about 250 times bigger than anyone had previously measured. Captain James Cook went to Tahiti as part of a worldwide campaign to observe the 1769 Venus transit, which resulted in a much more accurate estimate of the AU. Modern astronomers and millions in the general public observed two recent Venus transits of the Sun on June 8, 2004 and June 5, 2012. The next one isn't until 2117. NASA's Mars exploration rovers have observed transits of Phobos and Deimos from the surface of Mars, and extrasolar planet hunters have detected transits in other solar systems using ground-based telescopes and satellites, such as NASA's Kepler mission. Mizar-Alcor sextuple system. Early star catalogues of Hipparchus, Ptolemy, and Al-Sophi noted many bright stars that appear very close to each other in the sky. Among the most famous are the bright blue stars, second from the end of the Big Dipper's handle, which Arabic astronomers named Mizar and Alcor, and often called the Horse and Rider. The two stars are about 1/5 of a degree apart and test a person's naked eye visual acuity. Can you separate the Horse and Rider? Early astronomers were still deciding whether such pairs of stars were related to each other or just coincidentally close. The telescope's introduction made resolving what eventually became recognized as truly multiple star systems possible. Galileo appears to have discovered that Mizar is a double star, with a fainter companion, Mizar B, only 14 seconds away. 1 second of arc is 1 to 3/600th of a degree, requiring a telescope to find. But Galileo did not publish his discovery, perhaps because Mizar A and B did not show the parallax shifts that he expected would prove Copernicus's heliocentric theory. He and others thought that the stars were much closer to Earth than they truly are. Consequently, Italian astronomer Giovanni Riccioli, who published his data on Mizar A and B in 1650, often receives credit for the discovery of Mizar as the first known double star. However, the Mizar system turns out to be even more interesting than that. Astronomers discovered that Mizar A, a double star with a companion, is a spectroscopic binary in 1889, only detectable by analyzing the merged spectrum of the pair. In 1908, researchers also discovered Mizar B to be a spectroscopic binary. Mizar is a double-double system consisting of 4 stars. In 2009, researchers discovered Mizar's naked-eye companion Alcor to be a double, and recent evidence suggests that Mizar and Alcor might be gravitationally bound, transforming the Mizar-Alcor system into a sextuplet of 6 related co-orbiting stars. While we, as residents of a single-star system, find this astounding, estimates suggest that perhaps 60% of all stars in the galaxy belong to multiple star systems. Titan. Galileo's starry messenger of 1610, announcing the discovery of the 4 moons of Jupiter, the phases of Venus, and the presence of mountains and valleys on the moon, generated an enormous amount of excitement and instigated a space race of sorts among 17th century astronomers. If Galileo's relatively simple spyglass could make such discoveries, what new wonders awaited the even larger telescopes? Soon, bigger telescopes began reaching further into the sky. Saturn orbits the Sun nearly twice as far away as Jupiter, so sunlight is more than 3 times less intense than at Jupiter. It's no surprise that it took until 1655 for telescopes to become sensitive enough to detect the faint amount of sunlight reflected off a moon in orbit around Saturn. Christian Huygens, a Dutch astronomer, made that discovery using a telescope he designed. Huygens called the new moon Saturni Luna, Latin for Saturn's moon. It wasn't until 1847 that it was named Titan, as part of a Greek mythology theme for naming the 7 then-known satellites of Saturn. Modern observations of Titan by the Voyager and Cassini space missions have revealed a strange and unique world. Titan is the 2nd largest moon in the solar system, and at 3,200 miles, 5,152 kilometers across, it is larger than the planet Mercury. Titan's 1.9 grams per cubic centimeter implies an icy, rocky interior. It is the only moon with a thick atmosphere, a dense mixture of nitrogen and methane smog which shrouds the surface from view. We expect hydrocarbons created by sunlight in Titan's nitrogen-methane atmosphere to exist as liquids due to its temperature of 90 kelvins and a surface pressure about 50% higher than Earth's. Indeed, the Cassini orbiter's radar mapper found rivers and lakes of liquid ethane or propane on Titan. Titan's environment lacks oxygen, resulting in sluggish organic chemistry. It is an astrobiology hotspot, the best place in the solar system to study what the early Earth may have been like before life made our atmosphere oxygen-rich. Titan received the first probe to land on its moon in 2005. The successful mission was fittingly named Huygens. Saturn has rings. The planet Saturn was among the wonders that Galileo was the first to discover by telescope in 1610. Through his modest astronomical telescope, the planet appeared to be a round disk with 2 bright blobs on both sides that he called ears. The nature of these features, which came and went over the years, remained an unresolved puzzle for Galileo for the rest of his life. In 1659, the Dutch astronomer Christian Huygens trained his more powerful telescope on Saturn and became the first person to recognize the ears as a disk or thin, flat ring surrounding Saturn. In 1675, the Italian-French mathematician and astronomer Giovanni Domenico Cassini discovered a dark gap in the rings, now called the Cassini division. They suggested that the rings are a series of narrower, separate ones. Until the Scottish physicist James Clerk Maxwell hypothesized that gravitational and centripetal forces would tear apart solid rings, astronomers and mathematicians considered the rings to be solid disks. Maxwell's hypothesis was confirmed by the Voyager 1 and 2 flybys of and through Saturn's rings in the 1980s, which, along with the Cassini-Saturn orbiter, have revealed the rings to be an intricate structure of thousands of separate ringlets composed of countless dust-to-house-sized particles of nearly pure water ice, with impurities of silicate dust and possibly some simple organic molecules. The main rings are 174,000 miles, 280,000 kilometers wide, but are astonishingly less than 328 feet, 100 meters thick. Gravitational interactions with small moons orbiting within the rings have greatly depleted ring particles, creating the gaps in the rings. Planetary scientists debate the origin and age of Saturn's rings. Are they primordial or young? Perhaps formed only a few 100 million years ago from the catastrophic disruption of an icy moon? Great Red Spot. When the 17th century scientists Robert Hooke and Giovanni Domenico Cassini trained their early astronomical telescopes on Jupiter, they were the first to notice and track a circular reddish scar in the planet's southern hemisphere. Little did they imagine that they were tracking an enormous hurricane-like storm system, more than twice the size of the Earth, that would continue churning for nearly 350 more years, perhaps longer. Astronomers and planetary scientists have studied Jupiter's Great Red Spot in much more detail with modern telescopes and space missions. To atmospheric scientists, the Great Red Spot is now known to be a persistent, counterclockwise rotating atmospheric vortex. Time-lapse photography of the storm's rotation shows that it takes about 6 Earth days, about 14 Jupiter days, for the storm to spin once. Wind speeds along the edge of the storm zone, where it interacts with other belts and zones in Jupiter's atmosphere, peak around 270 miles per hour, 430 kilometers per hour. The Great Red Spot is cooler than the surrounding parts of Jupiter's atmosphere because its storm clouds are about 6 miles, 10 kilometers higher than the surrounding clouds. If we could somehow fly through that part of Jupiter's atmosphere, we would see something like a giant, slowly rotating thunderhead cloud rising above the haze. Strong jet stream winds to the north and south of the Great Red Spot provide the energy to keep the storm confined to the same latitude. While the spot's size has decreased somewhat in the past few decades, people have yet to determine how long it will continue to rage. Why the Great Red Spot is red is a mystery. Various hypotheses suggest that the color is caused by atmospheric gases or aerosols containing sulfur, phosphorus, or organic molecules. Astronomers have observed the spot's color change over the past few decades, from reddish to brownish, yellowish, and even whitish. The effort to understand the origin of the color of the Great Red Spot and the colors of Jupiter's other lovely atmospheric patterns is an active area of planetary science research. The mystery of the spot's origin and future only enhances the Van Gogh, the beauty of its colorful swirling clouds. Globular clusters. Stars form from the gravitational collapse of immense clouds of gas and dust. Astronomers have found that these clouds are often so large that many stars can form from a single cloud or closely associated collections of clouds, leading to the creation of multiple star systems and particular concentrations of enhanced star formation, such as spiral galaxy arcs. Some interstellar clouds, especially in the early universe, appear to have been so massive that they led to the formation of literally hundreds of thousands of stars in relative proximity. A globular cluster is a collection of stars that results when gravitational interactions between these nearby stars pull them together into a spherical mass, orbiting a common center of gravity, and possibly a black hole. Johann Ehle, a German post office official and avid amateur astronomer, made the first telescopic observations of a globular cluster in 1665. Ehle observed a dense cluster of stars now known in astronomer Charles Messier's catalogue as M22, or the Sagittarius cluster. M22 appears to be a faint, fifth magnitude smudge to the naked eye. Ehle and other 17th century astronomers could use their astronomical telescopes to reveal that the streak is the collected light of a swarm of countless closely packed stars. Since then, scientists have discovered more than 150 bright, densely packed globular clusters, like M22, orbiting the center of our Milky Way galaxy, part of a semispherical halo of stars and star clusters that are older than the typical stars found in the galactic disk. Researchers have discovered globular cluster halos in other galaxies, suggesting that halo formation plays a crucial early role in the formation of galaxies overall. Globular cluster halos extend so far out from the centers of many galaxies that astronomers speculate that some galaxies trade star clusters when they pass by, or interact with each other gravitationally. Stars in globular clusters interact with their close neighbors much more frequently than stars in normal space. As a result, astronomers do not believe that globular clusters would be good places to find stable, habitable planets. However, much remains unknown about these ancient stellar swarms. Iapetus and Rhea. The discovery of Jovian moons in 1610 and a moon around Saturn in 1655 set off a frenzy of moon hunting by late 17th century astronomers. Giovanni Domenico Cassini, the prolific Italian-French mathematician and astronomer, discovered the solar system's sixth and seventh new moons in 1671 and 1672, eventually naming them after the Greek titan Iapetus and his mother, Rhea. Strangely, Cassini could only see Iapetus when it was on the western side of Saturn. It seemed to disappear as it rotated around to the eastern side. In 1705, Cassini finally observed the moon on the other side of Saturn, when it was more than 6 times dimmer. Cassini and others had surmised that, like our own moon, Iapetus is tidally locked, with the same face pointed to its parent planet. Thus, half of the Iapetus faces forward in its direction of motion, the dark leading side, and half always faces backward, the bright trailing side. Rhea was also difficult to spot. It orbits 50% closer to Saturn than Titan. Its discovery closer into the glare of Saturn's disk is a testament to Cassini's prowess as an observer and the overall improvement in telescope and optics technology in the late 17th century. A ridge of unknown origin, 12.4 miles, 20 kilometers high, circles much of Iapetus's equator. Closer encounters with the Voyager missions in the 1980s confirmed the strange two-tone surface of Iapetus, which measured an ice-like density of around 1.1 grams per cubic centimeter. More detailed studies by the Cassini orbiter mission have revealed that Iapetus has an ancient, heavily cratered surface and an equatorial ridge that gives the moon a walnut-like shape. Voyager also revealed Rhea up close, showing it to be bright, with a reflectivity higher than 50%, heavily cratered, and with an ice-like composition. Why does Iapetus have such a strange two-toned surface? The neighboring moon, Phoebe, the source of a faint outer ring of Saturn, may be the culprit. The leading side of Iapetus may have darkened early on while ploughing into Phoebe's ring dust. Speed of light. Christian Huygens, 1629-1695, and Ole Christensen Remmer, 1644-1710. Throughout history, people have debated the nature of light. The Greek philosophers Aristotle, Euclid, and Ptolemy believed that light emitted from the eyes must travel at an infinite speed because we instantly see distant objects like stars when we open our eyes. 11th century scientists like the Muslim physicist Al-Haytham and the Persian scholar Al-Biruni proposed that light had a finite speed, however, based on some early experiments in optics. The debate continued into the 17th century, with luminaries like Kepler favoring an infinite speed and Galileo favoring a finite speed. A definitive measurement was necessary. The Danish astronomer Ole Christensen Remmer, who built on Galileo's original idea of using the moons of Jupiter as astronomical clocks, not for measuring longitude but for measuring light time, made the first accurate estimate of the speed of light. Roemer observed hundreds of eclipses of Jupiter's moon Io, carefully timing its disappearance or reappearance from Jupiter's shadow. He noticed that the predicted eclipse times systematically differed from the observed times. They occurred about 11 minutes earlier when Earth was closest to Jupiter and 11 minutes later when Earth was farthest away. Reamer attributed the discrepancy to the limited velocity of light. With the assistance of his Dutch colleague Christian Huygens, Reamer estimated the speed of light from his eclipse data to be approximately 137,000 miles, 220,000 kilometers per second. Although the more definitive 18th century stellar aberration measurements by the English astronomer James Bradley and the 19th century Michelson-Morley experiment later determined the actual value to be about 35% greater, Reamer's insight and years of careful observation enabled the first good estimate of the speed of light. Halley's Comet, Edmund Halley, 1656–1742. Comets are occasional, often dramatic interlopers among the otherwise clockwork regularity of the solar system. Early Chinese astronomers identified them as broom stars with long tails. Isaac Newton suspected that at least some of them orbit the Sun, though he didn't pursue proving the idea. But Newton's friend and colleague Edmund Halley, an English astronomer, geophysicist, and mathematician, soon picked up the idea. Halley observed a bright comet that appeared in 1682. Later, using historical records and Newton's laws to calculate its orbit, he proposed that it was the same comet seen in 1531 and 1607. These 76-year intervals allowed him to predict that the comet would return in 1758. It did, and while Halley did not live to see it return, astronomers named it Halley's Comet, now just Halley, in his honor. The comet underwent more advanced telescopic and photographic studies during its 1835 and 1910 passes. The 1986 Soviet Vega and European Giotto probes flew close by Halley's central nucleus, revealing it to be surprisingly small, approximately 9x5x5 miles, 15x8x8 kilometers, peanut-shaped, rugged, porous, with a density of approximately 0.6 grams per cubic centimeter, and dark as coal. Bright jets of ice composed of water, carbon monoxide and carbon dioxide emanate from the surface and interior, releasing dust and organic molecules and creating a long tail. We discovered Halley as the first periodic comet. Nearly 500 other short-period, less than 200 years comets are now known. Most come from the Kuiper belt, beyond Neptune, but some, including Halley, may have started as long-period comets from the distant Oort cloud. Astronomers have found that over 20 bright comets recorded between 240 BCE and 1682 CE were all previous apparitions of Halley's Comet. Its next pass will take place in the summer of 2061. Tethys and Dione. Having discovered Saturn's moons Iapetus and Rhea in 1671 and 1672, the astronomer Giovanni Domenico Cassini continued hunting for fainter moons, using ever more sophisticated telescopes at the Paris Observatory. In 1684, he discovered the fourth and fifth known moons of Saturn, eventually named Tethys, after the Greek sea goddess, and Dione, after the mother of Aphrodite, using a tubulus, or aerial telescope, 100 feet, 30 meters long. Little was known about these two new moons beyond their basic orbital properties until spectroscopic measurements in the 1970s revealed the presence of water ice on their surfaces. Later, spacecraft mission encounters revealed that they were unique worlds. Images of the moons from the Voyager and Cassini space missions showed Tethys to be about 670 miles, 1,080 kilometers, in diameter, about 30% the size of Earth's moon, and have a highly reflective and heavily cratered surface. The moon exhibits a high reflectivity and a density of 0.97 grams per cubic centimeter. Tethys's primary composition is consistent with water ice. Tethys exhibits some dramatic icy landscapes, including a huge impact basin named Odysseus, 250 miles, 400 kilometers wide, and an enormous valley named Ithaca Chasma, 62 miles, 100 kilometers wide, and 1.83 miles, 3.5 kilometers deep, which extends about 75% of the way around the moon. Images of Dione showed that it is also an ice-covered world, similar in size to Tethys, with icy cliffs hundreds of meters high. Dione's ancient, heavily cratered surface has fewer craters in some areas than others. This suggests that some parts of the moon may have been resurfaced early, possibly by liquid water volcanoes, erupting from a warmer interior and depositing younger ice lava flows on top of older surface areas. Dione has a higher density than most of Saturn's other moons, about 1.5 grams per cubic centimeter, implying a rockier interior. Radioactive heating from that rocky material could have provided the heat to drive early water ice volcanism. Zodiacal light. Seasoned and amateur sky watchers alike know that the best way to view the full splendor of the night sky is to go out on a clear, moonless night to a dark, isolated observing site, far from city lights. Even then, however, the sky is not completely dark. In addition to the thousands of visible stars and the Milky Way galaxy's diffuse glow, one can often observe another faint glow, particularly in the west after sunset or the east before sunrise. We call this glow the zodiacal light because it appears as a whitish band or faint spire from the horizon away from the sun, roughly along a line that follows the path of the zodiac constellations. The ecliptic, the plane of the sun's equator, and the orbits of most planets in the solar system also refer to this line. Islamic astronomers referred to the zodiacal light as the false dawn. Understanding its behavior and influence on determining a true sunrise or sunset was an important part of deciding the timing of daily prayers. Many Renaissance astronomers, including Giovanni Domenico Cassini, who observed the luminous streak in 1683, believed it was just an extension of the sun's atmosphere. Why it was bright only along the sun's equatorial plane remained a puzzle. The Swiss mathematician Nicolas Fatio de Duillier, who worked under Cassini at the Paris Observatory, was the first to propose the correct explanation. Particles reflecting the sun's light caused the glow. Modern spectroscopy and space probes proved the correctness of Fatio's hypothesis, revealing that the zodiacal light originates from sunlight reflecting off interplanetary dust grains, which range in size from a few hundredths to a few hundred microns. The width of a human hair is about 100 microns. Because these grains slowly spiral into the sun due to sunlight absorption, an effect called Poynting-Robertson drag, discovered by early 20th century physicists, there must be a continuous source to resupply them. Astronomers believe that dust from comets and occasional collisions between asteroids, most of which travel in or near the ecliptic, provide that continuous source of cosmic dust. Origin of tides. Throughout human history, coastal communities and maritime civilizations have tuned in to the tides, the twice-daily rise and fall of the sea. Babylonian and Greek astronomers recognized the relationship between the tide's height and the moon's position in its orbit. They believed that almost the same spiritual forces that governed the motions of the planets connected them. Early Arabic astronomers believed sea temperature fluctuations influenced the tides. Seeking support for heliocentrism, Galileo proposed that tides come from the sloshing of the oceans during the Earth's motion around the Sun. The English mathematician, physicist, and astronomer Isaac Newton was the first to propose the correct origin of the tides, linking the Earth, Moon, and Sun. Among other things, Newton had been working on a generalized theory to explain Kepler's laws of planetary motion, and by 1686, he had developed the basic outline for new theories of universal gravity and laws of motion. Newton hypothesized that both the Moon and the Sun exert a strong gravitational attraction on the Earth, and vice versa. Since verified and enhanced by space-age observations, his breakthrough discovery was that gravitational forces alone, not the Earth's spin or orbital motion, acting on the Earth's thin fluid ocean shell, are almost entirely responsible for the tides. The Moon's gravitational attraction raises a deep-water ocean tide of about 20 inches, 50 centimeters. The Sun's tidal effect is about half that. In shallow water, tidal heights can be up to 10 times larger, and the tides at any particular coastal location are a strong function of the positions of the Sun and Moon, as well as the local seafloor depth and coastline shape. The Earth's and Moon's solid parts also bulge in response to gravitational tidal attraction, with an amplitude typically about half that of the oceanic tides. Solid and liquid deformation dissipates energy in the Earth-Moon system through tidal friction. As a result, the Earth's spin is slowing down by a few milliseconds per century, and the Moon is slowly receding from the Earth by about 13 feet, 4 meters per century. Sir Isaac Newton asserts that there is a gravitational connection between the Moon, Earth, and Sun. Each exerts strong gravitational attractive forces on the other in proportion to their masses and inversely proportional to the square of their distances. The fluid nature of Earth's oceans allows these forces to express themselves as tides. Newton's laws of gravity and motion. The scientific revolution begun by Aristarchus, who proposed removing the Earth from its cosmological position of centrality, was carried on for 2,000 years by scientific rebels such as Aryabhata, Al-Brun, Nilakantha, Copernicus, Tycho, Kepler, and Galileo. This revolution decisively culminated in the work of Englishman Isaac Newton. Many consider Newton, a mathematician, physicist, astronomer, philosopher, and theologian, as one of the most influential scientists in human history. Newton was both an experimentalist and a theorist, and he excelled in both realms. He developed new concepts and tools in optics, including the first astronomical telescope to use mirrors instead of lenses, a design that bears his name. In the theoretical realm, using basic principles of then-modern physics and essentially inventing the new mathematical field of calculus as he went along, Newton discovered that Kepler's laws of planetary motion were the natural consequence of a force that exists between any two masses and that decreases as the square of the distance between them, known as 1r2 behavior. He called this force gravitas, Latin for weight. We now call it gravitation, and the 1r2 behavior is known as Newton's law of universal gravity. Newton built upon that foundation to derive his three famous laws of motion. Proper motion of stars. Of course, the British astronomer Edmund Halley is most famous for discovering the periodic return of Halley's Comet. However, he also studied other aspects of astronomy, including comparing stars' positions relative to those recorded by earlier astronomers, to identify the ones closest to the Sun and determine their absolute distances. Most of the history of astronomy assumed the stars to be fixed denizens of a crystalline or solid celestial sphere that either rotated around the Earth, to some, or appeared to rotate as the Earth spun underneath, to others. The occasional appearance of supernovae or comets, guest stars, cast doubt on the concept of a fixed celestial sphere but did not disprove it. Halley provided that proof by carefully comparing the positions of bright stars in 1718 to those recorded by Hipparchus in the 2nd century BCE. Three bright stars, Sirius, Arcturus, and Aldebaran, had moved significantly over 1,150 years relative to background stars. Halley calculated what he dubbed the proper motion of these stars, that is, the motion belonging to the star proper, rather than the perceived motion that would be due to parallax. Stars with the largest proper motion are relatively closer to the Sun. The three stars above are only about 9, 37, and 65 light-years away. Stars closer to the Sun, such as Proxima Centauri, 4.3 LLOI, and Barnard's star, 6 LOI, discovered in 1916 by the American astronomer E. Barnard, have even larger proper motions. Barnard's object has the largest known, moving more than 10 arc-seconds, 0.003 degree, per year. Halley and other pioneers of stellar astrometry, positional measurements, have helped us understand that the sphere of stars we see overhead at night is just the projection of an incomprehensibly enormous three-dimensional space volume. Everything is in motion relative to everything else, and as Edwin Hubble would discover in the 20th century, the entire volume is increasing over time. If we watch patiently enough, the universe is dynamic. Celestial navigation. Prior to the invention of the first astronomical telescopes, ancient through medieval astronomers had to use naked-eye instruments such as armillary spheres, celestial globes, and astrolabes to establish the altitude and azimuth of celestial bodies, what astronomers call their declination and right ascension respectively, as well as the relative distances between objects in the sky. Building circular instruments like the astrolabe in large and cumbersome sizes was necessary to achieve higher precision measurements. As a result, astronomers and instrument makers began using only semicircular segments to reduce instrument size while maintaining precision. Measuring instruments made from a quarter of a circle, quadrants, began appearing in the mid-16th century. Tycho Brahe invented a large pedestal-mounted or framed version spanning 1/6 of a circle, which he called a sextant. These devices continued to provide unsurpassed positional measurement accuracy even after the telescope's invention and proliferation. 1/8 circle versions, octants, appeared in the 18th century. Framed quadrants, sextants, and octants were fine instruments on land, but they needed to be more practical at sea, where more precision was required. Miniaturization, flexibility, and simplicity of operation on a moving platform were required. Isaac Newton proposed modifying the quadrant using two mirrors, like his reflecting telescope design. In 1757, the English instrument maker John Bird built a portable version of the sextant, which incorporated Newton's double mirror design. Many modern sextants essentially mimic this 18th century design, with the addition of higher-powered optics and the incorporation of composite materials. Even in our computerized and global positioning system era, it is heartening that many mariners today are still required to know how to perform the basics of celestial navigation using a sextant. Planetary nebulae. The advent of telescopes in the 17th century, as well as significant improvements in their size and ability to detect faint objects in the 18th century, enabled exciting discoveries by astronomers during the Enlightenment. Not just fainter stars, but entire new classes of objects became visible. Among the stars, the largest class consisted of fuzzy, extended patches of light that resembled faint, fixed clouds. Astronomers called them nebulae, singular nebula, Latin for clouds. Ancient and medieval astronomers recorded several bright nebulae, such as the Orion Nebula and a nebula in Andromeda. 20th century astronomers later recognized them as separate galaxies. Edmund Halley published a short list of nebulae in 1715. However, the crown prince of 18th century nebula observations was the French astronomer Charles Messier, who developed a definitive early catalogue of more than 100 nebulae. Messier discovered an object in 1764 and catalogued it as Object M27, which typified one type of nebula. With a somewhat circular, fuzzy appearance, M27 and similar objects looked much like the giant planets in telescopes of the day, causing the English astronomer William Herschel to dub them planetary nebulae. The name choice stuck out, but it was unfortunate, as modern spectroscopy observations show these objects have nothing to do with planets. Instead, modern spectroscopy observations have revealed planetary nebulae as enormous, expanding shells of hot, glowing gases ejected from red giant stars near the end of their stellar lifetimes. Typical planetary nebulae can be more than a light year across, and they glow from the emission of ionized carbon, oxygen, nitrogen, and other elements heavier than hydrogen and helium created during the collapse of their precursor stars. As such, planetary nebulae are part of a cosmic recycling program that turns hydrogen and helium into heavier elements and eventually life. Messier Catalogue. Witnessing exciting celestial events as a child, such as the Great Comet of 1744 and the solar eclipse of 1748, stimulated Frenchman Charles Messier's lifelong interest in astronomy. His passion for observing led him to work in Paris as a depot clerk for the official astronomer of the French Navy, a job that entailed using an observatory on the roof of the Hôtel de Cluny. Messier had ample time to observe, as well as a good dark sky observing location in pre-industrial revolution Paris. His early passion was comet hunting. He was among the first astronomers to verify the predicted return of Halley's Comet in 1758-1759. During the search, he discovered another comet and a comet-like streak of light in the constellation Taurus. Unlike a comet, however, this smudge didn't move relative to the stars. He made a note of it. As he continued hunting comets over the next decade, he encountered one fuzzy, cloud-like nebula after another, giving each a designation of the letter M followed by a number. Some, like M22, which had been discovered in 1665, could barely resolve as a circular cluster of huge numbers of closely packed stars, later called globular clusters. Others, like M31, had an elongated shape and had been previously recognized as a great nebula in Andromeda. Many were objects that Messier himself was the first person to discover and describe. He had collected so many that by 1771, he had amassed a collection of 45 objects, which he published as his Catalogue des nébuleuses et des amas d'étoiles, Catalogue of Nebulae and Clusters of Stars, in the Journal of the French Academy of Sciences. By 1781, he and his colleague Pierre Méchain, a future director of the Paris Observatory, had amassed even more. Their final catalogue contained 103 objects. 20th century astronomers discovered 7 more objects that Messier and Méchain observed after 1781, bringing the total number of Messier objects, now recognized as star clusters, planetary nebulae, molecular clouds, and galaxies, to its modern value of 110. Some amateur astronomers and astronomy clubs try to observe all 110 objects during springtime Messier marathons. Who knows? Such events might help inspire another child's passion for astronomy. Lagrange points. With his 1687 publication of the Principia, Isaac Newton expanded Kepler's laws of planetary motion into laws of gravitation and motion in general, thus establishing a reliable framework within which astronomers, physicists, and mathematicians could begin to understand the detailed intricacies of not only how planets, moons, and comets moved in the sky, but why they did so. Among the most challenging applications of Newton's laws was the so-called three-body problem. We could easily apply Newton's equations to understand the gravitational effects that govern the motions of two masses, such as the Earth and the Moon or the Sun and the Earth. Still, the calculations got pretty thorny when theorists introduced the gravitational effects of a third body. The French mathematician Joseph-Louis Lagrange was the first to successfully solve a specific case of the three-body problem. He predicted in 1772 that any three-body system with 2 large masses and 1 small mass should have 5 special places where the gravitational forces among the bodies would balance. These places are now called Lagrange points. The 20th century discovery of the Trojan asteroids, which are trapped in the Sun-Jupiter systems L4 and L5 Lagrange points, confirmed Lagrange's prediction. The French mathematician Pierre-Simon Laplace coined the phrase celestial mechanics in 1799 to describe the physics and math of studying complex solar system motions. Lagrange's solution to the three-body problem was relatively easy because it assumed one small object interacted with two large, massive objects, one in an essentially circular orbit around the other. Celestial mechanicians built upon Lagrange's discovery to address more comprehensive three-body problems. In fact, researchers in the 21st century frequently employ high-speed computers to resolve even more intricate n-body problems. These problems involve tracking the Newtonian motions of numerous individual bodies, such as planets, moons and asteroids, ring particles, or even grains of cosmic dust, to comprehend, elucidate, and forecast intricate motions within our solar system. Discovery of Uranus. No one had ever discovered a planet before 1781, the beginning of human history. The 5 planets besides Earth that are visible to the naked eye have been known since prehistoric times, and with the invention of the astronomical telescope, Galileo, Huygens, and Cassini discovered new moons, but no new planets. The honor of being the first person to discover an entirely new planet went to the English musician and astronomer William Herschel. Herschel's musical skills led to an interest in astronomy and optics, and he began making his telescopes after befriending the English astronomer Royal Neville Maskelyne. In March of 1781, Herschel observed a 6th magnitude extended, not star-like, object. His first reaction was that he had discovered a comet. He tracked and reported its position, and by 1783, other astronomers were able to verify that it was indeed a new planet orbiting at 19 astronomical units, well beyond Saturn. Herschel wasn't the first to spot the planet, but as the first to recognize it for what it was, he got to name it. He chose Georgium Sidus, George's star, after King George III. But, like previous celestial names inspired by patronages, it didn't stick. Astronomers later named it Uranus, pronounced Ur-Unus, after the Greek god of the skies. Modern telescopic observations and the 1986 Voyager 2 space probe flyby have revealed Uranus to be an ice giant planet, density 1.3 grams per cubic centimeter, 4 times the size and 15 times the mass of Earth. Compared to Jupiter and Saturn, Uranus's atmosphere is much less active, yet it remains rich in hydrogen and helium. Methane gives it a bluish-green color, and it envelops an Earth-sized, icy, rocky core. Uranus tilts on its side, giving the impression of rolling instead of spinning on its axis. The planet has 27 known moons, including 5 large icy worlds, 2 discovered by Herschel. In 1977, starlight, winking on and off as it passed by Uranus, revealed its thin, dark rings in 1977. In 2007, we passed through the plane of those rings. Astronomers are now busy studying springtime on the 7th planet, Titania and Oberon. After discovering Uranus in 1781, English astronomer William Herschel continued to observe the planet with successively larger telescopes. His instrument's larger mirrors and focal lengths enabled the increased light-gathering potential to detect fainter objects, as well as the increased resolution to distinguish these objects from others nearby. Better technology, careful observations, and assistance from his sister and fellow astronomer Caroline Herschel led to the discovery of new moons around Uranus and Saturn. Herschel discovered 2 moons orbiting Uranus on the same night in early 1787. Herschel and other astronomers quickly deduced the dramatic tilt of the Uranian spin axis, known as the obliquity, by monitoring their motions and assuming that the moons orbited in or close to the planet's equatorial plane. Uranus tilts on its side, with an obliquity of about 98 degrees. A planet's tilt is the reason for the seasons. Earth's tilt of 23.5 degrees causes our familiar winters, springs, summers, and falls, as well as the 6-month-long polar days and nights in the Arctic and Antarctic. On Uranus and its moons, the entire northern and southern hemispheres experience polar days and polar nights that are 42 Earth years long. Extreme tilts lead to extreme seasons. Herschel's son, John Herschel, also an accomplished astronomer, ultimately named these and the other Uranian moons, choosing characters from the works of William Shakespeare and Alexander Pope. He named the brighter of the two moons his father discovered, Titania, after the Queen of the Fairies in Shakespeare's A Midsummer Night's Dream. The second was named Oberon, after the Fairy King. The Voyager 2 encounter with Uranus in 1986 revealed Titania and Oberon to be heavily cratered worlds, each about half the size of Earth's moon. Their similar densities imply rocky and icy interiors. Since then, spectroscopy has revealed surfaces with water and CO2 ices, as well as simple organic molecules like those produced by the irradiation of methane or other carbon-bearing ice. Enceladus. Not content with aiming his larger and larger telescopes only at the newly discovered Uranus, English astronomer William Herschel also set his sights on searching for new moons around Saturn. The discovery of Saturn's sixth moon in August 1789 rewarded him, and nearly 60 years later, Herschel's son, John, named the moon Enceladus, Enceladus, after a mythical Greek giant. Several centuries of telescope observations of Enceladus revealed little more about the moon than its orbital period, 1.4 days. Its extreme brightness, it reflects nearly 100% of the sunlight from its surface, and its apparent association with Saturn's E-ring. A spectroscopy of Enceladus showed evidence of very fine-grained water ice. The Voyager flybys of 1980 and 1982, as well as the Cassini-Saturn orbiter mission that began in 2004, have revealed the true nature of this strange and interesting little world. It is only about 310 miles, 500 kilometers, across, but still exhibits some of the most varied geologic terrains in the solar system. Some of Enceladus is heavily cratered and ancient, but other areas show almost no craters, and thus must be geologically very young. Some places have deep troughs, steep ridges, or sharp grooves, suggesting that significant tectonic forces were at work. However, the most exciting discovery has been the discovery of active plumes of water vapor coming from Enceladus's south polar region. Piloting the Cassini probe through these plumes revealed the presence of minor amounts of nitrogen, methane, carbon dioxide, propane, ethane, and acetylene. This indicates that Enceladus is venting ice and organic molecules into space like a giant comet rather than a planetary moon. What is driving all of this activity on and inside Enceladus? The density of 1.6 grams per cubic centimeter suggests that some rocky material is suitable for radioactive heating. Like Io, Europa, and Ganymede, it experiences tidal heating due to its orbital resonance with Dione. Cassini data prove that a salty subsurface liquid water layer, an ocean, may lurk under that icy crust. Astrobiologists are taking note. Mimas. Shortly after discovering Enceladus, William Herschel struck Saturnian gold again, spotting the seventh known moon of the ringed planet in September 1789. At the time, this newest one was the closest to Saturn itself, with an orbital period of less than a day. William's son, John Herschel, would later name this moon Mimas after a giant in Greek Titan mythology. Herschel's innovative telescope designs, capable of collecting unprecedented numbers of photons from distant sources, enabled him to detect faint moons close to bright planets. For instance, he used a 40-foot, 12-meter reflecting telescope with a primary mirror 4 feet, 1.2 meters, in diameter to discover Mimas and Enceladus, making it the largest telescope in the world at the time. Telescopic spectroscopy of Mimas showed that it has a water ice-dominated surface, like all the other Saturnian moons except for Titan. Little was known about Mimas until the Voyager and Cassini spacecraft encounters obtained close-up images and other data. The images revealed Mimas to be a small world, only about 250 miles, 400 kilometers, in diameter, less than 1/8 the size of our moon, with a density of just under 1.2 grams per cubic centimeter, indicating a primarily icy interior. Astronomers believe Mimas is close to the smallest possible astronomical body that can form a spherical shape from its self-gravity. Mimas is noticeably oblate, about 10% wider at the equator than at the poles, because of the strong gravitational pull of nearby Saturn. Herschel used his renowned 40-foot, 12-meter telescope to discover Mimas and Enceladus. Mimas exhibits significant cratering, albeit not consistently. Canyons and fractures suggest that tectonic forces or cryovolcanism, ice volcanoes, may have resurfaced in some areas in the distant past. The most distinctive feature of Mimas is a single enormous crater, almost a third of the Moon's diameter across, which gives Mimas its distinctive Death Star look. Meteorites originate from space. While we often assume that rocks occasionally fall from the sky, for a significant portion of human history, this notion was considered absurd, and the late 18th and early 19th centuries deduced that many ancient and indigenous cultures recognized special stones with unique magnetic properties or high concentrations of iron metal as extraterrestrial samples of the main belt and near-Earth asteroids. In 1794, the German physicist Ernst Chladni proposed that some of these special rocks, including a large metal-rich sample he studied called the Pallas Iron, discovered in 1772 near the Russian city of Krasnoyarsk, were debris from outer space. Many scientists dubbed the idea incredible, believing these rocks to be volcanic or produced by lightning strikes. By the early 19th century, detailed laboratory measurements of these rocks were possible. In 1803, the French physicist and mathematician Jean-Baptiste Biot proved Chladni's hypothesis by showing that the chemical compositions of rocks found by the thousands near the town of L'Aigle, shortly after a spectacular shower of shooting stars, were unlike any known Earth rocks. Such rocks became known as meteorites, and the scientific field of meteoritics was born. Scientists have collected more than 30,000 meteorites worldwide, many from desolate deserts or Antarctic snowfields, where it is relatively easy to notice an odd rocky interloper that fell from above. Simple silicate minerals and tiny spherical grains called chondrules, thought to be some of the first materials condensed from the solar nebula, as well as the building blocks of asteroids and eventually planets, make up the vast majority of rocks that fall to Earth, 86%. About 8% of the rocks that fall to Earth are silicates without chondrules, samples of igneous rocks from the formerly geologically active crusts of large asteroids, the Moon and Mars. Only about 5% consists of iron and iron-nickel, similar to the rocks originally studied by Chladni and Biot. These rocks are fragments of the cores of ancient, now shattered asteroids and planetesimals, which had grown large enough to differentiate into core, mantle, and crust before being destroyed by impacts during the violent early solar system history. In 2008, researchers discovered a small, 14-ounce, 408-gram ordinary chondrite meteorite on the hard, pebbly surface of the Rub al-Khali Desert near Ash-Sharqiya, Saudi Arabia. The black surface is a thin fusion crust formed during the rock's short, fiery passage through Earth's atmosphere. Encke's Comet. Despite significant progress in promoting gender equity in science over the past few decades, men have dominated the history of astronomical observations and discoveries from antiquity to modern times. Among the first female pioneers to break into this old boys' club was the English astronomer Caroline Herschel, the younger sister of William Herschel, the discoverer of Uranus. Caroline was an accomplished vocalist and often performed in concerts with her brother in their younger years. Her interest in astronomy has paralleled William's, and as he began devoting more of his time to telescope making and observations, she joined him as a constant assistant. She became proficient in astronomical calculations and developed a reputation that exceeded her brother's as a mirror polisher and telescope engineer. In 1782, at her brother's urging, she began making her observations. The younger Herschel focused mainly on searching for comets. She discovered 8 during her career. The German astronomer Johann Encke later identified the comet she discovered in 1795 as the second known periodic comet after Halley's in 1819. Comet Encke is still famous among astronomers because it has the shortest period of all known periodic comets, taking just 3.3 years to orbit the Sun. Because of its relatively frequent appearances, it is also one of the most well-studied comets. Caroline Herschel also published an important 1798 star catalogue and discovered Messier 110, a companion to the Andromeda Galaxy. Until then, the world had widely recognized her as the most accomplished female astronomer. She was among the first women elected to honorary membership in the Royal Astronomical Society. It would be another 80 years until they let women become full members. In a field long dominated by men, she made a lasting impression as a skilled observer and role model for women aspiring to scientific careers. Ceres, the discovery of Uranus and a dozen new solar system moons in the late 18th century spurred astronomers into even more detailed cataloguing and searching of the skies. Among the most meticulous and methodical of those sky mappers was the Italian priest, mathematician and astronomer Giuseppe Piazzi of the Palermo Astronomical Observatory. Between 1789 and 1803, Father Piazzi oversaw the creation of the Palermo Star Catalogue, a survey of nearly 8,000 stars. On January 1, 1801, as part of his catalogue work, Piazzi noticed a dim, 8th magnitude star near the head of the constellation Cetus that had yet to appear in previous catalogues. Over the next few nights, he noticed it moved against the fixed stars and thought he might have discovered a comet. But the lack of any comet-like coma or tail led him to suspect it might be something better. Indeed, follow-on observations by Piazzi and others led to the discovery late in 1801 that the star-like object was instead orbiting the Sun as though it were a planet between Mars and Jupiter, near 2.7 astronomical units. Piazzi named it Ceres Ferdinandea after the Roman goddess of plants and his patron, King Ferdinand III of Sicily. Astronomers weren't sure how to classify Ceres, too small and dim to be a planet but not a star, comet, or moon. In 1802, the astronomer William Herschel coined the term asteroid, meaning star-like, to describe Ceres and the newly discovered Pallas. Modern telescopic observations have shown that Ceres is the largest of the main belt asteroids, with a diameter of around 590 miles, 950 kilometers, and a density of around 2 grams per cubic centimeter, suggesting the possible presence of an ice-rich interior. Astronomers today classify Ceres as a dwarf planet, similar to Pluto, due to its size and ability to form a round shape through gravity. We learned an enormous amount about the surface and interior of Ceres when the NASA Dawn mission finally reached it in March 2015. Highlights include the discovery of ancient ice volcanoes and simple organic molecules on the asteroid's surface. Astronomers have determined the orbits of more than 750,000 asteroids as of mid-2018, and they expect this number to grow much larger as more detailed surveys discover fainter objects. The solar system is teeming with minor planets. Vesta. Following the discovery of Ceres in 1801, scientists swiftly discovered a second asteroid, Pallas, in 1802, and a third, Juno, in 1804. The German astronomer Heinrich Wilhelm Olbers was involved in 2 discoveries: recovering Ceres near its predicted position in late 1801, and discovering and naming Pallas in 1802. Olbers, a physician by day and an astronomer by night, proposed that minor planets such as Ceres and Pallas could be the fragmented remains of a now destroyed planet that must have existed between Mars and Jupiter. Olbers searched for even more potential planetary fragments, and in 1807 he discovered the 4th known asteroid. The mathematician Carl Friedrich Gauss calculated its orbit and named it Vesta, after the Roman virgin goddess of the hearth. Gauss found that, like Ceres, Pallas, and Juno, Vesta orbits in what is now known as the main asteroid belt, ranging from about 2.1 to 3.3 astronomical units, AU, and centered around 2.7 AU. Now that astronomers know that Ceres, Pallas, Juno, and Vesta make up about half of the mass of the entire main asteroid belt, it's not surprising that early 19th century astronomy textbooks commonly refer to them as new planets. Today we might call them dwarf planets. Vesta is the brightest asteroid in the main asteroid belt. Ground-based observations by the Hubble Space Telescope and NASA's Dawn mission reveal it to have a diameter of about 330 miles, 530 kilometers, a rocky density of 3.4 grams per cubic centimeter, and a squashed shape due to two gigantic impact basins that gouged out the asteroid's south pole. Spectroscopic data indicate that the asteroid appears to have been once molten and differentiated into a core, mantle, and volcanic crust, much like the terrestrial planets. Meteorites from the classes known as Howardites, Eucrates, and Diogenites are likely samples of Vesta, perhaps blasted off by the giant south polar impact events. The Dawn mission provided much-needed details about Vesta's geology, composition, and history during its year-long orbital mission around Vesta in 2011-2012, and has revealed the asteroid to be a rare surviving example of an ancient transitional object known as a protoplanet, part asteroid, part planet. Vesta plays a crucial role in comprehending the formation process of terrestrial planets such as the Earth. Birth of spectroscopy. Isaac Newton's experiments in 1672 demonstrated that sunlight is not white or yellow, but rather a spectrum of many colors that refract slightly differently when passing through an object like a prism. Others, including fellow English scientist William Hyde Wollaston, widely repeated and expanded on Newton's experiments, becoming the first to observe mysterious dark lines in some parts of the sun's spectrum in 1802. Scientists needed a tool, a method, for understanding these dark lines and exactly where they occurred in the solar spectrum. In 1814, the German optician Joseph von Fraunhofer developed a spectroscope tool. An experimental technique known as spectroscopy could use this specially designed prism could be used to measure the positions or wavelengths of the lines. With his spectroscope, he observed more than 500 dark lines in the solar spectrum. Astronomers still refer to these as Fraunhofer lines. In 1821, he constructed a higher resolution spectroscope using a diffraction grating instead of a prism. He founded stellar spectroscopy by discovering that bright stars, such as Sirius, also have spectral lines that differ from the sun's. By the mid-19th century, physicists and astronomers could reproduce these lines in the laboratory by filtering light through various gases. Thus, they discovered that different kinds of atomic elements absorb different, very narrow and specific wavelengths of light, causing the lines. Without needing to touch the object directly, spectroscopy quickly emerged as the primary method for measuring the atomic and molecular composition of distant light sources like the sun, planetary atmospheres, stars, or nebulae. All that was required was a telescope and some spectral line measuring device, or spectrometer. Indeed, spectroscopy from ground and space-based telescopes, as well as orbiting and landing space missions to other worlds, is an important part of modern astronomy and space exploration. Stellar parallax. Parallax is an object's apparent motion from the observer's changing perspective. Hold a finger in front of your face and blink back and forth between your left and right eyes. Your finger will appear to move because of the small change in viewing perspective. That's parallax. It is possible to do a similar experiment using a much larger change in viewing perspective, the diameter of the Earth's orbit, to search for parallax motions among the stars and thus determine their distances from us. From Aristarchus's time to Tycho's, astronomers used the inability to observe parallax for any star as proof that the Earth remained motionless at the center of the universe. Following the establishment of Copernicus's heliocentric view, astronomers cited the continued inability to measure stellar parallax as evidence of the star's extreme distance. But how far? In 1838, German mathematician and expert stellar cartographer Friedrich Wilhelm Bessel won the race to finally measure a star's parallax. He used observations 6 months apart, when Earth was on opposite sides of the Sun, to measure a parallax of 0.34 arc-seconds, 0.0087 degrees, for the star 61 Cygni. Knowing that the viewing perspective had changed by 2 astronomical units, 186 million miles, 300 million kilometers, Bessel estimated the distance to 61 Cygni to be about 58 trillion miles, 93 trillion kilometers, or nearly 10 years distance at the speed of light. Bessel's estimate was close to the modern accepted value of 11.4 light-years. The astronomers Georg Wilhelm Struve and Thomas Henderson also reported similar parallax discoveries in 1838, leading to estimates of distances to Vega, 25 light-years, and Alpha Centauri, 4.3 light-years. Alpha Centauri also has one of the largest observed proper motions in the sky, and it is now known to be the star system closest to the Sun, at nearly 272,000 times the Earth's average orbital distance. Even the closest stars, it turns out, are immensely far away. First, astrophotography. The most successful pre-19th century astronomers were also talented artists by necessity. The only way they could record their observations was to sketch, draw, or paint what they saw with their eyes. However, the situation quickly changed with the invention of photography in 1839. Over time, new and improved photography methods will forever revolutionize astronomy. Early photographic methods were cumbersome, crude, and dangerous. The daguerreotype process, developed by French inventors and artists Louis Daguerre and Joseph Niepce, could produce relatively sharp images on wet copper plates coated with silver. Still, the process required photographers to work closely with toxic mercury, iodine, or bromine vapors. Still, the results were impressive, and the French government made the process publicly available to the world for free very soon after its invention. The American doctor, chemist, and photographer John William Draper quickly developed some improvements to Daguerre's process. His scientific interests compelled him to point his equipment skyward, and he took a series of increasingly higher quality daguerreotype plates of the moon from 1839 through 1843. Draper's lunar plates marked the first recorded photos of a recognizable astronomical object. The 1870s invention of dry plate technology helped astrophotography become an important scientific research tool for recording images and spectra. John Draper's son, Henry Draper, continued his father's legacy in astrophotography by mounting his cameras to large telescopes, recording the first photographic spectrum of the star Vega in 1872, and acquiring the first photograph of the Orion Nebula in 1880. Film eventually replaced plates, but analog photo technology reached its sensitivity limit in the mid-20th century. The 1970s saw the development of electronic imaging technology, primarily the charge-coupled device, which now serves as the preferred photographic medium for scientific and consumer applications. Discovery of Neptune. In the decades following its discovery in 1781, astronomers carefully tracked the position and refined the orbit of the slow-moving planet, Uranus. Several noted slight differences between what Newton's law of gravity predicted and its actual path across the sky. The English astronomer John Couch Adams and the French mathematician Urbain Le Verrier, two particularly talented theorists, speculated that the gravitational pull of an unseen planet might cause these differences. Working independently during 1845 and 1846, Le Verrier and Adams each developed predictions about where this hypothesized perturber of Uranus might be in the sky. Adams convinced colleagues at Cambridge to search for the planet, but the observers only recognized it as a star with a lot of sky to cover. In contrast, Le Verrier's prediction was over a narrower region of the sky. It took only a few hours on the night of September 24-25, 1846, for his colleague, the German astronomer Johann Galle, to find it from Berlin Observatory and, over several more nights, confirm its identity as the eighth planet. The French mathematician and politician François Arago hailed the discovery as a triumph of Newtonian physics, proclaiming that Leverrier had discovered a planet with the point of his pen. A gracious Adams, among others, jointly credited Leverrier and Galle with discovering the new planet. Leverrier called it Neptune, after the Roman god of the sea. Its discovery doubled the solar system's size yet again. With an average orbital distance of 30 astronomical units and an orbital period of nearly 165 years, Neptune's small apparent diameter and very slow motion explain why several earlier astronomers, including Galileo, had observed Neptune but, like Adams's colleagues at Cambridge, had not recognized it as more than just another bluish star. Only one space mission, the Voyager 2 flyby in August 1989, has studied Neptune up close, giving scientists a fleeting glimpse of a beautiful and stormy blue world in the far outer reaches of our solar system. Triton. The discovery of Neptune in the autumn of 1846 provided a new target for moon hunters, a challenge because of Neptune's great distance from the Sun. William Lassell, a British merchant and amateur-turned-professional astronomer, discovered Neptune's moon just 17 days after the discovery of Neptune itself. Lassell had made his money as a beer brewer and used it to build his telescope mounts, grind his mirrors, and assemble a Newtonian reflector, 24 inches, 61 centimeters, in diameter, which was, at the time, the world's largest functioning telescope. When John Herschel heard about the discovery of Neptune, he suggested to Lassell that he use his telescope to search for moons around the new planet. It didn't take long, only 8 days of searching, for Lassell to find a moon, and it was a strange one indeed. Tracking its orbit revealed it was orbiting backward, retrograde, compared to all known solar system moons. Furthermore, its orbit exhibits a high tilt to the plane of Neptune's orbit, causing each of its poles to occasionally point almost directly at the Sun, akin to a highly tilted Uranus. Lassell didn't name his discovery. Astronomers later agreed on Triton, the Greek sea god and son of Poseidon, the Greek equivalent of Neptune. Little else was known about distant Triton before the Voyager 2 encounter in 1989, which revealed it to be large, 1,678 miles, 2,700 kilometers in diameter, bright, 70–80% reflective, and with an icy rocky density of 2.1 grams per cubic centimeter. Most surprisingly, researchers discovered a very thin nitrogen atmosphere, gently erupting geysers, and a geologically young surface, few craters, that continually resurfaces through icy cryovolcanism. More recently, nitrogen, water, and carbon dioxide, which are only 30 to 40 degrees above absolute zero at the surface, but possibly warmed by radioactive heat in the interior, have composed Triton's strange landforms. Many astronomers believe that Triton, like Pluto, formed in the Kuiper belt, and that Neptune somehow captured it in its tilted backward orbit. Miss Mitchell's Comet. Even though the English astronomer Caroline Herschel established a pioneering path for women interested in science and astronomy around the turn of the 18th century, only a few women could follow that path successfully for some time. Indeed, it would be over another half-century before the first female scientist made a professional academic career in astronomy. That woman was Maria Mitchell, a native of Nantucket and a skilled observational astronomer and educator. Mitchell helped teach at a school that her father founded on the island, and she eventually became a librarian. She soaked up the scientific and literary works of the time while continuing to enhance her experience observing the night sky. In 1847, using her father's small observatory, she discovered a faint comet only visible via telescope. The comet was informally dubbed Miss Mitchell's Comet. Mitchell's astronomical work garnered widespread recognition. She traveled to Europe to meet other astronomers and receive awards. Eventually, a nautical almanac publisher offered her a job calculating Venus's positions. She became the first female member of the American Academy of Arts and Sciences, as well as the first woman elected to the American Association for the Advancement of Science. As much as she must have loved astronomical research, she never lost the passion for teaching that she had developed on Nantucket. When the wealthy New York businessman Matthew Vassar offered her a teaching position in 1865 at the new women's university he founded, she took the offer. She became Vassar College's first faculty member and the world's first female professor of astronomy. The Vassar College Observatory appointed her as its director. She used the facility as a teaching tool for astronomy students while researching sunspots, the changing appearances of Jupiter, Saturn, and their moons. She taught on the Vassar faculty for 23 years and trained scores of women who went on to pursue scientific careers. After her death, the society formed the Maria Mitchell to uphold her legacy. In 1908, the society opened the Maria Mitchell Observatory on Nantucket, a facility still dedicated to astronomical teaching and research. Doppler shift of light. Most of us are familiar with the dramatic change in the sound of an ambulance, train whistle, or race car as it approaches us and then speeds past. As the vehicle recedes, its sound changes to a distinctly lower pitch or frequency than when it was approaching. This change is known as the Doppler effect, named after the Austrian physicist Christian Doppler, who first proposed in 1842 that the observed frequency of any wave should depend on the relative difference in speeds between the wave's source and the observer. In 1845, Dutch meteorologist C.H.D. Buys-Ballot cleverly verified Doppler's hypothesis for sound waves by hiring musicians to play notes on a moving train, and then having stationary observers report the pitches they heard as the musicians approached and receded. In 1848, the French physicist Armand Hippolyte Fizeau showed how Doppler's hypothesis applied to light waves by noting slight changes in frequency or shifts of absorption lines in the spectra of stars. According to astronomers, the size and direction of these frequency changes, known as Doppler shifts, can reveal the speed at which astronomical bodies are approaching or receding from one another. Objects approaching us have their spectra shifted to higher frequencies or shorter, bluer wavelengths. Conversely, objects receding from us have their spectra shifted to red. In the 1860s, we measured the first accurate relative stellar velocities, and in the 1870s, we detected the star's Doppler shift due to the Earth's annual motion around the Sun. In the early 20th century, the American astronomer Vesto Slipher observed that most of the known nebulae, such as those in Messier's list, were red-shifted, or moving away from us. Soon after, Edwin Hubble, another American, showed that many of these nebulae were other galaxies, enormously far from the Milky Way. Hubble's work led directly to the concept of an expanding universe and the Big Bang theory. Hyperion. William Herschel's discovery of Mimas in 1789 led to the discovery of no new moons around Jupiter, Saturn, or Uranus for more than 50 years. Still, in late 1848, the two groups independently discovered Saturn's eighth known satellite within days of each other. The American father and son astronomer team of William Bond and George Bond observed the new moon first. Still, the English astronomer William Lassell was the first to announce his observations. All three astronomers were credited with the discovery. Just 1 year earlier, John Herschel published a compendium of new observations in which he proposed a Greek Titan naming scheme for the moons of Saturn. Lassell endorsed the scheme and suggested that the newest moon be named Hyperion, after the Greek Titan and brother of Cronus, the Greek equivalent of Saturn. Little was known about Hyperion, except that it traveled in a relatively eccentric orbit at an average distance of about 25 times the radius of Saturn, well outside the planet's ring system, until the Voyager flybys in the 1980s, and then the Cassini Saturn orbiter mission's encounters with the Moon in the early 2000s. Hyperion is the first and largest irregular, non-spherical moon discovered by a telescope. Space mission images show it to be an elongated body, and more recent telescope spectroscopy shows it to have a surface composed of dark, reddish, dirty water ice, perhaps similar to that on the dark side of Iapetus. Hyperion has a weird, spongy surface characterized by tons of deep impact craters, sharp-edged pits and cliffs. A giant impact crater, 75 miles, 120 kilometers wide, and 6 miles, 10 kilometers deep, scars one whole side of the moon. This suggests that Hyperion is only a fragment of a larger satellite, broken apart by a giant impact. The density of Hyperion, at just 0.56 grams per cubic centimeter, indicates that it primarily consists of highly porous water ice. Indeed, astronomers think that a remarkable 40–50% of Hyperion's interior is space between icy fragments. Foucault's pendulum. Our space-age perspective on our planet now makes it a matter of common knowledge that the Earth spins. Imagine, for a moment, going back to an era when there were no satellites, space probes, or fancy computerized planetarium programs, and trying to convince someone that the Earth is spinning. It's not intuitive. The sun and sky appear to move, not the Earth. If the Earth were spinning as fast as it would need to rotate once per day, about 1,000 miles per hour at the equator, wouldn't we all get flung off into outer space? Even today, it's hard to prove to someone that the Earth spins. A simple and repeatable experiment is required to demonstrate the Earth's rotation physically. The French physicist Jean-Bernard Léon Foucault first performed the most famous of these experiments in 1851. Like any good physicist, Foucault, pronounced Foucault, understood Newton's laws and exploited the first law: bodies at rest or in motion remain at rest or in motion unless acted on by an external force, for his experiment. He constructed a long, heavy, stable pendulum using a ball, or bob, made from lead-coated brass, suspended on a wire 220 feet, 67 meters, long from the ceiling to the floor of the Pantheon in Paris. Foucault knew that in the absence of any other forces, once he started the pendulum swinging, it would continue to swing in that same plane. That is, it would remain in the same inertial reference frame relative to the fixed stars, rather than to the Earth. By setting up hour markers like those on a sundial, or small obstacles for the bob to knock over, and by compensating for friction in the wire or from the bob's motion through the air, it became easy to demonstrate that the room, indeed, the whole Earth, was slowly rotating relative to the plane of the pendulum's swing. The following year, Foucault perfected a gyroscope based on similar principles. The simplicity of Foucault's pendulum made it a sensation in the 19th century, and you can still find hundreds of them in universities, museums, and science centers worldwide. Ariel and Umbriel. The British industrialist, brewer, and amateur astronomer William Lassell gained significant notoriety and fame with his discovery of Neptune's large moon, Triton, in 1846, and his co-discovery of Saturn's small moon, Hyperion, in 1848. He developed new telescope mounting methods. He perfected the equatorial mount design still in use today for many large telescopes, and new mirror fabrication and polishing techniques, making these discoveries possible from a relatively modest and often cloudy observatory location named Starfield, near his home in Liverpool, England. Lassell's countryman, William Herschel, had discovered Uranus's moons Titania and Oberon in 1787, using a lens 18.5 inches, 47 centimeters in diameter. However, the past 6 decades have yielded no new discoveries of Uranian satellites. Thus, Lassell expected to find even dimmer moons, perhaps even closer to Uranus, when he trained his 24-inch, 61-centimeter Newtonian reflector, still the largest routinely functioning telescope in the world at that time, on the Uranian system in 1851. His patience paid off, and he discovered 2 new moons around the 7th planet. In 1852, his colleague John Herschel named them Ariel and Umbriel, after fictional characters who appeared in works by both Pope and Shakespeare. In January 1986, the Voyager 2 space probe's flyby through the Uranus system allowed for capturing high-resolution images of the sunlit southern hemispheres of these worlds. According to the data, Ariel is about 1/3 the size of the Earth's moon and has a density that suggests a mixed icy and rocky interior. Long networks of complex extensional ridges and wide, flat-floored canyons point to significant past geologic activity on Ariel, perhaps driven by tidal interactions with Uranus or its other large moons. Similarly sized Umbriel is the darkest of the Uranian moons, reflecting only about 10% of the incident sunlight, compared to about 25% for Ariel, for example. Except for some brighter, possibly fresher patches of material in a few craters. On Umbriel, Voyager found only a heavily cratered surface, with no good examples of more complex geology. Kirkwood gaps. The discoveries of the asteroids. Ceres, Pallas, Juno, and Vesta in the early 19th century opened up a new area of solar system study, so-called minor planet research. However, it took more than 35 years to discover any new asteroids after Vesta's discovery in 1807. However, improvements in telescope sensitivity by the middle of the century led to a sort of mini-explosion in the size of the known population, and by 1857, there were 50 known asteroids, all orbiting in what would be known as the main asteroid belt, between Mars and Jupiter. This asteroid population caught the attention of American mathematician Daniel Kirkwood. In 1846, Kirkwood gained some fame for proposing a sort of Kepler's law for planetary spin rates versus distance from the Sun that initially seemed correct. Despite the eventual rejection of the idea due to better data, Kirkwood continued to pursue other studies on the solar system's dynamics. When he examined the orbital properties of the 50 or so asteroids known as 1857, he noticed a remarkable thing. Instead of a uniform, random, or even bell-shaped distribution of asteroid distances from the Sun, they appeared to bunch up into clusters, with many orbiting at certain distances and none orbiting at other distances. Kirkwood discovered that the locations in the main belt devoid of asteroids are those where an object orbits multiple times, expressing this as a simple integer about Jupiter's orbit. For instance, Kirkwood found no asteroids near 2.25 astronomical units, where an object would orbit the Sun 3 times for every Jupiter orbit. He correctly proposed that the resonance between Jupiter and any objects in such places would give them an extra gravitational tug from Jupiter, eventually nudging them away from that area, or even out of the main belt entirely. More than 150 years of data have confirmed the prediction, and astronomers named these gaps in the main belt the Kirkwood gaps in honor of their discoverer. The gap positions are also known as mean motion resonances. We have found other such gaps at 5.2, 7.3, and other mean motion resonances, as well as in the rings of Saturn, where mean motion resonances among embedded moons form them. Solar flares. The Sun is the most massive, energetic, and important, to us at least, object in the solar system, so it should not be surprising that many 19th century astronomers chose to train their increasingly powerful telescopes on our nearby star to study its inner workings. By using proper filters or projecting the solar disk onto a wall or screen, astronomers could measure and monitor features like sunspots on the Sun's visible surface, the photosphere. Scientists have studied sunspots for centuries, and systematic observations from the early 17th century revealed an 11-year cycle of repeating solar activity. Improvements in telescopes and observing techniques made studying them more detailed possible. One of the most noted and prolific observers of sunspots was the English amateur astronomer Richard Carrington. On September 1st, 1859, Carrington observed an intense brightening near a particularly dense cluster of sunspots. The event lasted only a few minutes. The next day, however, saw reports worldwide of intense auroral activity and major disruptions to telegraphs and other electrical systems. Carrington witnessed the first recorded example of a solar flare, an enormous explosion in the Sun's atmosphere that can hurl high-energy particles out into the solar system at enormous speeds. The dramatic effects of this solar wind crashing into the Earth's protective magnetic field are known as a solar storm. Since then, observers have observed numerous flares and storms, but visual records and ice core data suggest that the 1859 event was the first and largest in recorded history, potentially a once-in-a-millennium mega-flare. Carrington's scientific observations established a connection between the Sun's activity and the Earth's environment, and led to intense interest in studying space weather, the interaction of the solar wind with all the planets. Today's armada of Earth-orbiting satellites, in particular, represents billions of dollars of technology and infrastructure that is highly vulnerable to disruption by solar flares and their ensuing storms, especially when sunspot activity is high. This is just one reason why NASA and other space agencies are highly motivated to continue Carrington's important work of predicting, monitoring, and understanding the effects of space weather. Search for Vulcan. The French mathematician Urbain Le Verrier was still basking in the glory of his 1846 mathematical discovery of Neptune when he took on his next theoretical challenge. Over many decades, astronomical observations of Mercury's rapid motion, which orbits the Sun in just 88 days, revealed some inconsistencies in its motion, resulting in inaccurate predictions of solar transits and other observational phenomena related to the planet. Kepler's and Newton's laws of motion worked incredibly well for the solar system's other planets, moons, and asteroids, except Mercury. What was going on? Le Verrier guessed that Mercury's orbital inconsistencies were the same as Uranus's more than a decade earlier. Another planet must exert an occasional gravitational tug on Mercury, perturbing its orbit. We were waiting to discover another planet. Le Verrier did some calculations and predicted the unseen planet's location. He figured it must be very close to the Sun, with an orbital period of only about 20 days. He even named it Vulcan, after the Roman god of fire. He announced his discovery to the French Academy of Sciences in 1859, and the search for Vulcan continued. Mercury is extremely challenging to observe with a telescope due to its constant glare from the Sun, which prevents it from reaching a distance of about 20 degrees in the sky. Even more challenging was the prediction that Vulcan would never reach a distance of more than 8 degrees from the Sun. Still, professionals and amateurs searched. Le Verrier pursued a few reports of small objects transiting the Sun in roughly the right place, or objects of the appropriate brightness observed during eclipses. But follow-up observations could not verify any of these reports. Le Verrier passed away in 1877, believing that Vulcan remained undiscovered. Because Einstein's theory of general relativity and the curvature of space-time close to the Sun eventually explained Mercury's orbital motions, astronomers never found Vulcan. Still, Le Verrier's search lives on in some way. Modern astronomers are now searching for a hypothesized population of small asteroids inside Mercury's orbit called vulcanoids, white dwarfs. In the second half of the 19th century, skilled astronomers and instrument makers, such as William Lassell in England and Alvan Clark in America, designed, manufactured, and operated larger, higher-quality telescopes. Clark specialized in designing and grinding large glass refracting lenses, which he combined to achieve high angular resolution and achromatic performance, eliminating the colored rainbow and halo artifacts that plagued many large lenses in previous refractor designs. Alvan Clark and Sons, telescope makers in Massachusetts, gained a worldwide reputation for high-quality instruments, many of which are still in operation today. One of those Clark sons was Alvan Graham Clark, who often tested the company's new lenses on his own astronomical research. On one such occasion, on January 31, 1862, while observing from the outskirts of Boston, the younger Clark trained a new 18.5-inch, 47-centimeter refracting telescope on the bright nearby star Sirius. In 1844, German mathematician Friedrich Wilhelm Bessel predicted that Sirius and Procyon's bright stars had correct motion changes caused by unseen companions. The superbly clear night and the excellent quality of the lenses enabled Clarke to discover that faint companion to Sirius, now known as Sirius B. Despite being much fainter, Sirius B's spectrum resembled Sirius's by the early 20th century. We soon recognized it, along with a few other visually dim stars, as part of a new class of small, hot stars dubbed white dwarfs. White dwarfs are now known to be a common end result of low-mass, sun-like stars that have run out of hydrogen fuel but are too small to have exploded into supernovas. By analyzing their orbits and using Kepler's laws, white dwarfs like Sirius B are extremely dense, packing anywhere from 0.5 to 1.3 times the mass of the Sun into a volume the size of the Earth, for a density of more than 1,000 grams per cubic centimeter. As such, white dwarf stars are members of a special club of compact objects, including neutron stars and black holes, with the highest known densities of anything in the universe. Source of the Leonid meteors. On a clear, moonless night, go out to a dark sky location away from the city, park yourself on a blanket or in a nice reclining chair, and look up. Once your eyes have adapted to the dim light of the stars, it won't be long until, out of your eye, you spot a short, bright streak of light zipping across the sky. You've just seen a meteor, a tiny bit of rock or ice from space entering the Earth's atmosphere and burning up from the friction. Often called shooting stars, a typical clear night can reveal a few meteors per hour. Once in a while, though, usually around the same time each year, careful and lucky observers can spot dozens or perhaps hundreds of meteors per hour, a meteor shower. Extremely rarely, a storm of thousands and thousands of meteors per hour can briefly light the night sky, creating a cosmic fireworks show, rivaling any New Year's Eve or Independence Day celebration. For millennia, people viewed such meteor showers or storms as ominous. Astronomers uncovered the connection between meteor showers and comets in the late 1860s. The key to solving the mystery was the discovery in 1866, independently in France and America, of a new short period, 33-year, comet named Tempel-Tuttle after its discoverers. Other astronomers, including the French mathematician and Neptune discoverer Urbain Le Verrier, realized that Tempel-Tuttle's orbit was remarkably similar to the orbits of meteors often seen in the mid-November shower, which are known as the Leonids. This allowed astronomers to accurately predict the next big Leonid shower, which occurred around the turn of the 20th century, and thus proved that meteor showers and storms happen when the Earth passes through patches of icy and rocky debris caused by a comet that passed through the same part of space sometime before. In addition to the Leonids in mid-November, you can also enjoy watching the fiery demise of tiny bits of comets during the Perseid shower in mid-August from comet Swift-Tuttle, the Orionids in late October from Halley's Comet, and more than a dozen other increased meteor activity events throughout the year. Helium, a total eclipse of the Sun, when the new moon completely covers the Sun's disk and casts its shadow onto a small part of the Earth, is a spectacular and inspirational sight. For most human history, people treated such events as portents of fear, doom, and change. By the 19th century, however, scientists treated accurately predicted eclipses as grand natural experiments, chances to study the Sun's atmosphere under special circumstances. The French astronomer Jules Janssen mounted a special expedition to India on August 18, 1868, to observe the total solar eclipse and take spectroscopic observations of the solar corona. His data revealed a new, unidentified Fraunhofer-like emission line in the Sun's spectrum. A few months later, the British astronomer Norman Lockyer developed a method to acquire spectra of the Sun's atmosphere without an eclipse, and he observed the same new spectral line. Lockyer and Janssen named the new element helium, after the Greek word for the sun. By the end of the 19th century, scientists discovered helium, He, on Earth as a gas associated with radioactive uranium deposits. Scientists studied the new gas in detail, learning about its extraordinary properties. For example, helium liquefies at 4 degrees above absolute zero, and at temperatures very close to absolute zero, it becomes a superfluid, an almost frictionless, zero viscosity material. More than a century of experiments and observations have revealed helium to have a relatively simple and stable structure, with a nucleus most commonly having 2 protons and 2 neutrons, He4, but rarely with only 1 neutron, the isotope He3. Because of its simplicity, helium is the second most abundant element in the universe, and most of it likely formed in the Big Bang. Even today, some helium forms when radioactive elements, such as uranium, decay. It is perhaps a humbling scientific lesson worth remembering that Janssen and Lockyer, taking the time to search for the unexpected, enabled the discovery of a colorless, odorless, non-toxic, inert material that we've since discovered constitutes nearly a quarter of the observable mass of our entire galaxy. Deimos. By the mid to late 19th century, the telescope's use and refinement had allowed astronomers to discover 2 new planets and more than a dozen new moons in the outer solar system. However, the inner solar system yielded only a few discoveries, excluding the discovery of a small number of main belt asteroids. Asaph Hall, an American astronomer and U.S. Naval Observatory professor, was surprised to learn that only a few astronomers had seriously tried searching for any moons around Mars. To be sure, it was a difficult problem because of the intense glare from the red planet itself, but Hall knew that he had unique access to an excellent instrument, a 26-inch, 66-centimeter Alvan Clark and Sons refractor that was, at the time, the largest refracting telescope in the world. Mars and the Earth pass each other approximately every 26 months during an opposition. Mars is opposite the Sun. Hall used the excellent opposition of 1877 and the Clark refractor's high image quality to search for Mars satellites. He spotted a faint object near and moving with the planet on August 11, 1877. On subsequent nights, he verified that it was a moon in orbit around the planet, accompanied by a second moon even closer to Mars. A colleague suggested naming the moons after the Greek sons of Mars, Dread, Deimos, and Fear, Phobos, and the names stuck. Hall and others realized that Deimos must be very small, but little more was known until space missions to Mars began observing the satellites as opportunities arose. Deimos has since been discovered to indeed be tiny, 9.3 x 7.5 6 miles, 15 x 12 x 10 kilometers, irregular and asteroid-like in shape, with a cratered but strangely smooth and muted surface texture. With a density of about 1.5 grams per cubic centimeter and no evidence of an icy surface, astronomers speculate that Deimos may be a relatively porous, rocky object, with a composition similar to some of the chondritic meteorites, the building blocks of Earth and other planets. However, it may take a dedicated mission to Deimos to figure out if it is a captured asteroid. Phobos. After the initial discovery of Deimos on August 11, 1877, the American astronomer Asaph Hall continued to scan the skies around Mars using the 26-inch, 66-centimeter Alvan Clark and Sons refractor of the U.S. Naval Observatory in Washington. Fog and bad weather frequently interrupted D.C. Hall's efforts, but his persistence paid off. Not only could he confirm that Deimos was in orbit around Mars, but on August 17, 18, he could peer even closer into Mars and discover a second faint small moon, which was eventually named Phobos. Hall and other astronomers quickly realized that Phobos orbits closer to Mars than any other known moon relative to its primary planet. So close, in fact, that with an orbital period of just over 7.5 hours, it actually spins around Mars faster than Mars itself rotates on its axis. This meant that an observer on Mars's surface would see Phobos rise in the west and set in the east, even though it orbits Mars in the same direction as Mars spins. The silhouette of Phobos as it eclipses, transits, the Sun, photographed from the NASA Mars rover Opportunity on January 21, 2006. Modern space missions have been able to reveal more about this tiny, slightly reddish, asteroid-like world, but much still remains a mystery. Phobos is irregular in size, 17x 13.7x 11 miles, 27x 22x 18 kilometers, and has a density near 1.9 grams per cubic centimeter, suggesting a porous, rocky, chondritic composition, perhaps similar to Didymos's. Heavy cratering covers the surface, with a series of deep grooves encircling one large crater, Stickney, named for Hall's wife, Angeline Stickney. Is Phobos an asteroid that Mars somehow captured from the nearby main asteroid belt? Or is it a piece of Mars created from the ejected fragments of a giant impact on the red planet? In 1988, the Soviets sent 2 robotic probes to land on Phobos, but both failed, one en route and the other after only a few months in Mars orbit. In 2011, Russia launched a new robotic mission, but it failed shortly after launch. New mission ideas are in the works, but it seems that Phobos will continue guarding its secrets. End of the ether. In 1676, Ole Christensen Romer, a Danish astronomer, and his Dutch colleague Christian Huygens emerged as the first scientists to demonstrate that light travels at a finite speed. Their initial estimate of the speed of light was a little low, but by the 1860s, physicists such as Jean Foucault had come very close to the modern accepted value, 186, 282 miles, 792 kilometers per second. However, 19th century scientists were still uncertain whether light required some medium to travel through. Isaac Newton, following Aristotle, argued that there might be a luminiferous ether, or simply there, within which particles of light traveled. In the late 1870s, the Scottish physicist James Clerk Maxwell described a way that physicists could test for the existence of the ether by searching for slight variations in the speed of light, depending on whether the Earth was moving toward or away from the ether. In 1887, the American physicists Albert Michelson and Edward Morley turned Maxwell's ideas into an elegant experimental test for the existence of the ether. The Michelson-Morley experiment divided a light beam into 2, then used mirrors and a small telescope to recombine the beams. Changing the distance between the mirrors could cause the beams to add or subtract from one another until a characteristic interference pattern of light waves emerges in the telescope, like wave ripples merging on a pond. The scientists would observe a very sensitive fringe pattern change as they rotated the apparatus, which floats on a pool of liquid mercury if the light beam's speed changed due to their interactions with the ether. However, they observed no such change, proving the constant value of the speed of light and providing definitive evidence that there is no luminiferous ether. The experiment set the stage for dramatic advances in physics and astronomy in the 20th century, including Einstein's general and special relativity theories. Star color, star temperature. Physicists made major advances in understanding light and energy in the second half of the 19th century. For example, the German physicist Gustav Kirchhoff developed fundamental equations describing how a hypothetically perfect light-absorbing object called a blackbody should emit energy as electromagnetic radiation at a particular temperature. He found that black bodies at the temperatures of typical real-world objects radiate a continuous spectrum of energy, from the long wavelength part of the radio and infrared spectrum to the higher energy, shorter wavelength visible and ultraviolet wavelengths. A German physicist, Wilhelm Wien, developed these concepts in 1893 and established Wien's law, a simple relationship demonstrating the inverse relationship between an object's temperature and its peak energy emission wavelength. Hotter objects emit most of their energy at shorter UV and visible wavelengths. Cooler objects emit mostly in the infrared. Max Planck, another German physicist, would further expand on these ideas about black bodies and light, helping to create the field of quantum mechanics. Astronomers used this new understanding of light and energy to visually interpret objects they could observe. Specifically, Wien's law helped astronomers deduce the relative temperatures of the stars. Hotter stars should emit more of their energy at shorter wavelengths and thus appear bluer, and cooler stars should be emitting most of their energy at longer wavelengths, with their spectra peaking toward the yellow, orange, and red end of the spectrum. Our Sun, for example, is a yellowish star, putting it near the average to slightly cooler than average end of the stellar color scale. As a result, scientists systematically understood the star's origin, evolution, inner workings, and ultimate fate in the 20th century, using their colors as key observational parameters to classify them according to temperature. Milky Way dark lanes. The grand Milky Way sweeps from horizon to horizon, with bright starry bands and black inky lanes stretching out like a celestial Jackson Pollock painting splashed across a grand cosmic canvas. On such beautiful nights, it's easy to understand our ancestors' reverence for the night sky and their need to understand what they saw. In the late 19th century, many of the world's major cities were still considered arc sky observing sites, but the electrification of the night sky became ubiquitous only after World War II. Thus, the American astronomer E. Barnard jumped at the opportunity to move to the University of Chicago in 1895 to access what had just become the world's largest refracting telescope, the giant 40-inch, 102-centimeter lens at Yerkes Observatory. Armed with a great telescope and his newfound interest in the nascent field of astrophotography, Barnard began collecting the best data on bright star fields and dark, seemingly empty gaps across the Milky Way's grand sweep. An important collaborator on B. Barnard's Milky Way studies was the German astronomer and astrophotographer Max Wolf. Wolf knew that many astronomers were puzzled by the Milky Way's dark lanes, what the English astronomer William Herschel had called holes in the sky. Careful observations could reveal faint embedded stars, or even background stars, allowing astronomers to derive the properties of the dark lanes from Barnard's photos and Wolf's analysis. Wolf made a convincing and ultimately accurate argument. The dark areas in the Milky Way are enormous clouds of relatively opaque dust that obscure the otherwise blazing light of the background stars and prevent them from shining through. He observed that pockets of bright nebulosity, possibly from newly formed stars, frequently accompanied the dark lanes, leading him to surmise that the dark regions could be cosmic cocoons, where dust and gas undergo compression and thickening, preparing to form new suns. Wolf and Barnard's early speculations about the origin of the dark lanes have turned out to be spot on. Greenhouse effect. Often, we perceive our home planet as a natural paradise, unlike the scorching heat of Venus, which is closer to the Sun, or the frigid ice world of Mars, which is farther away from the Sun. At the end of the 19th century, however, scientists realized that Earth is a habitable oceanic world only because of the influence of two relatively minor but critically important atmospheric gases: water vapor, H2O, and carbon dioxide, CO2. Without them, Earth's oceans would freeze solid, and if life had evolved on our planet, it most likely would have been significantly different. The French mathematician Joseph Fourier was the first scientist to discover that Earth's equilibrium temperature, or how warm the surface would be if heated by sunlight alone, was well below freezing in the 1820s. So why are the oceans liquid? Fourier speculated that the atmosphere might act as an insulator, trapping heat like the panes of glass in a greenhouse, but Fourier needed to figure it out. The Swedish physicist and chemist Svante Arrhenius provided the answer, showing that atmospheric gases are warming the surface by more than 30 degrees, thus keeping our planet above freezing. The specific gases responsible are mostly water and carbon dioxide. These transparent gases allow sunlight to reach the surface, but also absorb a significant portion of the planet's outgoing infrared heat energy, causing the atmosphere to warm. Fourier's earlier ideas and experiments led to the name greenhouse effect, even though the warming differs from that in a closed glass box. Arrhenius knew greenhouse warming was a simple and fortunate consequence of Earth's natural abundance of water and carbon dioxide. He speculated that past reductions in carbon dioxide, in particular, could explain the ice ages. He was the first to further speculate that future burning of fossil fuels could enhance carbon dioxide abundance and lead to global warming. The Earth's climate is more complex than Arrhenius envisioned, but his concern over people's role in changing the Earth's environment has turned out to be prescient. Radioactivity. In Europe and America, late 19th century physics labs were abuzz with new discoveries related to electricity and magnetism. The newly created ability to generate and store large voltages and currents for use in a variety of experiments often led to surprises, such as the German physicist Wilhelm Röntgen's 1895 study of high-voltage cathode ray tubes that generated a mysterious new form of radiation, which he dubbed X-rays. French physicist Henri Becquerel suspected that X-rays could cause some natural material's ability to phosphoresce or glow in the dark. In 1896, he conducted a series of experiments to determine if these materials emitted X-rays when exposed to sunlight, and he accidentally discovered that one of the materials, uranium salts, spontaneously emitted radiation on its own. He had discovered radioactivity, something altogether different from X-rays. Becquerel went on to collaborate with fellow French physicists Pierre Curie and Marie Skłodowska. Curie, who were also interested in the strange and exotic behavior of this newly discovered spontaneous radiation. Marie Curie's studies of uranium led her to discover two new radioactive elements: polonium, named after her native Poland, and radium. Becquerel and the Curies received the 1903 Nobel Prize in Physics for their fundamental discoveries. Scientists have utilized radioactivity as a natural lock for the past century due to its predictable energy release and elemental decay. Using the age and evolution of the Sun as a guide, scientists have used radioactivity to accurately determine the ages of the Earth, Moon, meteorites, and, by extension, the entire solar system and beyond. Because of radioactivity and the pioneering work of scientists like Becquerel and the Curies, we now know with astonishing precision that the Earth is 4.54 billion years old and that the solar system formed 4.567 billion years ago. Phoebe. By the end of the 19th century, most astronomers realized that building progressively larger telescopes was not the only way to study progressively fainter objects. Just as important as increasing light-gathering power was increasing the sensitivity of the detector used to record that light. As a result, more observatories were converting their detector of choice from the human eye to the photographic plate. The Harvard College Observatory, HCO, was no exception. The late 19th century HCO director Edward Charles Pickering pioneered astrophotography to collect and record high-resolution spectra of stars. Pickering's brother, William Henry Pickering, was also an HCO astronomer. In 1899, he analyzed photographic plates of the sky near Saturn, taken a year earlier by HCO staff member Delisle Stewart, and discovered a faint new moon orbiting the ringed planet. But this was quite an oddball moon. It orbited backward compared to Saturn's other moons, in a highly eccentric and tilted orbit 4 times farther from Saturn than the next closest moon, Iapetus. W. H. Pickering named the new moon Phoebe, following the theme of naming Saturn's satellites after titans from Greek mythology. We discovered Phoebe, the first moon in our solar system, using photography instead of the naked eye. Astronomers gained more detailed information about Phoebe during the Voyager 2 Saturn flyby in 1981, particularly through the Cassini-Saturn orbiter mission, which commenced in 2004. It is a relatively large and somewhat spherical moon, about 134 miles, 220 kilometers in diameter, with low reflectivity, approximately 6%, and moderately low density, 1.6 grams per cubic centimeter. Bright, icy patches appear beneath the dark surface layers along steep slopes, and spectroscopy measurements show some to be carbon dioxide ice. P Phoebe's composition and strange orbit suggest it might be a captured Centaur object, an interloper diverted inward from the Kuiper belt. Impacts on Phoebe have created an enormous, tilted, dark and diffuse distant ring of icy, rocky material around Saturn, some of which appear responsible for darkening the leading hemisphere of the two-toned Iapetus. Quantum mechanics. What is light? The question has perplexed philosophers and physicists for millennia. Aristotle and his followers thought it to be a wave-like disturbance propagating through the air, while followers of Democritus subscribed to a so-called atomist theory, which posited that light existed as particles. Debates about light's wave-particle duality permeated Renaissance physics as well. Isaac Newton believed that only corpuscles, particles of light, could explain its behavior in optics. Christian Huygens held just as firmly that light must be wave-like because it required a medium to travel through and refract. At this confusing stage, late 19th century physicists began to propose a fundamental paradigm shift in our scientific understanding of the very nature of matter. The revolution began with a mathematical trick of sorts by German physicist Max Planck. Planck was trying to understand why objects of a given temperature, such as atoms, molecules, or stars, radiate and absorb energy, and why they sometimes produce distinct bright emission lines or dark absorption lines in their spectra. Planck's revolutionary assumption at the turn of the century was that matter could only emit or absorb light, also known as radiation or energy, in discrete packets known as quanta, whose energies solely relied on the frequency or wavelength of the light. P. Planck's quantization of energy led to a detailed energy level theory of electrons orbiting an atomic nucleus, proposed by physicists such as Niels Bohr, 1885-1962. In the Bohr model of energy levels in an atom, such as the sodium atom depicted here, electrons gaining and losing energy between levels explain the bright and dark lines in atomic spectra, lower right, at discrete wavelengths. Planck saw energy quantization as a straightforward mathematical assumption required to solve an equation, similar to the physics joke of suppose a spherical shape. It's not necessarily an expression of any physical reality. But his contemporaries, including the physicist Albert Einstein, saw a deeper truth in Planck's work, proposing that light consists of quanta of energy called photons, whose interactions with matter follow wave-like equations. Rather than a conundrum, the wave-particle duality of light became a fundamental tenet of a new branch of physics called quantum mechanics. Pickering's Harvard computers. Like most other scientists, astronomers like to group the objects they study into convenient classes or groups, making it easier to compare and contrast their properties and histories. Coming up with a suitable scheme to classify the stars was particularly important. Thousands are visible to the naked eye, and millions are accessible from the telescope. The early star catalogues of Hipparchus, Ptolemy, and Alsoph recorded the relative magnitudes of the brighter stars and sometimes their relative colors, from bluer to redder. Father Angelo Secchi, an Italian astronomer, acquired spectroscopic data for thousands of stars in the 1860s, developing the first stellar classification scheme and dividing them into 5 main classes based on spectral patterns. Many astronomers, including Harvard College Observatory Director Edward Charles Pickering, worked on refining and extending Secchi's scheme to classify millions more stars. For his project, Pickering had access to excellent telescopes, and like other observatory directors of the time, he hired human computers to help sift through and analyze the enormous data set, thousands of photographic plates, under collection. Many of these computers were women hired for little or no pay to perform what many of their male employers regarded as menial and tedious work of measuring stellar spectral lines. Some of these women became quite skilled in stellar spectroscopy and went on to make important contributions to the field. Among the standouts was Annie Jump Cannon, who used her knowledge of the strengths of absorption lines to reorganize and simplify what had become overly complex and competing schemes. Astronomers still use Canon's 1901 class names, OBAFGKM, which range from bluer and weaker to redder and stronger lines. Subsequent research would demonstrate a direct correlation between her classes, stellar temperature, and stellar evolution. Himalaya. As evidenced by the discovery of Phoebe in 1898, astronomers were scanning ever larger volumes of space around giant planets in search of new moons. Edouard Roche and George William Hill, two 19th-century astronomers, expanded on Joseph-Louis Lagrange's celestial mechanics work to come up with more accurate estimates of how far a moon could be from a planet and still stay in a stable orbit, a realm that is today known as a planet's Hill sphere. In 1904, Lick Observatory astronomer Charles Perrine discovered a faint, distant outer moon of Jupiter, orbiting 4 times as far from the planet as Callisto, the outermost Galilean satellite. People called it Jupiter 6 until 1975, when they finally named it Himalaya, after the Greek nymph who gave birth to 3 of Zeus's sons. En route to Saturn, the Cassini mission took distant photos of Himalaya, revealing its size to be around 93 miles, 150 kilometers across. Since then, researchers have discovered Himalaya to be the largest and brightest of a veritable swarm of over 50 small, irregular satellites orbiting Jupiter in distant orbits. However, Jupiter is not alone in hosting irregular satellites. Saturn has 38, Uranus has 9, and Neptune has 6. Many irregular moons orbit backward, retrograde, relative to the main moons of the giant planets, and many are in significantly tilted orbits relative to their primary planet's equator. Unlike the main moons and Earth's moon, none appear tidally locked, with one face always pointed toward the primary planet. These characteristics lead astronomers to believe that outer irregular satellites, like Himalaya, are captured bodies. Perhaps they formed nearby, but eventually they wandered close enough to become gravitationally trapped in a giant planet's Hill sphere. They may have been main belt asteroids, or Kuiper belt objects gravitationally diverted and captured. Dedicated space missions may need to target these tiny worlds to find out. Einstein's miracle ear. Imagine learning something new about the nature of the universe, space, and time that nobody else knows. And then, imagine if no one would believe you, or even understand you when you talked about it. Would the immense frustration of being so far ahead of your time overpower the sheer, unbridled joy of making one of science's most important discoveries? Albert Einstein, the physicist and visionary, faced this dilemma. Born in Germany to middle-class parents, Einstein demonstrated an early aptitude for math and physics in school, along with unconventional thought and conflicts with authority. After graduating from a Swiss college with a degree in physics, he was unsuccessful in finding a teaching job. So in 1902, he began working in the patent office in Bern, specializing in electromagnetics. Still, he continued to dabble in physics. And boy, did he dabble. In one magnificent year, 1905, Einstein worked out the details of the particle nature of light and the so-called photoelectric effect that is the basis of all modern digital camera CCD, charge-coupled device detectors. He explained the tiny random movements of molecules called Brownian motion. He introduced the theory of special relativity, which set the speed of light as immutable, meaning that both space and time change in bizarre ways as one approaches light speed. And perhaps most notably, he showed that energy and mass are fundamentally related through the famous equation E Shams mc2, a powerful new concept that would eventually lead to the nuclear era that we live in today. This prolific outpouring of new ideas and explanations earned him a PhD from the University of Zurich, and shortly after that, led to a Nobel Prize in recognition of his genius. Einstein continued to develop new ideas and extend his previous ones throughout his life. One of his most famous later theories was general relativity, which explained gravity as a change in the shape of normal, 4-dimensional space and time, what physicists call the space-time continuum. For over a century, astronomers and physicists have been testing and extending Einstein's relativity theories and other concepts, nearly all of which have proven correct. Jupiter's Trojan asteroids. The advent of photography in astronomy enabled the discovery of faint objects because photographic plates are more sensitive than the human eye, and fast objects, such as asteroids, which move through the sky at a different rate from the stars. Max Wolf, a German astronomer, was among the leaders in late 19th and early 20th century astrophotography. Throughout his career, Wolf discovered almost 250 asteroids using his photographic methods. On February 22, 1906, Wolf made one of his most significant discoveries when he identified the 528th known indoor planet. Unlike most others, however, this one was far beyond the main asteroid belt, with an average distance from the Sun of around 5.2 astronomical units, almost the same as Jupiter. The Austrian astronomer Johann Palisa, also a prolific discoverer of asteroids, found that Wolf's discovered object was orbiting the Sun in approximately the same orbit as Jupiter, but about 60 degrees ahead. The French mathematician Joseph-Louis Lagrange proposed the idea of gravitationally balanced stability regions, or Lagrange points, in 1772, and it became clear that Wolf had verified it after finding more asteroids in the same area, and a corresponding area some 60 degrees behind Jupiter. Wolf had discovered the first of what would later be named by Palisa the Trojan asteroids, in honor of the Trojan War's heroes. Wolf's asteroid number 588, which orbits near the L4 Lagrange point of the Jupiter Sun system, was eventually named Achilles after the Greek hero from Homer's Iliad. Other warriors from the Greek camp named other asteroids in the L4 region, while heroes from the Trojan camp named those in the L5 region. Astronomers have discovered more than 4,000 Trojans between the two camps, and they estimate that the L4 and L5 clouds of Jupiter Trojans may contain up to 1 million asteroids larger than 0.6 miles, 1 kilometer, in size. Many are dark and reddish and may look like inactive comets, but little else is known about this enormous population of small bodies. This is a graphical representation of the positions of 4,079 Jupiter Trojan asteroids, yellow dots, with well-known orbits as of 2011. The leading, L4 cloud of Reeks is at the top. The trailing, L5, Rojans, are at the lower right. Jupiter is at center right. Using the Celestia Planetarium program, we created the plot. Mars and its canals. During the 1877 opposition, an excellent and relatively rare closer-than-normal alignment between Earth and Mars led to the partial discovery of the Martian moons Phobos and Deimos. Others took advantage of the opportunity to focus on Mars itself, including Italian astronomer Giovanni Schiaparelli, who created numerous maps in which he gave the planet seas, darker areas, and ontinents, bright areas, historical Latin and Mediterranean names. He also observed fine, dark, linear features on the planet that he thought might be channels of some kind. Many people mistranslated the Italian word for hanals, or canali, into English as canals. The Massachusetts industrialist, author, and astronomy enthusiast Percival Lowell became smitten with Schiaparelli's and other descriptions of such linear features on Mars, and was convinced that higher quality observations could reveal the features in more detail. In 1894, he used part of his family fortune to found a high-altitude observatory in Flagstaff, Arizona, and to equip it with a 24-inch, 61-centimeter, Alvan Clark and Sons refracting telescope. Lowell Observatory quickly became one of the world's premier centers for astronomical research, and Lowell focused much of his own observing time on detailed observations and drawings of Mars. Lowell saw intricate networks of dark, linear markings crisscrossing Mars, markings that could only be the creation of an intelligent species. In his popular 1906 book, Mars and Its Canals, he imagined that these were alien waterways designed to bring meltwater from the polar caps down to the great equatorial cities of the Red Planet. He popularized the idea that a race of highly skilled engineers inhabited Mars. Modern photography and space missions have revealed that Schiaparelli's and Lowell's scans were likely optical illusions. However, the public's and scientists' fascination with Mars as a potential life abode has remained as strong. Tunguska explosion. On June 30, 1908, a spectacular event awakened many residents of what is now the Krasnoyarsk Krai region of remote central Siberia, near the Tunguska River. Around 7:15 a.m., the skies above Siberia erupted in what eyewitnesses reported as a blinding flash of light, followed by thunderous explosions. The ground shook with the force of a magnitude 5.0 earthquake. A fierce hot wind and a rain of fire stripped and felled 80 million trees over more than 801 square miles, 2,100 square kilometers, an area half the size of Rhode Island. Asia and Europe recorded seismic shock signals from the event, and night skies worldwide glowed with an eerie light for several days afterward. Scientists suspected that the residents of Tunguska had experienced a meteoroid impact. The first scientific group to study the remote uninhabited region didn't arrive until 1927, when the Russian mineralogist Leonid Kulik searched vain for the resulting impact crater and potentially valuable iron-nickel meteorite deposits. Shockwaves, heat, and fire primarily caused surface damage during the airburst explosion, but no associated crater formed. For more than a century, planetary scientists have debated the nature of the impactor, with many claiming that it must have been an icy comet fragment that disintegrated catastrophically from atmospheric entry, and others claiming that the object must have been a small, rocky asteroid, perhaps a rubble pile object that was also too weak to survive on the surface. Whatever its origin, an object only about 33 feet, 10 meters across, traveling at around 6 miles, 10 kilometers per second, exploded around 6 miles, 10 kilometers, above the surface with an energy of about 10 megatons of TNT, about 1,000 times the explosive yield of a World War II atomic bomb. Remarkably, the Tunguska explosion did not claim any lives. Tunguska was a wake-up call for understanding impact events, especially the catastrophic effects that even small objects traveling at extreme velocities can have on our environment when they occasionally slam into our planet. Cepheid variables and standard candles. Astronomers have long known that measuring the distances to the nearest stars should be possible using their parallax shift from Earth's motion around the Sun over a year. However, even with the world's largest telescopes, how could we measure the distances to farther off stars without detectable parallax? The answer came from Henrietta Swan Leavitt, one of Harvard College Observatory Director Edward P. Pickering's Harvard Computers, a female staffer tasked with analyzing millions of stars on thousands of photographic plates. Henrietta Swan Leavitt concentrated on the brightness changes in periodic or pulsating variable stars. She examined thousands of variables and discovered an interesting pattern among a certain class called Cepheid variables, after the prototype Delta Cephei. In 1908, she published her initial finding that the brighter or more luminous the Cepheid, the longer its period was. This period-luminosity relationship meant that Cepheids with the same period that vary in brightness must be at varying distances from us. If we could independently determine the distance to any Cepheid, we could use them as yardsticks or standard candles. In 1913, the Danish astronomer Einar Hertzsprung independently determined the distances to several Cepheid variables using sensitive parallax measurements. These provided the key to estimating the distances to any other Cepheids. Unfortunately, Leavitt's largely unheralded discovery and subsequent analysis of Cepheids in the Andromeda galaxy and elsewhere led to the proof that Andromeda and other similar nebulae were actually independent galaxies of their own, at vast distances of millions of light-years beyond the Milky Way. Main sequence. In the early part of the 20th century, astronomers worldwide were characterizing and classifying enormous numbers of stars in terms of their colors and spectroscopic lines, expanding on the methods pioneered by Edward Pickering's group at Harvard. When the Danish astronomer Einar Hertzsprung and the American astronomer Henry Norris Russell plotted the spectral classes or temperatures of the stars against their actual brightness, i.e., after correcting their apparent brightness in the sky for their distance from us, they independently noticed an important advance. Most of the stars clustered in a broad sequence from upper left to lower right. Hertzsprung coined the term in sequence to describe this prominent trend among the stars. Around 1910, people started using these plots, known as Hertzsprung-Russell (HR) diagrams. Over the next few decades, astronomers began to understand that the main sequence was more than just random clustering. It represented an evolutionary pathway for tracking the age and eventual fate of the stars. Most stars are born when their central pressures and temperatures are high enough for the nuclear fusion of hydrogen atoms into helium. During this hydrogen-fusing phase of its lifetime, a normal star will plot on the main sequence at a position that depends on its mass, with luminous stars a few to 10 times the mass of the Sun, blue giants, on the upper left end of the plot, and dim stars from about 1/10 to 1/2 the Sun's mass, red dwarfs, on the lower right. As stars age and exhaust their hydrogen fuel, they diverge from the main sequence and eventually exhibit characteristic, often spectacular behaviors that again depend on their mass. Astrophysicists such as Arthur Eddington and Hans Bethe later understood the details of stellar interiors, making it possible to predict how stars with specific masses would live and die. Our Sun turns out to be an average mass, middle-aged main sequence star that appears destined in about 5 billion more years to bloat up into a red giant, expel its outer layers into a planetary nebula, and then fade away as a white dwarf. Size of the Milky Way. During the decades since Cepheid 1908, astronomers have found variable stars useful as measuring sticks for determining cosmic distances. They work to determine distances to spiral nebulae, globular clusters, and other enigmatic objects to determine whether they were inside or outside of the Milky Way. Indeed, the size of the Milky Way itself was the subject of intense debate, with many astronomers believing that it essentially was the universe. On the other hand, the 18th century philosopher Immanuel Kant labeled the distant nebulae as just one of numerous distinct island universes. The first astronomer to make an experimental estimate of our galaxy's size was American astronomer Harlow Shapley, who studied the distribution of globular clusters in the sky. Shapley used Cepheid variable stars to determine the distance to a nearby globular cluster, assuming they were all the same size, and using the changing apparent diameter of other clusters to estimate their distances. By 1918, he had determined that the globular clusters form a sort of halo around the plate-like disk of our galaxy, enabling him to estimate that the Milky Way is about 300,000 light-years across, with the Sun not centered, but offset by about 50,000 light-years. So much for heliocentrism. This was astonishingly larger than many had thought the galaxy to be, and it convinced Shapley that there were no island universes. The globular clusters and spiral nebulae must all be bordering or within the Milky Way. Shapley's estimate of the size of the Milky Way was about 3 times too large, mostly because his assumption that all globular clusters are the same size is not valid. The disk of our galaxy measures approximately 100,000 light-years across and 1,000 light-years thick, featuring a somewhat thicker central bulge, with the Sun situated approximately 27,000 light-years away from the center. Shapley was right about the globular clusters being in and near the Milky Way in a diffuse halo, but he was wrong about the spiral nebulae. As Edwin Hubble and others demonstrated in subsequent decades, spirals and many other forms of nebulae are separate galaxies, some like our own, some not, but all are millions to billions of light-years away. Centaur asteroids. Even though the number of discovered asteroids approached 1,000, in the early 20th century, astronomers were still occasionally surprised by the discovery of new, enigmatic objects. A case in point was the German astronomer Walter Baadé's discovery of asteroid 944 in 1920. The asteroid, which was eventually named Hidalgo after the Mexican priest and independence leader Miguel Hidalgo, turned out to have an extremely comet-like, tilted and eccentric orbit, eccentricity of 0.66, that takes it from the inner edge of the main asteroid belt, 1.95 astronomical units, or AU, out to a distance almost as far from the Sun as Saturn, 9.5 AU. Scientists discovered another asteroid, 2060 Chiron, in 1977, moving in a similar comet-like orbit between Saturn and Uranus. Since then, scientists have discovered several hundred more eccentric asteroids with orbits roughly between Jupiter and Neptune. Members of this part asteroid, part comet population are called centaurs, inspired by mythical creatures that are part horse and part human. The diverse colors of centaurs indicate their composition of various substances. In fact, some telescopic spectra reveal that they consist of water ice, methanol ice, and tholins, organic remnants from the UV radiation of methane or ethane ice. Many of these components are also present in comets. Researchers have found a weak coma, a fuzzy comet-like head, in 3 centaurs, including Chiron, indicating comet-like activity. Centaurs have yet to be encountered by spacecraft, but many astronomers believe Saturn's irregular moon Phoebe may be a captured centaur, providing a close-up view of their appearance. Given that they traverse the orbits of the giant planets and have a lifespan of just a few million years before launching into new orbits, we may need to expedite our research. Eddington mass-luminosity relation. Even though astronomers were classifying stars based on properties such as color, temperature, and intrinsic brightness, it took much longer to figure out how stars actually work. Why do they shine? Where do they get their energy? What's happening inside a star? Arthur Stanley Eddington, a British astrophysicist, was one of the scientists whose work was critical to answering such questions. Eddington was interested in understanding the gravitational collapse of nebular gas and dust to form a star. Astronomers knew that gravity was responsible for pulling the gas into a sphere and causing it to compress. But what stopped gravity from collapsing stars into smaller and smaller sizes? Eddington published a detailed model in 1924, explaining how the super-high temperatures and pressures inside a star create radiation pressure, an outward force that balances gravity and allows stars to reach their equilibrium sizes. Eddington's stellar interior models also allowed him to determine a simple relationship between a main sequence star's luminosity and its mass. A star twice as bright as another will be more than 10 times as massive, specifically LOCM 3.5. Thus, based on his work, it was possible to estimate the mass of a star just by measuring its apparent brightness and distance, and therefore, astronomers could show that the main sequence is the mass-dependent lifeline, an evolutionary track taken by about 90% of all stars. At the time, Eddington and anyone else understood the workings of the so-called mass-luminosity relationship, or the generation of radiation pressure inside a star. According to a leading theory, gravitational contraction provides energy. As Eddington speculated, nuclear fusion could generate the required energy, but the idea met with skepticism until the late 1930s. The NASA Solar Dynamics Observatory obtained this spectacular ultraviolet view in August 2010 of a dark coronal hole in the Sun's atmosphere. This region is where solar wind particles stream into space, generating auroral displays in our atmosphere. Liquid-fueled rocketry. Propelled by gunpowder burning, rockets have been around for over 1,000 years. It is believed that the Chinese were the first to use rockets in battle and for entertainment purposes, such as fireworks. But in 1903, the Russian mathematician Konstantin Tsiolkovsky wrote the first scholarly work that envisioned them as more than weapons. He also saw them as a potential means of space travel. He worked out much of the theory of rocketry, and was among the first to propose using liquid fuels instead of gunpowder to maximize the combustion efficiency and the rocket's thrust-to-weight ratio. In Russia and the Soviet Union, Tsiolkovsky holds the title of the father of modern rocketry. However, it was Robert Goddard, an American rocket scientist and Clark University physics professor, who was first able to test Tsiolkovsky's and his own theories and show that liquid-fueled rockets were feasible and could provide the thrust needed to lift significant mass to high altitudes. He created and patented crucial designs for gasoline and liquid nitrous oxide-powered rockets, as well as the idea of multi-stage rockets, asserting their potential to achieve extreme altitudes. Even though his own rocket's flights were modest by today's standards, Goddard's methods were sound, and others, including a group of post-war space race engineers led by rocketry pioneer Wernher von Braun, were able to expand on his designs to enable longer, higher, and eventually orbital and beyond liftoffs. Like many inventors, Goddard was a visionary. He often worked alone and saw possibilities that others overlooked. He was an early advocate of rocketry for atmospheric science experiments, and, like Tsiolkovsky, for eventual travel into space. It is perhaps ironic that war was the impetus for the eventual development of rockets that would posthumously achieve God's dream of space travel. Robert Goddard poses with his first liquid-fueled rocket, launched from Auburn, Massachusetts, on March 16, 1926. Unlike conventional rockets today, this model's combustion chamber, nozzle, and fuel tank were at the top. It flew for 2.5 seconds and rose 41 feet, 12.5 meters. The Milky Way rotates. In 1918, American astronomer Harlow Shapley obtained the first quantitative estimate of the size of the Milky Way galaxy by measuring the distances and directions to the halo of globular clusters surrounding the galaxy's disk. Shapley's study also allowed him to estimate the position of the galaxy's approximate center, which he placed in the brightest part of the Milky Way's vivid band of stars in the direction of the constellation Sagittarius. As it became clearer that we were embedded inside a spiral galaxy, much like others being studied in detail with astrophotography and spectroscopy, some astronomers discovered that, presumably like the other spiral galaxies, individual stars in the Milky Way could be spinning around a common galactic gravitational center. Bertil Lindblad, a Swedish astronomer in the 1920s, was the first to investigate this hypothesis in detail. In 1927, the Dutch astronomer Jan Oort carefully measured the movements of hundreds of individual stars to provide the first observational proof of Lindblad's hypothesis. He confirmed that the Milky Way rotates and, further, that the rotation is differential, that is, stars at different distances from the rotation axis orbit the center at different speeds, with farther away stars lagging behind the closer-in ones. About halfway out of the galactic center, the Sun takes about 250 million years to orbit the galaxy's center. According to S. Shapley's earlier estimate, Oort's and Lindblad's work helped refine the galaxy's exact rotational center. However, the dark lanes of dusty nebulosity that E. Barnard and Max Wolf had studied in the late 19th century obscured much of the galactic center, making it difficult for astronomers to learn more from visual observations. Later, astronomers would use X-ray, infrared, and radio telescopes to study this region intensely, eventually learning that an enormous energy source, called Sagittarius A, pronounced Sagittarius A star, probably powered by a 4 million solar mass black hole, lies at the center of our galaxy. H. Hubble's law. The 1848 discovery of the Doppler shift of light provided a tool that astronomers could use to determine the velocity of an astronomical object relative to Earth. All that was required was the ability to detect and measure the shift of a suitable absorption line, or lines using spectroscopy. In 1912, the Lowell Observatory astronomer Vesto Slipher obtained the first spectra of spiral nebulae and other objects later recognized as other galaxies. Slipher discovered that most spiral nebulae have spectral lines, Doppler shifted toward longer, redder wavelengths. They are redshifted and receding from us. The American astronomer Edwin Hubble was also interested in studying spiral nebulae, and beginning in 1919, he had the advantage of access to the brand new 100-inch, 254-centimeter Hooker reflecting telescope at the Mount Wilson Observatory in Southern California, then the largest and most sensitive telescope in the world. Hubble studied Schleifer's galaxy redshift data and spent a decade painstakingly collecting more data of his own. In 1929, Hubble published a landmark paper describing his initial results. He had found that, remarkably, the redshift of the galaxies increases the farther away a galaxy is from the Earth. Everything seemed to be moving away from us, and the farthest stuff was the fastest. This observation, Hubble's law, implies that the volume of the observable universe is expanding. This amazing result was consistent with earlier theoretical predictions about the expansion of space-time by the Russian cosmologist Alexander Friedmann, based on Albert Einstein's theory of general relativity. Edwin Hubble works on the 100-inch, 2,540mm telescope at Mount Wilson Observatory. Hubble's law states that in the past, space was smaller. Today, cosmologists interpret the data to indicate that all of space and time, the universe as we know it, began in an enormous explosion called the Big Bang some 13.7 billion years ago. Hubble profoundly changed our understanding of the cosmos. The Hubble Space Telescope, named in honor of the discoverer of the expanding universe, took this unprecedentedly sensitive photograph in 2004 after more than 11 days of exposure on the same tiny patch of the sky. Almost every dot and smudge in this photo is a galaxy. Discovery of Pluto. French mathematician Urbain Le Verrier's calculations of the likely position of a planetary mass object causing variations in Uranus's orbit enabled the discovery of Neptune in 1846. Subsequent observations of Uranus and Neptune led some astronomers to speculate that Neptune was not responsible for all the discrepancies in Uranus' orbit. There could still be an Earth-sized planet lurking way out there. Percival Lowell, a New England businessman who founded Lowell Observatory in Flagstaff, Arizona in 1894, was among the astronomers who believed in Planet X. Together with American astronomer William Henry Pickering, they made predictions about the potential location of Planet X. Flagstaff conducted an unsuccessful search from 1909 until Lowell died in 1916, during which a battle over Lowell's state put the search on hold. Pickering's 1919 search also failed. In 1929, the search resumed in Flagstaff under the leadership of 23-year-old Clyde Tombaugh, a new staff member who had impressed Lowell Observatory director Vesto Schleifer with his observations and sketches from his Kansas upbringing. Tombaugh used Lowell's 13-inch, 33-centimeter astrograph, a telescope designed to work with large photographic plates, to survey the expected regions of the sky for objects moving at the right trans-Neptunian rate. After almost a year's effort, on February 18, 1930, he found a small new world in the right place. A British girl won a subsequent naming contest by choosing the moniker Pluto after the Roman god of the underworld. Ironically, modern reanalysis of the Uranus orbit showed no discrepancy beyond Neptune's explanation. Tombaugh's discovery of Planet X was pure skill and coincidence. Nonetheless, for more than 75 years, Pluto was the solar system's 9th planet, orbiting out nearly 40 astronomical units, and now known to have 5 moons, one Charon, relatively large. In the 1990s, however, it became clear that Pluto is simply one of the largest of the small icy worlds in the Kuiper Belt. Pluto controversially and unceremoniously lost its status as a dwarf planet in 2006. Radio astronomy. Carl Guter Jansky grew up in Oklahoma, surrounded by physics and radio science. His father was a professor of electrical engineering and dean of the engineering college at the university in Norman, while his older brother was a radio engineer. It was no wonder that he went to college, majored in physics, and in 1928 took a job with the fledgling Bell Telephone Laboratories, the relatively new research arm of Alexander Graham Bell's original American Telephone and Telegraph Company, AT&T. At Bell Labs, Jansky studied how noise and static might interfere with possible long-distance transatlantic radio telephone service. He needed a way to monitor the intensity and direction of noise sources, so he built a radio telescope 100 feet, 30 meters long, steerable on a set of 4 Ford Model T tires. The telescope could detect radio signals with a wavelength half its length, or a frequency of around 20.5 MHz, MHz. In the summer of 1931, Jansky began observing with his radio telescope. He successfully identified sources of background static, detecting radio signals from nearby and distant thunderstorms, and a faint and relatively steady hiss that he couldn't initially identify. Over time, he found that the strength of the signal varied with a period of 23 hours and 56 minutes. The exact duration of the sidereal day, the time it takes the Earth to spin on its axis relative to the fixed stars. He found that the hiss was most intense when looking toward the constellation Sagittarius, specifically toward the region that astronomers had identified as the center of the Milky Way galaxy. Carl Jansky invented radio astronomy. 40 years later, scientists identified the intense radio, along with X-ray and infrared, emission from Sagittarius A, pronounced star, a region believed to harbor a 40 million solar mass black hole at the center of our galaxy. Jansky was not an astronomer, but his initiative, skill, and creativity with the world's first radio telescope inspired a new kind of astronomy and a new way of seeing and studying the cosmos. The epic Oort cloud. By the early 20th century, hundreds of years of meticulous observations had enabled the calculation of precise orbits for dozens of bright comets. They appeared to come in 2 varieties: periodic short-period comets, with orbits that bring them back into the inner solar system roughly every 20 to 200 years, and periodic long-period comets, with long, highly eccentric orbits that could take hundreds to thousands of years or more to complete, or not to repeat at all, for the related non-periodic single-apparition comets. The trajectories of the longest-period comets take them extremely far from the Sun, with some traveling as far as 50,000 to 100,000 astronomical units, almost a third of the way to the nearest star, when near their aphelion, or farthest point in their orbit. Several researchers independently noted that the cluster of aphelion distances at those extreme ranges probably meant that a supply or reservoir of comets originated at those extreme distances. The fact that long-period comets come from all directions in the sky, not just along the plane of the ecliptic, like the planets and most short-period comets, also meant that this reservoir was likely spherical, like a huge cloud surrounding the solar system. In 1932, the Estonian astrophysicist Ernst Öpik was the first to postulate the existence of this vast reservoir of comets in a paper describing the role that passing stars might have in gently nudging comets from this distant cloud into new orbits that would take them toward the Sun. Independently, in 1950, Dutch astronomer Jan Oort came up with a similar idea, but expanded to include the role of Jupiter and the other giant planets in flinging in a solar system comets out into this enormously distant cloud. Subsequent studies of new long-period comets, about one new one is discovered every year, confirm the idea. Even though it's never been directly seen, a vast cloud of distant comets appears to surround the Sun. Astronomers now call this the Oort cloud, or Öpik Oort cloud. By some estimates, there could be a few Earth masses in a trillion or more kilometer-sized comet nuclei out there. Some formed closer into the Sun, but ejected into a perennial deep freeze. Others formed at the edge of the Sun's gravity and waiting for their first gentle stellar nudge into the warmth. Neutron stars. Early 20th century advances in physics and chemistry at the molecular, atomic, and subatomic levels paralleled advances in astronomy on the grandest cosmic scales. Indeed, atomic physics helped astronomers make theories and predictions about processes that were difficult to observe directly. A wonderful example of this synergy between the macroscopic and microscopic came about shortly after the English physicist James Chadwick discovered the neutron in 1932. Neutrons are subatomic particles with about the same mass as protons, but unlike protons and electrons, they do not carry any electrical charge. Without neutrons' strong nuclear binding force in an atomic nucleus, positively charged protons would repel each other, and atoms would be unstable and fly apart. The neutron discovery had a profound impact on astronomy. For example, in 1933, the astronomers Walter Baade and Fritz Zwicky began thinking in detail about the processes that could lead to the gravitational collapse and explosion of massive stars, explosions that Zwicky dubbed supernovae. They speculated that such explosions' enormous central pressures and temperatures could unbind atomic nuclei and leave compact remnant objects behind, mostly composed of bare neutrons. They called these hypothetical objects neutron stars. According to Baade and Zwicky's calculations, neutron stars should be rapidly spinning, extremely dense objects that pack 1 to 2 times the mass of the Sun into a sphere only about 6 to 7.5 miles, 10 to 12 kilometers across, and have a surface gravity greater than 100 billion times Earth's gravity. In 1968, the discovery of a tiny, massive stellar remnant spinning at 30 revolutions per second at the heart of the Crab Nebula, a result of the supernova 1054, validated their theory. Since then, astronomers have discovered thousands of other hot spinning neutron stars, pulsars, providing precise cosmic clocks to study the extreme astrophysics of compact objects. Dark matter. We always deal with unseen forces, the wind blowing through our hair, gravity pulling us downward. However, we can make observations or run experiments that tell us these forces are there, which can ultimately reveal their source. In 1933, the Swiss-American astronomer Fritz Zwicky encountered new evidence for the action of unseen forces in the cosmos, but ran into a major, paradigm-changing roadblock because there was no apparent or perhaps even measurable explanation for what he saw. Zwicky studied clusters of galaxies, some of the largest structures known in the universe. In one study, using spectroscopy, he measured the redshifts and relative velocities of the members of the Coma cluster, a group of about 1,000 co-moving galaxies, about 320 million light-years from Earth. He discovered that the galaxies were moving relative to each other in a way inconsistent with their inferred masses. Despite accounting for all the mass visible in visible light photographs, Zwicky found an enormous amount of missing mass, about 400 times more than what he could see, needed to explain the gravitational movements of the individual galaxies. This missing mass problem led Zwicky to postulate that there must be some form of unseen matter, undetectable with then-modern methods, that was causing observed motions. Despite the development of new radio, infrared, X-ray, and gamma-ray astronomy methods, the missing mass in galaxy clusters, including our own galaxy, remained undetectable based on the motions of nearby globular clusters. Astronomers now refer to this ubiquitous unseen material as dark matter. Many studies now require the existence of apparently undetectable material that has mass and exerts a gravitational influence on normal matter. Cosmologists believe it accounts for about 80% of all matter, making the mystery extremely profound and humbling. We are a minor piece of a universe of things we don't yet understand. Elliptical galaxies, astronomers. Harlow Shapley, Vesto Slipher, Edwin Hubble, and others work on determining the galaxy's scale and collecting spectroscopic data for large numbers of spiral nebulae during the first few decades of the 20th century eventually led to the realization that there are other galaxies, other Milky Ways, each harboring hundreds of billions of stars of their own. As astronomers identified and studied more galaxies, They naturally sought to categorize them into distinct categories, just as they had done for the stars. As a leading observer of galaxies, and with access to some of the best telescopic facilities in the world, Hubble was in a particularly unique position to take the lead on galaxy classification. And lead he did. In a series of papers and lectures, eventually compiled into a landmark 1936 book called The Realm of the Nebulae, Hubble outlined a scheme for the morphologic, shape, size, brightness classification of extragalactic nebulae, now called the Hubble sequence. The elliptical nebulae, now known as elliptical galaxies, were on one end of the Hubble sequence. Elliptical galaxies are one of three main classes, the others being spiral galaxies, like our own Milky Way, and lenticular, lens-shaped galaxies, intermediate in form between ellipticals and spirals. Elliptical galaxies, as the name implies, are ellipsoidal to spherical shapes and vary smoothly in brightness from a bright central core to diffuse outer edges. Modern surveys reveal that roughly 10–15% of galaxies in the local neighborhood consist of elliptical galaxies, but fewer existed in the early universe. Ellipticals are mostly older, lower mass stars devoid of the gas and dust required for new star formation. The origin of elliptical galaxies is controversial, but some astronomers hypothesize that they may result from ancient mergers and collisions between former spiral galaxies. Nuclear fusion. Astrophysicists like Arthur Stanley Eddington empirically worked out some of the major characteristics of stellar interiors, including their extremely high pressures and temperatures in the 1920s, but substantial uncertainties remained about how stars generated their energy. Eddington had considered the possibility that nuclear fusion, fusing lighter elements into heavier ones, releasing energy in the process, might power stars like the Sun. But this was only speculation, based partly on early nuclear transmutation experiments, the conversion of one element to another, by Ernest Rutherford and others. Physicists soon had the means to work out and test theories for energy generation in stars in more detail. Among the pioneers in this field were the German physicist Carl Friedrich von Weizsäcker and the German-American nuclear physicist Hans Bethe. Bethe, in the United States, and Weizsäcker, in Germany, worked out how hydrogen atoms could fuse into helium in extreme conditions near the centers of stars between about 1937 and 1939. Bethe's 1939 paper, Energy Production in Stars, described the nuclear chain reactions that were likely at work in the interiors of average mass stars like the Sun and high-mass stars. As exciting as these discoveries were, Weizsäcker, Bethe, and their colleagues knew that the nuclear genie was out of the bottle. The artificial creation of some nuclear synthesis chain reactions, based on the same physics as star reactions, could release enormous amounts of energy. As World War II broke out, the American and German governments set their physicists to work on the weaponization of nuclear fusion. Bethe, a leading theorist, led the US effort known as the Manhattan Project, which resulted in the development and detonation of the atomic bombs that ended the war and the hydrogen bombs that initiated the long Cold War. Geosynchronous satellites. Newton's laws of gravity and motion and Kepler's laws of planetary motion, in particular, apply to artificial satellites, just as well as to planets in orbit around a star or moons in orbit around a planet. Rocket technology and astronautics, the study of navigating through space, advanced quickly after Robert Goddard developed the first liquid-fueled rockets capable of reaching high altitudes in the 1920s. Several of Goddard's contemporaries were already beginning to think about the mechanics and dynamics of orbital and beyond rocket flights. Two of those contemporaries were the Hungarian-German physicist Hermann Oberth and the Austro-Hungarian rocket engineer Hermann Potočnik, who elaborated on and worked out the details of concepts first described by the Russian mathematician Konstantin Tsiolkovsky. A geostationary or geosynchronous orbit was one of those concepts. A satellite in a geosynchronous orbit will complete one orbital revolution while it takes the Earth to spin once on its axis. an observer on Earth's surface would perceive such a satellite as stationary, parked high in the sky. Newton's second law uses the Earth's mass and rotation rate to calculate the orbital altitude of a geosynchronous satellite, revealing it to be approximately 22,000 miles, 36,000 kilometers, above the surface. The British science fiction author and futurist Arthur C. Clarke was one of the first to grasp what would ultimately be one of the most practical applications of such satellite orbits: global telecommunications, described in a 1945 magazine article called "Extraterrestrial Relays: Can Rocket Stations Give Worldwide Radio Coverage?" Clarke's popularization of the idea helped it gain widespread attention and support. Since 1964, geosynchronous satellites have gone far beyond just radio relays. Today, they also relay TV, internet, and global positioning system (GPS) signals to help us monitor Earth's weather and climate. Miranda. After the discovery of Saturn's moon Phoebe in 1898, the discovery rate of large, hundreds of miles in size, planetary moons precipitously dropped. After several decades with no major new moons discovered, solar system studies went out of fashion because many early 20th century astronomers thought the census of the solar system's main bodies was relatively complete. One scientist who continued to study and observe the planets, however, was the Dutch-American astronomer Gerard P. Kuiper. Kuiper began working at the University of Chicago's Yerkes Observatory, the world's largest refracting telescope, in the late 1930s, as well as at the new McDonald Observatory in Texas, which had a telescope with the resolution and sensitivity that Kuiper needed to search for faint new planetary satellites. In 1948, he discovered the fifth and innermost satellite of Uranus. Following the established theme, he named the new moon Miranda after a character from Shakespeare's The Tempest. Miranda's orbit, small size, and likely icy composition were all unknown until the Voyager 2 flyby of the Uranus system 1986. Miranda is indeed small, with a relatively spherical shape about 292 miles, 470 kilometers, in diameter. However, its surface is surprisingly diverse, consisting of a patchwork of regions covered by bright and dark ridges and cliffs, interspersed with bland, heavily cratered, icy terrain. They took Miranda apart, then clumsily put it back together. Some astronomers think an ancient impact may have done just that. In 1949, Kuiper also discovered a second moon of Neptune, which he named Nereid. He was a founding father of modern planetary science, pioneering spectroscopy to study planets and moons. Kuiper also discovered carbon dioxide in Mars' atmosphere and a methane atmosphere around Saturn's moon Titan, and helped pick the Apollo lunar landing sites in the 1960s. Jupiter's magnetic field. Just as in a standard wire-wound electric motor, the rotating electrically conductive, metallic interiors and/or cores of planets and satellites are prime locations for magnetic field generation. Electrical currents within Earth and Mercury's spinning, partially molten, iron-rich cores are believed to generate their magnetic fields. High electrical conductivity in a metallic core deep within Ganymede may also explain the Moon's magnetic field. Researchers have discovered stronger magnetic fields on our solar system's gas and ice giant planets. The first such discovery was in 1955, when radio astronomers from the Carnegie Institution in Washington, D.C. noticed strong radio frequency emissions from Jupiter. Starting with Carl Jansky's pioneering discovery of the strong radio source at the center of the Milky Way galaxy in 1931, radio astronomers had been scanning the skies looking for other natural sources of extraterrestrial radio waves. We have identified the Crab Nebula as another strong radio source. Indeed, radio telescope observations intended to study the Crab Nebula accidentally discovered Jupiter's radio emission, interpreted to originate from a strong magnetic field. More details about Jupiter's field came from flying spacecraft through it. First with the Pioneers in the 1970s, then the Voyagers in the 1980s, and then the Galileo orbiter and Cassini-Jupiter flyby in the 1990s and early 2000s. Sensitive magnetometers on these missions discovered that Jupiter's magnetic field is about 10 times stronger than Earth's, generating about 100 terawatts of power, or more than 1,000,000 times Earth's magnetic field radio power. The field is generated by electrical currents flowing through metallic hydrogen in Jupiter's outer core. Jupiter's magnetic field interacts with the solar wind and the moon's, particularly Io, where volcanic eruptions inject sulfur dioxide into a donut-shaped plasma torus that encircles it, ionizing it. And it is enormous. The volume of space encompassed by Jupiter's magnetic field, its magnetosphere, is the largest continuous structure in the solar system, not counting the Sun's magnetic envelope. If we could see Jupiter's magnetosphere with our eyes, it would be 5 times larger than the full moon. Neutrino astronomy. Early 20th century physicists, such as Wolfgang Pauli, who were trying to understand the nature of the radioactive decay of certain elements, knew that they had big holes in their understanding of the atom. For example, the protons and electrons created during radioactive decay couldn't explain the energy released. The discovery of the neutron in 1933 didn't help. It was too massive. We also needed an additional low-mass, electrically neutral elementary particle. Pauli proposed the existence of a new subatomic particle, later named the neutrino, little neutral one. The actual evidence for the existence of the neutrino came in 1956 from high-energy particle accelerator collision experiments. Subsequent experiments in the 1960s showed that neutrinos come in different varieties, or flavors, each associated with other kinds of elementary particles, including electrons, and that each neutrino flavor also has an antiparticle. It became apparent that atoms are busy places. The neutrino discovery paved the way for an entirely new field of neutrino astronomy. Without a charge and having almost negligible mass, neutrinos easily pass through even enormous quantities of ordinary matter at nearly the speed of light. With little attention to contrast, photons or sunlight generated in the sun's interior can take more than 40,000 years to bounce around and escape from that dense, opaque environment. Sputnik 1. Americans vividly recall where they were and what they did during key events defining certain generations or eras. Examples include the bombing of Pearl Harbor, the assassination of John F. Kennedy, the explosion of the Space Shuttle Challenger, and, of course, the traumatic terrorist events of 9/11. For one generation of Americans, the defining event came in the fall of 1957. On October 4th, the Soviet Union became the first nation to launch an artificial satellite into space. Leading Soviet rocket engineer Sergei Korolev headed the team that had created the USSR's first intercontinental ballistic missile, ICBM. And he lobbied the government to allow him and his team to modify the R-7 rocket so that it could launch a small scientific payload into Earth's orbit. The Soviet government approved Korolev's plan in the hopes that they could beat the Americans into space. They named the payload Sputnik, which is Russian for satellite. The space age had officially begun. For 3 months, Sputnik 1 circled Earth every 96 minutes, emitting a telltale beep 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 on its single-watt radio that ham radio operators worldwide could easily pick up. The satellite created a sort of mild hysteria in the United States, where the public was acutely aware of the Soviet Union's ability to launch ICBMs, outfitted with nuclear warheads, at any target on the planet. About 2 weeks after Sputnik burned, the US government stepped up its space efforts and successfully launched America's first satellite, Explorer 1. The effects of Sputnik's unprecedented mini-revolution on science and technology funding and education in the United States continue to resonate today. The Americans most influenced by Sputnik, often referred to as the Apollo generation, went on to see America win the space race, watching 12 people walk on the moon between 1969 and 1972, followed by decades of other stunning achievements. Earth's radiation belts. After the Soviet Union surprised the world with the successful launch and operation of Sputnik 1 in the fall of 1957, the US government scrambled to catch up. The Army Ballistic Missile Agency, responsible for launching the satellite on a modified Jupiter Redstone intermediate-range ballistic missile, and the Jet Propulsion Laboratory, an Army Caltech, California Institute of Technology facility near Pasadena, shared the goal of launching and operating a small satellite with a minimal, simple science payload. Explorer 1's scientific payload, the brainchild of the American space scientist James Van Allen, consisted of a cosmic ray counter, a micrometeoroid impact detector, and some temperature sensors. Although the experiments were more complex than Sputnik's simple radio transmitters, the Jupiter missile could deploy them into orbit due to their low mass, power, and volume. On January 31, 1958, the Cape Canaveral Missile Annex in Florida successfully launched America's first artificial satellite, the world's third, following Sputnik 2 in November 1957. Explorer 1 settled into a 115-minute elliptical orbit and operated its science instruments for over 3.5 months before its batteries died. The science instruments transmitted real-time data streams back to the JPL science team during the mission. Initially, the puzzling data from Explorer 1 stemmed from dramatic increases in the number of energetic particles at specific altitudes and locations around Earth. Van Allen and his team interpreted the data to reveal the presence of a zone or belt of high-energy particles or plasma confined by Earth's magnetic field. Explorer 3 confirmed the results a few months later. The satellite made the first major space science discovery, and the region of enhanced energetic particles in near-Earth space was named the Van Allen Radiation Belt in honor of the science team's leader. Explorer 1 was the first of 84 successful missions in the Explorer series. NASA and the Deep Space Network. The success of Sputnik 1 caused some soul-searching within the US government, which had been embarrassed by the Soviet launch. Part of the problem was that numerous federal agencies and branches of the military were splitting or duplicating efforts to make rapid progress in space exploration. As a result, in 1958, the US Congress and President Dwight Eisenhower established a new federal agency, the National Aeronautics and Space Administration, NASA, to oversee the nation's civilian space and aeronautics programs. Simultaneously, the armed forces formed the Advanced Research Projects Agency, now DARPA, to oversee space-related technology. Developing the critical communications infrastructure necessary to maintain contact and control of future space probes was part of consolidating the civilian space effort. For the early Explorer missions, the Army's Jet Propulsion Laboratory, JPL, at the California Institute of Technology, Caltech, deployed portable radio tracking stations in California, Singapore, and Nigeria to constantly communicate with the missions as they circled the globe. In late 1958, NASA transferred control of JPL and assigned JPL the leading role in coordinating an ambitious program of future robotic space missions, indicating the need for a more permanent communications solution. The solution was to establish the Deep Space Network, DSN, a set of small, medium, and large radio telescopes spaced roughly equally around the world so that they could remain in constant contact with NASA's space missions. Goldstone, California, near Madrid, Spain, and Canberra, Australia, established DSN stations, each equipped with one large, 230 feet, 70 meters, and several smaller, 112 feet, 34 meters, radio telescopes, along with their transmitters and other equipment. The DSN is the Earth's switchboard, the solar system's hub of interplanetary radio communications. NASA and other international space agencies run an incredible armada of over 60, soon to increase to over 90, active Earth and planetary missions. The far side of the Moon. Synchronous rotation describes how the Moon orbits Earth, spinning on its axis precisely once for each orbit around the planet. However, from our earthly perspective, the Moon appears stationary, as synchronous rotation ensures that a satellite's same hemisphere, or face, consistently faces its primary planet. As a result, our familiar view of the full moon is what astronomers call the near side, the side that always faces us. Until the age of space, no one had ever seen the side of the moon that always faces away from us, the far side. In fact, the only way to see it would be to send a spacecraft out beyond the moon and turn it around to take a picture looking back. And that's exactly what the Soviet Union did in 1959 with the Luna 3 mission, another first for the Soviet space program. On October 4, 1959, 2 years after Sputnik 1, Luna 3 launched toward the moon. 3 days later, after passing by the moon's south pole, it became the first successful 3-axis stabilized spacecraft when ground controllers directed it to take photos as it looped around the far side. The spacecraft took 29 film pictures, scanned them, digitized them, and radioed them back to Earth. The Luna 3 photos are fairly low quality compared to modern space photography, but they were good enough to enable Soviet space scientists to map and name features and discover that the moon's far side is dramatically different from the near side. The far side is more uniformly bright, with fewer dark mares, lava-filled impact basins, pronounced MAH ray, than the near side. In 1965, the Soviet Zond 3 satellite captured much better follow-up photos of the far side, revealing that the bright areas were heavily cratered, rugged highlands regions. Spiral galaxies. In the galaxy classification scheme defined by Edwin Hubble in the 1920s and 1930s, spiral galaxies, immense numbers of stars bound together and sculpted by gravity, with 2 or more arms slowly spinning around a common center of mass, represent an extreme shape, the others being elliptical and lenticular galaxy forms. We see some spiral galaxies face-on, while others appear edge-on. The arms of edge-on galaxies confine themselves to a wide, flat disk, with a central bulge encircled by a halo of distant stars and globular clusters. As worked out by Harlow Shapley and others, our own galaxy, the Milky Way, is more than 100,000 light-years across. Around 1959, radio astronomers devised ways to use spectroscopy to look at the strong, 21-centimeter emission line of hydrogen and figure out how fast the arms of face-on spiral galaxies are spinning. The expectation was that stars farther from the galactic center would rotate more slowly, following Kepler's laws, like planets orbiting a central star. However, the observations revealed that the velocities of stars remain roughly constant with distance from the galactic center. More and more spiral galaxy observations confirmed this galaxy rotation problem. In the mid-1970s, the American astronomer Vera Rubin proposed a solution. If most of the mass in spiral galaxies consisted not of the kind of matter that we could see through telescopes, but instead of the same kind of unseen dark matter that Fritz Zwicky had proposed in 1933, then the observed non-Keplerian motions of spiral galaxies could make sense. Most astrophysicists today accept the existence of dark matter based on the evidence presented by Zwicky, Rubin, and others. Spiral galaxies are beautiful. Ancient structures believed to have formed in the early universe and continue to evolve today. Enshrouded in halos of mysterious dark matter and hosting million solar mass black holes in their cores, they are like enormous pinwheels in the cosmos, spinning along for billions of years on the virtual winds of the Big Bang. SETI. Are we alone in the solar system, the galaxy, or the universe? People have asked that question throughout and before recorded history, but only in the last century or so have we started to develop the means to find out. The 1931 discovery of natural sources of extraterrestrial radio waves from the galactic center and later from neutron stars and other high-energy objects provided a route to address the question because it became clear to astronomers that radio signals could travel vast distances across interstellar and intergalactic space. In 1959, the physicists Giuseppe Cocconi and Philip Morrison published a paper in Nature entitled "Searching for Interstellar Communications." Radio communication across vast galactic distances became a serious topic of scientific study. In that work, they described ways astronomers might search for radio signals transmitted by other civilizations. Radio astronomer Frank Drake almost immediately took up the challenge, using the 85-foot, 26-meter radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia, in 1960, to conduct the first dedicated search for non-natural radio transmissions from nearby sun-like stars. Drake's search was not successful, but it spurred what has now been a more than 50-year international observing campaign called the Search for Extraterrestrial Intelligence, SETI. Drake also developed a crude estimate of the potential number of civilizations in our galaxy, NC, the number of stars, NG, the fraction with planets, FP, the number of habitable planets, NHZ, the fraction of life, FL, the fraction with intelligent life, Fi, the fraction with technological civilizations, Fc, the lifetime of those civilizations, L. Known as the Drake equation, this yields estimates ranging from 1 Earth to potentially millions of intelligent civilizations in the Milky Way. Given recent discoveries of extremophile life forms on Earth and habitable extrasolar planets around other nearby stars, many SETI participants, now including the general public thanks to the internet, remain optimistic about the long-term potential to make contact. Of course, if we don't listen, we may never know. The first humans in space. The Soviet Union's successful launch of Sputnik 1 in 1957 marked the beginning of the space age and an epic geopolitical race for technological, military, and moral superiority with the United States. The Russians had launched the first animal into space, a dog named Laika on board Sputnik 2, and the US was launching monkeys and chimpanzees. But both governments knew that the next big victory in the space race could only be claimed by launching a person into space. Similar to the original Sputnik effort, the Soviet human spaceflight program, known as Vostok, relied on modifying existing intercontinental ballistic missile rockets to fit a small passenger capsule. The Soviet Air Force secretly screened about 20 pilots to select Senior Lieutenant Yuri Gagarin as the first cosmonaut, or space sailors in Russian. At the same time, the US human spaceflight program, called Project Mercury, was on a parallel track, modifying the Redstone missile to accommodate its small single-passenger capsule. They ultimately selected 7 Air Force, Navy, and Marine test pilots who instantly became celebrities, even before their flights. They chose Navy test pilot Alan Shepard to fly the first Mercury mission. Vostok and Mercury had early unmanned launch failures. Both teams had to demonstrate that their rockets would work with an empty capsule before government leaders authorized a human-piloted flight. Both teams were neck and neck in the race to launch a person first in early 1961. And once again, the Soviets scored an enormous international victory by successfully sending Gagarin into space first for one orbit of Earth in Vostok 1 on April 12, 1961. 3 weeks later, Shepard became the second person, and first American, to launch into space with his successful suborbital flight in the Freedom 7 capsule. The Russians had again taken the lead. However, shortly after Shepard's flight, America upped the ante when President John F. Kennedy, in an address to Congress, called for NASA to land a man on the moon before the decade was out. Radio telescope, Arecibo. Astronomers have known that increasing a telescope's sensitivity and resolution necessitates its size since Galileo and others used the first astronomical telescopes in the early 17th century. However, physical limitations on material strengths and the ability to grind and polish large glass lenses or silvered mirrors make it technically impossible to build useful single-lens telescopes larger than about 3 feet, 1 meter, in diameter, or single-mirror telescopes larger than about 16 feet, 5 meters in diameter. In radio astronomy, however, mirrors that reflect or transmit radio waves can be made from metal, just as antennas are. This allows for significantly larger sizes. In the late 1950s and early 1960s, a group of radio astronomers and atmospheric scientists at Cornell University realized that building a giant stationary radio telescope out of wire mesh inside natural bowl-shaped depressions was possible. They identified a suitably radio-quiet location in the mountains near Arecibo on the island of Puerto Rico. It is also conveniently located near the equator, enabling it to view most of the sky. In 1960, with the help of the Advanced Research Projects Agency, the US military's parallel agency to NASA, construction of the enormous semi-spherical dish and support structures for steerable radio transmitters and receivers hanging above the dish began. The Arecibo radio telescope became operational in the fall of 1963 and remains the largest single-dish telescope in the world. Arecibo has yielded numerous significant astronomical discoveries. Early in the telescope's operation, radar observations revealed Mercury's rotation rate and topography on the cloud-covered Venus surface. Arecibo astronomers discovered one of the first known pulsars, rapidly spinning neutron stars, in the heart of the Crab Nebula, and the first millisecond pulsar, which rotated around 500 to 1,000 times per second. Arecibo astronomers bounced the first radar waves off near-Earth asteroids to determine their size and shape, and the telescope is still the premier observatory on Earth for determining the orbits of potentially hazardous asteroids that could represent an impact threat to our planet. Quasars. Like astronomers working at visible light wavelengths, so-called optical astronomers, early radio astronomers were keen to survey the skies using their newly developed radio telescopes to identify the most interesting natural sources of radio waves. In addition to strong radio sources with well-identified optical counterparts, like the center of the Milky Way galaxy or the Crab Nebula supernova remnant of 1054, astronomers in the 1950s began discovering hundreds of strong radio sources with no corresponding optical counterparts. Many appeared very small in the sky, almost star-like, but not stars. Astronomers began calling them quasi-stellar objects, or quasars for short. In 1962, the brightest quasar known, called 3C273, passed behind the path of the Moon's limb on multiple occasions, allowing radio astronomers to determine its position with very high accuracy. Martin Schmidt, a Dutch-American astronomer, used this high-precision location data to search for and identify the quasar optically using the 200-inch, 5-meter Hale telescope at Mount Palomar, which had become the world's largest reflecting telescope since coming online in 1948. Schmidt took spectra of 3C273 and, in 1963, discovered that it was indeed not star-like at all, but rather showed Doppler-shifted emission lines from hydrogen, which suggested that it was both a great distance from us, following Hubble's law, and full of extremely high speed, about 16% the speed of light, ionized gas. Since then, scientists have discovered that quasars are the brightest objects in the observable universe. The quasar 3C273 is one of the closest to us, but is still 2.4 billion light-years away. This tells us that quasars are ancient features that were more common in the universe's early history. According to astronomers, quasars are the violent inner regions of ancient active galactic nuclei, where matter falls into black holes at the centers of quasar-host galaxies, releasing enormous amounts of gravitational energy. Sometimes a spiraling disk of material releases energy in intense jets of radiation perpendicular to the disk. The brightest quasars appear to point toward the source, where these luminous energy jets point almost directly toward us. Cosmic microwave background. Most cosmologists used Edwin Hubble's 1929 discovery of the expansion of space as evidence that the universe was smaller in the past, and that if you could go far enough back in time, about 13.7 billion years ago by the latest estimates, you would discover that the universe had sprung into being with a big bang from an extremely hot, dense, and small point. Not all astronomers, however, initially embraced the Big Bang theory. In 1948, for instance, an alternative model emerged, proposing that despite the expansion of space, the constant creation of new matter, primarily hydrogen, maintained density, the amount of matter per unit of volume, over time. Called the steady-state theory, this model described a universe with no beginning and no end, and, as strange as it seemed, it was consistent with the available astronomical data of the time. Cosmologists have devised methods to test the relationship between the Big Bang and steady-state models of the universe. For instance, the Big Bang model predicts that today's universe should still display a faint residual glow, characterized by a distinctive pattern from the early recombination era when electrons underwent deionization and space became transparent to photons. According to predictions, the temperature of that glow would be around 3 to 5 kelvins, just above absolute zero. This predicted amount or pattern was inconsistent with the steady-state model's background radiation. Radio astronomers knew that the radiation signal should be most detectable in the microwave part of the spectrum, around wavelengths of 1–2 millimeters, and the race was on to detect it. In 1964, astronomers Arno Penzias and Robert Wilson won the race when they detected unexplained and near-uniform background radiation, corresponding to a temperature near 3.5 kelvins. They won the 1978 Nobel Prize in Physics for their discovery at Bell Labs, where Carl Jansky had invented radio astronomy in 1931. Subsequent space satellite measurements revealed that the cosmic microwave background has a temperature of 2.725 kelvins, with very small fluctuations in matter and space that appear to be the seeds that eventually grew into stars and galaxies. Black holes. Even though they are among the strangest, most exotic, and perhaps most misunderstood objects in the universe, black holes can be thought of simply as collapsed stars. Part of their mysterious appeal comes from their fundamentally unobservable nature, and we can only learn about them by watching the strange and beautiful ways they modify and interact with their surroundings. Once a large enough star, perhaps 5 to 10 times the mass of our Sun, converts all its hydrogen to helium and other heavier elements, nuclear fusion reactions can no longer counterbalance gravitational forces, and the star collapses. The collapse eventually causes an enormous supernova explosion, which ejects much of the star's material into space. However, some of that explosive energy further compresses the dense remaining core of the star, which continues to contract, grow more dense, and radiate more energy. If the collapsed star's mass continues to grow, perhaps by stealing material from a companion star, at some point, not even light may be able to escape from the object's gravity. The region around the core would look like a black hole from the outside. The British astrophysicist Roger Penrose mathematically proved in 1965 that collapsing stars can form black holes, and that massive stars should shrink to an infinitely small point, known as a singularity. Weird stuff indeed. However, since gravity falls off as one moves away from such an object beyond some distance, called the event horizon, any light or other radiation related to the black hole can escape and be observed. The black hole's enormous gravitational and magnetic fields accelerate gas or dust to enormous velocities, resulting in much of this observed radiation. These areas are believed to form quasars. Einstein's theory of relativity predicts that many strange things happen near a black hole's event horizon, including time itself appearing to stand still as viewed by an observer from the outside. Unfortunately, since information can never escape from a black hole, it may never be possible to truly know what they are like up close. Hawking's extreme physics. Early to mid-20th century astronomers' research led to a detailed understanding of how stars work and the realization that they have finite lifetimes. Stars are born, follow a fairly common lifestyle, and then die, with all the details depending mostly on their mass. The most massive stars explode as supernovae, leaving behind highly dense stellar cores that can become neutron stars, pulsars, or, if massive enough, black holes. Many astrophysicists are interested in understanding these compact, high-energy objects because they and their environs provide places to study some of the most extreme physics in the universe. Among the most influential of these researchers is the British cosmologist Stephen W. Hawking, who began publishing papers about the physics of black holes while a Cambridge graduate student in 1965. He has also done important work refining theories of quantum gravity, wormholes, and the Big Bang. Hawking was particularly interested in studying singularities, the infinitely small and dense remains of the runaway collapse of massive stellar cores. He and his Cambridge colleague Roger Penrose each made critical discoveries about these strange objects, which, because of their super-high gravitational and magnetic fields, were excellent places to study Einstein's theory of general relativity and extreme examples of quantum mechanics. Hawking's theoretical studies have realized that singularities are possible and potentially abundant in the cosmos, from quasar-host galaxies to individual black hole stellar remnants. Indeed, Hawking pointed out that the Big Bang itself began as a singularity, so studying the origin and behavior of singularities provides insight into our universe's very origin. At the age of 21, Hawking suffered from a motor neuron disease associated with amyotrophic lateral sclerosis, ALS, leaving him paralyzed and dependent on a computer for communication. Notwithstanding an initially bleak prognosis, he persevered and became a leading theoretical physicist, inspirational best-selling author, and staunch advocate for scientific education and literacy among the general public. Venera 3 reaches Venus. Most media attention on the 1960s space race between the United States and the Soviet Union focused on the human spaceflight program and the quest to land the first astronauts on the moon. But the race also extended farther across the solar system. Following the success of the Luna 3 and Zond 3 lunar orbiters, their far-side photos, and the Ranger 7, 8, and 9 lunar impact probes between 1959 and 1965, both the Soviets and the Americans began to concentrate more of their robotic missions on studying the nearby planets, Venus and Mars. Venus, Earth, and Mars form a triad of generally similar terrestrial planets that, when studied in detail, reveal important differences in planetary surface and climate evolution. Telescopic observations revealed that clouds continuously shroud Venus's surface, with only radar observations from the Arecibo radio telescope in the early 1960s revealing some surface details. Mariner 2 became the first robotic probe to fly past Venus in 1962. But much about Venus remained unknown, including a basic consensus about the planet's surface temperature and atmospheric pressure. The Russians initiated the Venera robotic probe program to study Venus in more detail, using a series of flybys, orbiters, atmospheric probes, and landers. The Venera 1, 1961, and 2, 1965, Venus flyby missions failed before reaching the planet. But the Venera 3 mission did reach the planet and enter the atmosphere before losing radio contact with the Earth. Despite not returning any scientific data, the Venera 3 mission made history by becoming the first human artifact to crash into Venus on March 1, 1966. Persistence paid off for the Soviet space program, however. The follow-on missions of Venera 4, 5, and 6 in 1967-1969 were successful, with Venera 4 providing the first direct measurements of the chemistry, temperature, and pressure of the atmosphere of another planet, and Venera 5 and 6 providing more measurements of wind speeds, temperature, and pressure. These missions, and the successful 1967 US Mariner 5 mission flyby, revealed Venus to be a hellish world, with a surface pressure over 90 times that of Earth and surface temperatures above 840 degrees 450 degrees C. Pulsars. The astrophysicists Walter Baade and Fritz Zwicky proposed the concept of neutron stars, highly dense, compact stellar remnants from supernova explosions, back in 1933. However, it wasn't until 1965 that radio astronomers Anthony Hewish and Samuel Okoye discovered the first observational evidence for a neutron star, a powerful but very small source of intense radio energy coming from the center of the Crab Nebula, the explosive remains of the famous daytime star supernova of 1054. Hewish and colleagues at the University of Cambridge continued searching for new neutron stars and other radio sources. Just 2 years later, using the new, more sensitive 4-acre radio telescope west of Cambridge, Hewish's student Jocelyn Bell discovered the first rapidly pulsating radio star, pulsar, in the constellation Vulpecula, with a constant pulse rate of every 1.3373 seconds. Bell and Hewish considered the possibility that the pulsar's eerily regular radio signal might be a sign of extraterrestrial intelligence. They had jokingly named the source LGM-1 for Little Green Men 1. However, by 1968, they and other astronomers had developed a more plausible explanation, partly due to the discovery of a radio pulsar with a pulse rate of every 33 milliseconds in the neutron star at the center of the Crab Nebula. Researchers discovered that pulsars are rapidly spinning neutron stars with strong magnetic fields that beam some of their energy in specific directions, usually along or close to their rotation axis. When the spinning pulsar aligns its beamed electromagnetic radiation to sweep past the Earth, it can illuminate radio telescopes, akin to a lighthouse's spinning beacon. Since then, scientists have discovered thousands of pulsars, including several hundred millisecond pulsars like the one in the Crab Nebula. In 1992, scientists interpreted variations in the timing of signals from the pulsar PSR B.1257+12 as the result of planets orbiting the pulsar, marking the first examples of extrasolar planets. A high-resolution composite Hubble Space Telescope, RED, and Chandra X-ray Observatory, blue image of the central region of the Crab Nebula, Messier 1, a remnant from a supernova explosion in 1054. The central energy source is a pulsar, a rapidly rotating neutron star, with a 33 millisecond rotation period. Study of extremophils, astrobiology, studies the origin, evolution, and distribution of life and habitable environments in the universe. It is a distinct discipline because it has only one data point to justify its existence. So far, we know of only one example of life in the universe, that is, life on Earth, all of which is fundamentally similar, based on similar RNA, DNA, and other carbon-based organic molecules. However, searching for life elsewhere is more than just searching for complex life forms like ours. It is a search for other planetary environments suitable for our planet's most dominant form of life, bacteria and other simple life forms. Our planet, where we have significantly advanced our understanding of habitability over the past 50 years, is the best place to start searching for those conditions. In 1967, the American microbiologist Thomas Brock wrote a landmark paper describing heat-tolerant bacteria, hyperthermophiles, that flourished within hot springs at Yellowstone National Park. He challenged the prevailing wisdom that the chemistry of life requires moderate temperatures to operate. Brock's work helped spur the study of extremophiles, life forms that survive and even thrive in harsh environments. Since then, researchers have identified hyperthermophilic bacteria in extremely hot water near deep-sea hydrothermal vents, while psychrophiles thrive in temperatures close to or below freezing. Researchers have discovered that life forms persist in extremes of salinity, halophiles, acidity, acidophiles and alkaliphiles, high pressure, piezophiles, low humidity, xerophiles, and even high levels of UV or nuclear radiation, radioresistant. The message for astrobiologists from the history of life on our planet is clear. Life can thrive in an enormous range of environments. Thus, searching for evidence of past or present extremophiles or their habitable environments in extreme places such as Mars, the deep oceans of Europa and Ganymede, or the frigid, organic-rich surface of Titan, is not as crazy an idea as it used to be. First on the Moon. After Yuri Gagarin became the first human in space, the race between the United States and the Soviet Union quickly became focused on the next big milestone: landing astronauts on the Moon and bringing them safely back to Earth. The Soviet Union reoriented the Vostok program to focus on the larger rockets and landing systems required for a lunar landing and return. The challenge in America was to beat the Russians and meet slain President John F. Kennedy's 1961 goal of doing it before this decade is out. Between 1961 and 1969, the US conducted a series of increasingly advanced missions, beginning with the Mercury single astronaut flights, followed by the Gemini two-person Earth orbital docking and rendezvous flights, and culminating in the three-person Apollo missions to the Moon. Apollo 8 achieved an important first in 1968 by sending the first humans to orbit the Moon and view the whole Earth and the lunar far side firsthand. The feat was repeated in early 1969 with the flight of Apollo 10, a full dress rehearsal of a lunar landing that sent astronauts to within 10 miles, 16 kilometers, of the lunar surface before returning home. Meanwhile, the Russians continued progressing in their secret lunar cosmonaut program. Several catastrophic unmanned launch failures in 1969 set their program back significantly, opening the door for an American victory. That victory came on July 20, 1969, with the world watching as astronauts Neil A. Armstrong and Edwin G. Buzz Aldrin became the first humans to land, walk, and work on the Moon. Armstrong and Aldrin landed on the ancient volcanic lava flows of the Mare Tranquillitatis, Sea of Tranquility, impact basin. Age dating of the samples showed them to be 3.6–3.9 billion years old, and spent about 2.5 hours collecting samples and exploring the terrain. After less than a day, they took off and rejoined Command Module pilot Michael A. Collins back in lunar orbit for the 3-day trip home as world heroes. Second on the Moon. Just 4 months after the successful voyage of Apollo 11, NASA astronauts were once again walking on the Moon. On November 19, 1969, astronauts Alan Bean and Charles Pete Conrad targeted Intrepid's lunar module toward a precision landing near NASA's 1967 Surveyor 3 robotic lander, while Command Module pilot Richard Gordon circled high above. Conrad and Bean successfully demonstrated pinpoint landing accuracy by setting their spacecraft down within 600 feet, 180 meters, of Surveyor 3. Such accurate landings would be critical to future Apollo missions. Conrad and Bean spent about 32 hours on the Moon, nearly a quarter of which was spent outside, taking samples and setting up experiments in the flat lava plains of Oceanus Procellarum, Ocean of Storms. Their longest excursion consisted of a walk to the Surveyor 3 probe, where they took off some pieces and instruments to return to the Earth. Surveyor 3 had been sitting on the lunar surface for over 3 years. The returned parts provided detailed information on the long-term effects of vacuum, intense sunlight, and micrometeorite impacts on lunar surface equipment. Amazingly, some dormant bacteria on some of the surfaces somehow made the trip to the Moon and back, and some tests showed they still remained viable, even after 3 years in the Moon's harsh vacuum and ultraviolet UV environment. The longer duration on the surface let the Apollo 12 astronauts collect about 75 pounds, 34 kilograms, of lunar samples, compared to 48 pounds, 22 kilograms, from Apollo 11, including soils, small rocks, pieces of boulders, and impact crater deposits. Scientists analyzing those samples discovered that the Procellarum Basin's dark volcanic rocks are much younger, 3.1 to 3.3 billion years old, than those returned by the Apollo 11 crew from the Tranquillitatis Basin, 3.6–3.9 billion years old, indicating that the Moon was volcanically active for at least the first 1.3–1.5 billion years of its history. The rocks in Apollo 12 samples are also chemically different from those in Tranquillitatis. They include dark, glassy rocks and the first samples of breccia, a new type of lunar rock made up of broken rocks that have been melted and joined together by impacts. Astronomy goes digital. Astronomy was a visual craft for millennia, with practitioners relying on their keen eyesight and excellent night vision to find and characterize celestial objects. Even 200 years after the invention of the telescope, the human eye was still the only detector available to astronomers. The introduction of astrophotography in 1839 provided astronomers with more sensitive light detection devices, first silvered glass plates, and then sensitized photographic films. Although it was a huge advancement in data archiving and observational repeatability, photography only improved the ability to capture light from fainter astronomical sources. During World War II, the development of radar and navigation electronics for aircraft and weapons made a gigantic advance in astronomical detector sensitivity possible. These advancements led to the invention of the first electronic switches, diodes, around 1939, and the first electronic amplifiers, transistors, in 1947. These devices relied on the properties of certain elements, such as silicon or germanium, that are not quite conductors, as metals are, and not quite insulators. Such semiconductors are materials that generally don't conduct electricity, but that can be coerced by applying the right voltage or, in some cases, just by shining a light on them to conduct electricity. The critical semiconductor advance for astronomers, and ultimately for digital camera and cell phone users, came in 1969, when the American physicists Willard Boyle and George Smith at AT&T Bell Labs created an array of semiconductors that converted incoming light, photons, into analog voltage signals that could then be stored, amplified, and converted into digital numbers. We refer to the invention as a charge-coupled device, CCD, because the incident light on the array is coupled to the generated electrical charge. Astronomers instantly fell in love with CCDs as they became available in the 1970s and 1980s. Their output signal is linearly proportional to the brightness of the object shining on them, and they are 100 times more sensitive than photographic film. CCD cameras are now standard equipment for astronomical telescopes and space missions. Organic molecules in Murchison meteorite. One of the motivators of space exploration is the search for life beyond our home planet. But how do we conduct such a search? One way is to search for the chemical elements that occur in life on our planet. Elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements, however, occur in many places and environments throughout the cosmos, such as the insides of stars, that are unlikely to be conducive to life. A more effective strategy might be to search not for specific elements, but for certain arrangements, molecules, that could reveal evidence for life's basic chemistry. Life on Earth is based on organic molecules. Some organic molecules are simple, like methane, CH4, methanol, CH3OH, or formaldehyde, H2CO, and others are much more complex, like proteins, amino acids, ribonucleic acid, RNA, and deoxyribonucleic acid, DNA. Over the last half-century, astronomers have identified many simple organic molecules in dense interstellar clouds, comet tails, icy moons and rings of the outer solar system, and the atmospheres of Titan and the giant planets. On September 28, 1969, a meteor and fireball streaked across the daytime sky and crashed to the ground near the town of Murchison in Victoria, Australia. The area yielded more than 220 pounds, 100 kilograms, of meteorite samples. After detailed analysis of the samples, scientists announced in 1970 that the meteorite, from the most ancient and primitive class of meteorites, known as carbonaceous chondrites, contained some common amino acids. Later studies found that the Murchison meteorite contained more than 70 kinds of amino acids, plus many other simple and complex organic molecules. Life, as we know it, requires liquid water, sources of energy like heat or sunlight, and abundant complex organic molecules. The discovery of amino acids in Murchison and other meteorites supports the idea that molecules critical to life can form non-biologically in environments such as a solar nebula disk, comet, or planetesimal. Life may or may not be abundant in the cosmos, but it appears everywhere. Venera 7 lands on Venus. Despite the failure of their lunar cosmonaut program in 1969, the Soviet Union continued to achieve remarkable successes with their robotic probes on the planets. The Venera 3-6 missions to Venus, undertaken from 1966 through 1969, did not survive to the surface, but still, they provided enough new data on the planet's atmosphere to enable mission controllers to design subsequent missions to withstand the harsh conditions. Success came with the flight of Venera 7, which, on December 15, 1970, became the first human-made object to land and return data from another planet's surface. Venera 7 floated down through the atmosphere on a parachute for 35 minutes before landing, after which it returned data for another 23 minutes. During that time, the lander relayed temperature data showing the surface to be at about 870 degrees 465 degrees C, with a surface pressure inferred to be about 90 times Earth's surface pressure. Under such scorching and crushing conditions, it's a wonder the lander survived. The success of Venera 7 set the stage for an incredible string of successful follow-on Soviet Venera landers, orbiters, and atmospheric probes between 1972 and 1985, the most ambitious long-term program of Venus robotic exploration ever conducted. Geochemical measurements of the planet's surface composition, similar to basaltic volcanic rock compositions found in Hawaii and Iceland. The first pictures of the rocky surface taken when sunlight broke through the thick clouds, and the first large-scale maps of mountains, ridges, plains, and other tectonic and volcanic features made with radar imaging from the Venera 15 and 16 orbiters were some of the most important discoveries. Besides the hellish surface conditions, the Venera probes also helped planetary scientists discover that the wind speeds in Venus's middle and upper atmosphere exceed 220 miles, 100 meters per hour, which is much faster than the planet itself rotates. One Venus day is about 243 Earth days. The cause of this super-rotation of Venus's atmosphere is unknown, but it is one focus of ongoing and planned future missions to study Earth's so-called twin, Venus. Lunar robotic sample return. The Soviet Union's robotic space exploration program in the 1960s and 1970s achieved a string of scientifically important firsts in missions to the Moon, Venus, and Mars. Among the most important and technologically impressive were Luna 16, Luna 20, and Luna 24, the world's first robotic sample return missions. These small, automatic stations launched from Earth on a 5-day cruise to the Moon. After a 3-day return trip and parachute landing, they autonomously performed a soft landing on the lunar surface, drilled shallow holes into the surface to collect lunar samples, and then launched small sample return capsules back to Earth. Luna 16, launched in September 1970, was the first of these autonomous sample collection and return missions, returning 3.5 ounces, 100 grams, of lunar soil and rock fragments from the dark lava plains of the Mare Fecunditatis impact basin. Luna 20 repeated the feat in 1972, collecting 2 ounces, 55 grams, of samples from a bright highlands region, also near Mare Fecunditatis. And Luna 24 did it again in 1976, returning 6 ounces, 170 grams, of samples from Mare Crisium, a lava-filled impact basin near the Moon's eastern limb. The lunar specimens complement the much larger Apollo return sample collection because they include different and unique lunar surface compositions and mineralogies. Combined, the Apollo and lunar samples provide the fundamental information that drives current theories for the origin and evolution of the Moon, including the key pieces of supporting evidence for the giant impact model for the formation of the Moon. The Soviet lunar sample return missions were the most complex robotic missions yet attempted. Since then, scientists have conducted other sample return missions to retrieve pieces of a comet tail, the Stardust mission, solar wind particles, the Genesis mission, and tiny fragments of a near-Earth asteroid, the Hayabusa mission. Still, the lunar sample return missions remain among the most complex planetary exploration missions ever conducted, an achievement made even more remarkable because they relied on 1960s technology. Proposals and plans for future robotic sample return missions from other regions of the Moon, Mars, Venus, and near-Earth asteroids persist. The first, Mars orbiters. For 50 years, robotic planetary exploration has followed a progression of more daring and technologically challenging space missions. Initially, the goals were to learn how to navigate remote probes in space and make them fly by or fly into the Moon and other planets, sending back data in pictures and other measurements. The next logical step is to establish orbiting satellites around other worlds, to spend time learning about an alien environment and mapping an extraterrestrial surface or atmosphere. NASA's Mariner 9 space probe was the first satellite to leap to the next level of planetary exploration and orbit another planet. Mariner 9 arrived at Mars in November 1971, during the throes of what astronomers had noticed was a planet-wide dust storm. While the spacecraft's spectrometers were taking data on dust properties and atmospheric temperatures, the probe's television cameras were seeing a bland, dusty cue ball of a world, primarily with a few dark spots poking out of the dust. After almost an Earth year in orbit, the dust had cleared enough for the mission to map the planet's surface in unprecedented detail. The Mars revealed in the Mariner 9 images was a geologic wonderland of giant, towering volcanoes, the dark spots seen during the dust storm. Enormous tectonically formed canyon systems, ancient river channels, and countless impact craters. The impact crater-dominated glimpse of Mars from the previous Mariner flyby missions in 1965 and 1969 was a stark contrast. The Soviet Union also took advantage of the opportunity to launch 2 Mars orbiters of their own in 1971, called Mars 2 and Mars 3. Both went into orbit a few weeks after Mariner 9 and returned useful scientific information about the atmosphere and surface once the dust had cleared. Both also deployed small landers and mini-rovers to explore the surface. Though neither lander was successful, they became the first human artifacts to impact the surface of Mars. Gamma-ray bursts. Physicists studying the spontaneous decay of radioactive elements around the turn of the 20th century recognized 3 kinds of particles or radiation emitted by radioactive elements, such as uranium and radium. When some elements decayed, they emitted helium nuclei, alpha particles. Others emitted higher energy electrons or positrons, beta particles. And when physicists discovered a third, even higher energy form in still other radioactive decay events, they named those particles gamma rays. Like X-rays, gamma rays are a form of electromagnetic radiation of very high energy, very short wavelength. Physicists of the later 20th century discovered that electrons surrounding an atom undergoing radioactive decay emit X-rays, while the atomic nucleus emits higher energy gamma rays. Physicists predicted and observed the creation of gamma rays during nuclear fusion bomb tests because the nucleus generates them. Indeed, in the 1960s, the United States and the Soviet Union deployed gamma ray detectors in space to confirm adherence to the terms of the 1963 Partial Test Ban Treaty. The US satellites were part of the military's Vela series, which could detect gamma rays from anywhere in space. Surprisingly, beginning in 1967, the satellites began to occasionally, a few times a year, detect mysterious short gamma ray bursts, GRBs, lasting from milliseconds to several minutes, that were later determined to be coming from random directions in deep space. The military declassified the data and alerted civilian scientists to the phenomenon in 1973. GRBs puzzled astrophysicists for decades, because their energies were far higher than gamma-ray events produced by radioactive decay or stellar nuclear fusion reactions. The detailed nature of GRBs would remain mysterious until space telescope observations from NASA's Compton Gamma Ray Observatory in the 1990s revealed their origin. GRBs appear to be formed by supernova explosions, the collapse of massive stars, or merging pairs of colliding neutron stars. Like pulsars, the exploding star sends jets of highly focused energy toward Earth, resulting in GRBs. Gamma-ray bursts appear to be the most violent and energetic events in the cosmos. Pioneer 10 at Jupiter. Robotic exploration of the solar system primarily focused on the inner solar system, specifically the Moon, Venus, and Mars, until the 1970s. Planetary scientists realized that understanding the solar system would eventually require detailed, up-close exploration of the outer solar system. Pilots 10 and 11 were born with missions. Pioneer 10, launched on March 2, 1972, and its twin spacecraft Pioneer 11, launched on April 4, 1973, were nuclear-powered probes designed to study the properties of interplanetary space beyond Mars. Their findings revealed that dust and micrometers in the main asteroid belt do not significantly threaten future spacecraft. During the Jupiter flyby, Pioneer 10 got to within 125,000 miles, 200,000 kilometers, of the cloud tops and took photographs, revealing great detail in the planet's atmosphere. Pioneer 10 maintained its interstellar mission beyond Jupiter for 30 more years, sending its final signals in 2003. Pioneer 10, one of only 5 spacecraft accelerated to escape velocity from our solar system, is still traveling at more than 7.5 miles, 12 kilometers per second, and is now more than 120 astronomical units, AU, from the Sun. They also launched 3 others in the 1970s, generally heading in the opposite direction. Pioneer 11, last heard from in 1995, is currently at more than 99 AU and headed toward the center of the Milky Way. Voyager 2 is at more than 116 AU and still sends back occasional fields and particle data from deep space. However, Voyager 1 holds the record at more than 141 AU and still transmits scientific data as it speeds outward at more than 10.5 miles per second, 17 kilometers per second. The 5th mission to achieve escape velocity from the solar system is the NASA New Horizons probe, launched in 2006. It flew past Pluto in the summer of 2015 and is now more than 40 AU from the Sun. Voyager 1 was the first of these robotic emissaries from Earth to leave the solar system. In 2012, the spacecraft crossed the heliopause, the boundary where the Sun's faint solar wind merges into the general background of interstellar space. Vikings on Mars. The short but successful mission of Mariner 9 in 1971 formed the basis of a new NASA project to explore Mars in greater detail than ever before. The Viking project aimed to launch 2 orbiters and 2 landers to Mars, significantly enhancing our understanding of the red planet's surface, atmosphere, and potential as a past or present home for life. Launched in August and September 1975, the Viking 1 and Viking 2 probes arrived at Mars in June and August 1976, respectively. During the first month in orbit, the Viking 1 team took photos of the surface, searched for a safe place to deploy the nuclear-powered lander, and eventually chose a flat region known as Chryse Planitia, Plains of Gold. On July 20, 1976, Viking Lander 1 safely set down, marking the first successful mission to the surface of Mars. Viking Lander 2 successfully landed a few months later, about 3,000 miles, 4,800 kilometers away, in flat and rocky Utopia Planitia. With a cost of about $1 billion, Project Viking was the most complex and expensive Mars mission attempted up to that time, and it was a phenomenal success. The orbiters provided detailed global maps of the surface, down to hundreds of meters or better resolution, revealing ancient water-carved valley networks, finely layered polar cap deposits, and details of the younger volcanic mountains and giant canyons discovered by Mariner 9. The idea that early Mars may have been warmer, wetter, and more Earth-like was based on Viking orbiter data. The landers also developed a lasting paradigm for Mars studies. Meteorology experiments provided detailed information on the surface conditions and weather patterns that are hostile to humans. Most importantly, however, the landers' search for evidence of organic molecules, potential indicators of life, or at least of habitable environments, came up empty. However, the setback for astrobiologists was temporary. It helped refine new experiments for future missions. Voyager Grand Tour begins. Mission planners and celestial dynamics experts contemplating robotic missions to the outer solar system in the late 1960s and early 1970s realized that a fortuitous alignment of Jupiter, Saturn, Uranus, and Neptune could potentially allow a single probe to use gravity assists to fly past all 4 giant planets in the 1970s and 1980s. NASA researchers were greatly excited by this historic Grand Tour concept, which they eventually implemented in a new pair of missions called Voyager. Launched on August 20, 1977, Voyager 2 would reach Jupiter in mid-1979, Saturn in mid-1981, Uranus in early 1986, and Neptune in mid-1989. Voyager 1's launch was on September 5, 1977, on a faster trajectory that would get it to Jupiter in early 1979 and Saturn in late 1980. Voyager 1's tour included only Jupiter and Saturn flybys because the desire to perform a close flyby of Saturn's large, thick atmosphere moon Titan required a course correction, making it impossible to subsequently encounter Uranus and Neptune. The missions of Voyager 1 and Voyager 2 are among the most exciting and successful adventures in the history of space exploration, or any other kind of exploration for that matter. The probes enabled scientists to make new discoveries about the giant planets' atmospheres, magnetic fields, ring systems, and their planet-sized moons, Io, Europa, Ganymede, Callisto, Titan, and Triton, plus many smaller moons. Voyager discoveries enabled even more discoveries at Jupiter and Saturn by the follow-on Galileo and Cassini orbiters, respectively, and provided the data needed for eventual orbital missions to Uranus and Neptune sometime in the future. Like the pioneers, each Voyager also has a message in a bottle, a golden record containing encoded images, voices, and music, a cosmic time capsule bearing greetings from planet Earth to whoever finds it in the far future. Uranian rings. Discovered. In 1659, the Dutch astronomer Christian Huygens observed and explained Saturn's rings as a thin disk of material circling the 6th planet. Saturn appeared to be the only planet with a ring system until 1789, when, shortly after discovering Uranus, the English astronomer William Herschel thought he detected a faint ring around that planet as well. However, subsequent visual and photographic observations of Uranus couldn't verify Herschel's claim. Nearly 200 years later, on March 10, 1977, the American team of planetary scientists James Elliott, Ted Dunham, and Douglas Mink was preparing to observe Uranus pass in front of a relatively bright star, an eclipse of sorts known as an occultation. To ensure that they were in the precise location to catch the rare occultation, the team observed the event from the Kuiper Airborne Observatory, a telescope mounted in a NASA C-141A jet that flew missions in the stratosphere above most of our atmosphere's clouds and water vapor. The occultation yielded an exciting surprise. Uranus eclipsed the star 5 times, causing its brightness to drop dramatically. Then, just after the star re-emerged from the eclipse, it happened 5 more times. Elliott and his team's analysis revealed that the starlight drops occurred at the same radial distance from Uranus on either side of the planet. They had discovered a faint set of narrow rings, meaning that the 7th planet had become the second known planet with rings. Follow-up observations revealed 4 more narrow rings around Uranus, bringing the total to 9. Astronomers using the Hubble Space Telescope discovered two more rings during Voyager 2's 1986 flyby, revealing that the rings are extremely dark, likely made of centimeter to meter-size icy blocks darkened by interactions between Uranus's magnetic field and icy organic molecules. Later, Voyager data revealed faint rings around Jupiter and Neptune, confirming that all the giant planets in our solar system, not just Saturn, are ring worlds. Charon. At nearly 40 times farther from the Sun than Earth, Pluto was a challenging object to observe decades after its discovery by Clyde Tombaugh in 1930. Nonetheless, astronomers continued to observe Pluto to learn more about its origin and properties. Astronomers conducted many of these observations from telescopes at the Lowell Observatory in Flagstaff, Arizona, the site of Pluto's discovery. While analyzing a series of such observations in June 1978, Lowell astronomer James W. Christie noticed a bulge in some of Pluto's photographs. According to Christie, the bulge moved around Pluto's main image. After further analysis, he and his colleague Robert S. Harrington published their discovery of a satellite orbiting Pluto. Christie named the moon Charon in honor of his wife, Charlene, or Shah, and after the mythological Greek ferryman of the dead, which is why we pronounce the name Sharon, not Charon. Charon is quite large, 750 miles, 1207 kilometers in diameter, about half of Pluto's diameter, making Pluto-Charon more like a double planet system. Charon also turned out to have a surface dominated by water ice and possibly small amounts of hydrated ammonia, a combination quite different from Pluto's surface, which is dominated by nitrogen and methane ice. Observations of Pluto and Charon by the Hubble Space Telescope 2005 revealed another surprise: more moons. In 2011 and 2012, the Hubble Space Telescope discovered two additional but much smaller satellites orbiting the Pluto-Charon system's center of mass, Nix and Hydra, after other Greco-Roman mythological figures. When the NASA New Horizons probe flew past them in July 2015, excitement mounted about what these distant worlds looked like. Active volcanoes on Io. When Pioneer 10 flew by Jupiter in 1973, the probe took spectacular images of the giant planet, but was not able to get very good views of Jupiter's large satellites, Io, Europa, Ganymede, and Callisto, discovered by Galileo back in 1610. The Voyager 1 probe that flew by Jupiter in March 1979 contained a much more sophisticated and higher resolution camera system. However, its flyby trajectory would take it closer to the planet and its large moons. The Voyager 1 encounter with Jupiter revealed many surprises, perhaps the biggest of which was the discovery of active volcanic plumes and lava flows on Jupiter's innermost moon, Io. Initially visible in silhouette in distant images, more than 400 active volcanoes cover the surface of Io in high-resolution, close-approach views. Io's volcanoes ooze out fresh, molten, rocky lava flows tens to hundreds of miles long, often colored by the presence of molten sulfur at a range of temperatures, and they sometimes erupt explosively, hurling an umbrella-shaped cloud of ash and rocky debris hundreds of miles out into space. The images from Voyager 1 and then Voyager 2 revealed that Io is the most volcanically active world in the solar system. On March 8, 1979, scientists took a discovery photo of volcanic plumes erupting on Io. But why? Io, Europa, and Ganymede orbit Jupiter in a 4-2.1 pattern called orbital Laplace resonance, which causes the moons to occasionally tug on each other gravitationally and make them wobble a little in slightly eccentric orbits. On the other hand, Jupiter's gravity tries to lock the moons into synchronous rotation, with the same side always facing the planet, like Earth's moon. The result is that strong tidal forces constantly squeeze and stretch the moons, especially the innermost Io, and the friction from all that squeezing heats their interiors. Tidal heating has completely melted it, boiling off all its water and other ices and causing global-scale volcanic eruptions that continually resurface the satellite and spew sulfur and dust into a giant donut-shaped disk around Jupiter. It is a tortured little world, turned inside out by relentless tidal forces. Jovian rings. The first space probes to encounter Jupiter, Pioneer 10 and 11, made detailed measurements of the planet's magnetic field and energetic particle environment as they sped past in 1973 and 1974. The data showed some unexplained variations in protons and electrons in Jupiter's equatorial plane near the orbit of Amalthea and the other inner moons, suggesting that something, perhaps a ring, was absorbing particles at those distances from the planet. Alerted by this enigma, mission planners for the Voyager 1 flyby of Jupiter in March 1979 designed special observations to take long-exposure photos of the region. To the team's delight, the photos captured the tip of a narrow ring system orbiting Jupiter, making it the third known giant planet with rings. The Voyager 2 probe took more views of Jupiter's ring system during its flyby in July 1979. More detailed pictures taken by the NASA Galileo Jupiter Orbiter and the Cassini and New Horizons missions during their flybys of Jupiter showed that the ring system has four main parts. The donut-shaped halo ring is closest to the planet. The main ring is bright and thin, 19,186 miles, 3,300 kilometers wide. The two diffuse gossamer rings are farther away and connected to the small moons Amalthea and Thebe. Unlike the rings around Saturn and Uranus, Jupiter's rings are dusty rather than icy. Comet or asteroid impacts appear to have blasted dust and small rocky particles off the moons Metis and Adrastea, forming the main and halo rings. Dust-sized grains blast off Amalthea and Thebe, forming the gossamer rings. Bands and other structures indicate that small embedded moonlets, or clumps of ring material, also supply and shape the rings. Jupiter's rings must be young and constantly replenished with new impacts, as one of the inner moons should only eject dust after a lifespan of about 1,000 years. The spacecraft created this Galileo Jupiter Orbiter mosaic of Jupiter's ring system, viewed edge-on and facing the Sun as it passed through Jupiter's shadow behind the planet. An ocean on Europa. Since Galileo discovered it in 1610, little has been known about Jupiter's second large satellite, Europa. We only know that Europa locked into a 4.2 EO Europa Ganymede orbital resonance, making it likely to experience interesting tidal forces. Telescope spectroscopy revealed that Europa has a bright, water-ice-covered surface. Regarding the detailed nature of Europa's surface, the slate was almost completely blank when the Voyager 1 and 2 probes made the first detailed reconnaissance of Jupiter's system. Voyager's discoveries at Europa were good. The planet-sized moon, only slightly smaller than Mercury, turned out to have one of the smoothest surfaces in the solar system. However, a dense and intersecting network of cracks and low ridges covers that smooth surface, seemingly dividing it into icy plates that move relative to each other. This was one of the first clues that the surface is a relatively thin, tectonically active shell of ice floating on a thick layer of liquid water, an ocean, in the subsurface. Other clues that Europa is an ocean world come from the observation that there are few impact craters on the surface, suggesting that it is geologically young and actively resurfacing itself. The NASA Galileo Jupiter Orbiter enabled a much more detailed study of Europa during its mission from 1995 to 2003. More evidence for the presence of a deep ocean came from Galileo spectrometer observations of salty mineral deposits within some of the cracks and fractures, the kind of mineral deposits that would form from the evaporation of salty ocean water. Galileo magnetic field data also revealed that Europa's subsurface is electrically conductive, another indicator of salty ocean water beneath the icy crust. The available data so far are consistent with Europa having a deep, 60-mile, 100-kilometer global ocean underneath a relatively thin, 6 to 20-mile, 10 to 30 kilometer, icy shell. But direct proof of that ocean must await future missions that will orbit or land on, and possibly drill through, the European crust. In the meantime, astrobiologists are excited about the prospects for Europa as a potential life abode. With energy from tidal heating by Jupiter, organic molecules from a steady rain of comets and asteroids, and abundant liquid water, we may one day discover that Europa's ocean is a habitable, or perhaps even inhabited, environment. Gravitational lensing. The curvature of space and time near extremely massive objects is a fundamental feature of physicist Albert Einstein's early 20th century theory of general relativity. Einstein and others predicted that due to the curvature of space-time, the gravitational field of massive foreground objects would bend light from distant objects. Arthur Stanley Eddington, a British astrophysicist, confirmed the prediction in 1919 when he noticed that stars observed near the Sun during a solar eclipse were slightly out of position. Einstein continued to study this effect in the 1930s, and he and others, including the Swiss-American astronomer Fritz Zwicky, speculated that more massive objects, such as galaxies and clusters of galaxies, could bend and amplify light from distant objects almost as a lens bends and magnifies normal light. However, it took many decades for astronomers to find observational evidence of such gravitational lensing. In 1979, astronomers at the Kitt Peak National Observatory in Arizona discovered the first example of what appeared to be twin quasars, two active galactic nuclei very close to each other in the sky. A foreground galaxy's strong gravitational field bent and split the light of the two quasars into two parts. Since then, researchers have discovered numerous additional examples of gravitational lensing, suggesting three possible mechanisms for the effect to occur. Strong lensing occurs when distinct, multiple, or partial, usually arc-like images are formed. Weak lensing has been detectable by observing small and subtle shifts in star or galaxy positions over large regions. In microlensing events, the gravitational lensing effect of a large foreground mass, such as another star or galaxy, temporarily amplifies the brightness of random distant stars, or even planets. Initially, researchers discovered and studied gravitational lenses as accidental, serendipitous events. However, scientists have intentionally conducted several astronomical surveys to search for gravitational lensing events. These surveys aim to obtain unique measurements of the properties of distant galaxies that would not be visible without the lens amplification, as well as the properties, such as mass, of the lensing galaxies and clusters themselves. Pioneer 11 at Saturn. Launched in 1972 and 1973, the Pioneer 10 and 11 missions aimed to conduct the first reconnaissance of the outer solar system and beyond. Pioneer 10 first encountered Jupiter in 1973, setting the stage for Pioneer 11's flyby of that giant planet in 1974-1975. However, unlike Pioneer 10, Pioneer 11 was on a trajectory that could harness Jupiter's gravity to propel it toward its first ever encounter with Saturn in 1979. The Pioneer 11 encounter with Saturn was a great success, with the probe passing within about 13,000 miles, 21,000 kilometers, of Saturn's cloud tops on September 1, 1979. The mission carried cameras, magnetic field and charge particle instruments, cosmic dust particle and radiation counters, and other scientific instruments that provided planetary scientists with their first views of the environment at and around the ringed planet. In a way, the Pioneer missions were pathfinders for the more ambitious Voyager probes into the outer solar system. For example, during the Saturn flyby, Pioneer 11 traveled through Saturn's ring plane to determine if small dusty or icy ring particles might threaten the spacecraft. They did not, thus enabling mission planners to direct Voyager 2 through the same region of the rings to get it on a trajectory that would allow subsequent encounters with Uranus and Neptune. Pioneer 11 data also yielded other discoveries at Saturn, such as the observation of the large atmosphere-bearing moon Titan's extremely low temperature, 90 kelvins, perhaps too cold for life. The discovery and near collision with of a new small moon and an additional ring, and detailed mapping of Saturn's magnetic field, a large charged particle structure similar in some ways to Jupiter's magnetic field. Like Pioneer 10, Pioneer 11 is on an escape trajectory from our solar system. It is now more than 83 astronomical units away from the Sun, heading toward the center of the Milky Way galaxy. The spacecraft lost contact with the probe in late 1995, but it still carries a plaque similar to Pioneer 10's, which will serve as an informative greeting for any future galactic neighbors who discover the probe. Cosmos, a personal voyage. Astronomy and space exploration are interesting and exciting topics, yet throughout recent history, scientists have yet to be compelled or encouraged to share their discoveries, or, pointedly, their failures, with the public. It was enough to publish their results in books or academic journals, or to present their findings at scientific conferences. Many even appeared arrogant about their work. The public wouldn't understand, so why tell them? Even in the 1960s and 1970s, when the media coverage of the Apollo missions heightened the huge public interest and international appeal of space exploration, it remained challenging for average folks to keep up with the latest observations and discoveries. In the United States, the three main broadcast TV networks aired mostly entertainment and news shows, and a fourth, the Public Broadcasting Service, PBS, aired a few good general interest science shows, but nothing focusing on space. In 1980, a charismatic and thought-provoking American astronomer named Carl Sagan hosted a new television series focusing specifically on astronomy and space exploration. Cosmos. A Personal Voyage became a smash hit. With an audience of more than 500 million people, it was the world's most watched PBS series. Through Cosmos, Sagan enthusiastically and educationally conversed with the public about the latest observations and theories concerning some of the biggest questions we ponder. What is going on up there? Where did it all come from? Why are we here? Are we alone? Sadly, Sagan met significant resistance from many of his scientific contemporaries for his tireless work popularizing the value of science and space exploration. According to reports, other scientists' petty jealousies denied him membership in the National Academy of Sciences. However, a new generation of astronomers and planetary scientists, many of whom grew up watching Cosmos, have embraced Sagan's ideals and legacy. Members of the Planetary Society, a public space advocacy organization he helped found in 1980, have promoted these ideals worldwide, and the scientific community now views them as essential to public communication and understanding of science in our modern world. Voyager-Saturn encounters. The Pioneer 11 robotic probe flyby of Saturn in 1979 served as a preliminary study for the NASA Voyager 1 and Voyager 2 probes, which launched in 1977, for an even more ambitious and detailed study of the planet's atmosphere, moons, rings, and magnetic field. Voyager 1 flew past Saturn in November 1980, and Voyager 2 followed closely behind in August 1981. The Voyager-Saturn encounters dramatically increased our knowledge about the diverse bodies and processes in the Saturn system. High-resolution imaging revealed details about the impact cratering record, composition, and geologic histories of the large icy moons Iapetus, Rhea, Tethys, Dione, Enceladus, Mimas, and Hyperion. The Voyager images revealed 7 small new moons of Saturn, several embedded in a much more spectacularly complex ring system than previously thought. We discovered that Saturn's rings consist of thousands of individual rings and ringlets, separated by thin gaps and kept organized by the gravity of several shepherd moons that co-orbit in the ring system. Voyager data confirmed the telescopic and Pioneer 11 discoveries that Saturn's largest moon, Titan, has a thick and hazy atmosphere. Titan's atmosphere has more than 50% higher surface pressure than Earth's, making it the only moon in the solar system with a thick atmosphere primarily composed of nitrogen. Small amounts of methane, ethane, propane, and other organic molecules, some predicted to exist as surface liquids at Titan's very low temperature, contributed to the orangish color of Titan's haze. However, Voyager's cameras could not penetrate Titan's haze to view the surface. Those discoveries would come some 15 years later, during the Cassini-Saturn orbiter and Huygens Titan lander missions. Voyager 1's planetary exploration mission ended at Saturn. We diverted the probe's trajectory from its Grand Tour path, which included a potential flyby of Pluto in the late 1980s, to bring it close enough to Titan for a detailed study of its early Earth-like atmosphere. Voyager 1 still operates some 120 astronomical units from the Sun, making it the most distant object humans have ever sent into the cosmos. Space Shuttle. The dream of human spaceflight, as rocketry pioneers Konstantin Tsiolkovsky and Robert Goddard first envisioned, has never been about one-way trips into space. Rather, we truly realize the full impact of people voyaging beyond our planet when they return home and share their adventure stories, scientific findings, and samples with the rest of us. But to get people, or payloads, to and from space requires the rocket to carry return capsules, parachutes, and supplies. The Vostok, Mercury, Gemini, and Apollo astronaut programs only used each return capsule and system once. For as long as engineers have considered rocket designs, they've considered reusable rocket designs, not only as ways to slash the cost of getting people and equipment into space, but also as a means of making access to space a matter of routine, as commercial airline travel is today. This motivated NASA's development of the National Space Transportation System, known as the Space Shuttle, in the 1970s. Space shuttles used a reusable orbiter vehicle for the crew and equipment, with rocket engines for ascent and airplane-like wings for descent, 2 reusable solid-fuel rockets, and a large expendable tank to fuel the orbiter's engines during launch. Between the first launch in 1981 and the 135th and last launch in 2011, 5 orbiters, Columbia, Challenger, Discovery, Atlantis, and Endeavour, carried 355 astronauts, some on multiple flights, into low Earth orbit, approximately 250 miles, 400 kilometers, above the surface. 14 astronauts lost their lives in the line of duty. 7 in Challenger, which exploded on launch in 1986, and 7 in Columbia, which broke up on re-entry in 2003. Despite never becoming routine and never realizing the hope of more economical access to space, the Space Shuttle's missions were still incredibly successful overall. Shuttles were critical for constructing the International Space Station, repairing and servicing the Hubble Space Telescope, launching numerous Earth and planetary satellites, and important space-related biological, astronomical, and Earth sciences research. NASA plans to build a new rocket system capable of carrying astronauts beyond the shuttle's low Earth orbit, either back to the Moon or to new destinations like near-Earth asteroids and Mars and its moons, now that the Space Shuttle fleet has retired. Rings around Neptune. With the discovery of the Uranian rings in 1977, and then the Jovian rings around Jupiter in 1979, 3 of the 4 giant planets were known to have ring systems. The British astronomer William Lassell, who had discovered Neptune's large moon Triton in 1846, also reported seeing a ring around the planet. But the observation was never confirmed. The hunt to find out if Neptune had rings lasted over 140 years. Several astronomers began observing Neptune's stellar occultations in the 1960s, when distant stars appeared to slip behind and eclipse the planet. A stellar occultation of Uranus had led to the discovery of that planet's ring system, so astronomers figured the method would also reveal rings around Neptune. Most of the results were ambiguous and not repeatable, but in 1982, 2 separate groups, one in New Zealand and the other in Arizona, reported detecting potential rings or partial ring arcs around Neptune based on analysis of observations made in 1968 and 1981. Then, in 1984, two groups of astronomers from Arizona and France were able to observe the same occultation event, and for the first time, they independently confirmed the detection of telltale dips in starlight near the planet, a strong indicator of the possibility of rings. It wasn't until the Voyager 2 flyby of Neptune in August 1989. However, the spacecraft's cameras provided solid proof of the existence of Neptune's rings. Voyager images and additional stellar occultation data revealed Neptune to have 5 distinct, generally faint, and dark rings, named after prominent astronomers who contributed to early Neptune science: Galle, Leverrier, Lassell, Arago, and Adams. The Adams ring is farthest from Neptune and contains at least 5 brighter parts or arcs than the rest. Previous ground-based astronomers have detected and identified these arcs as possible rings. Neptune's rings are dark and dusty, resembling the rings of Jupiter more than the rings of Saturn or Uranus. Like the rings of Uranus, however, Neptune's are currently thought to be relatively young remnants of a recent impact breakup of small inner moons or moonlets. Astronomers are still actively trying to determine the cause of the puzzling arcs in the Adams ring: circumstellar disks. The prevailing theory for the formation of our solar system is that an enormous cloud of gas and dust, perhaps the remnants from the supernova explosion of a previous generation star, slowly began to gravitationally contract, spin, and flatten into a disk of condensing material. More than 99% of the mass in this solar nebula disk went into the Sun. Most of the rest formed Jupiter. We live on a tiny speck of the leftovers. If this model is correct, it should also have occurred around other stars, especially Sun-like stars, common in the Milky Way galaxy. Searching for disks, rings, or dust halos around stars proved impossible, as direct starlight is 1 million to 1 billion times brighter than any reflected light from disks or planets orbiting them. A critical breakthrough was the use of a special telescopic attachment called a coronagraph, invented by the French astronomer Bernard Liot in 1930 to help block direct sunlight so that astronomers could observe the Sun's upper atmosphere or corona. Using a smaller version of the device, astronomers could block out the direct light from a star and detect the faint light from objects close to the star. In 1983, the joint NASA, Dutch and British space telescope, called the Infrared Astronomical Satellite, IRAS, conducted the first all-sky survey of infrared heat energy emitted by cosmic objects. Researchers speculate that the unusual excess of low-temperature infrared heat energy around the young Beta Pictoris stems from dusty or rocky material orbiting the star, as revealed by IRAS data. Astronomers at Las Campanas Observatory in Chile used a specially designed Liot-style coronagraph to confirm the theory in 1984. They saw a beautiful dusty and rocky circumstellar disk that stretched about 400 astronomical units, AU, from the star's center, showing a solar nebula around another star. The Beta Pictoris disk is now one of many known circumstellar disks, believed to be young solar systems caught in the act of formation. In 2008, astronomers imaged even closer to Beta Pic and discovered a giant planet about 8 times the mass of Jupiter, orbiting just 8 AU from the star, one of the first directly imaged extrasolar planets. Voyager 2 is at Uranus. During its 1981 flyby of Saturn, NASA spacecraft engineers used the ringed planet's gravity to steer the Voyager 2 space probe onward to an encounter with the giant planet Uranus in January 1986. This was the third stop in Voyager 2's grand tour of the outer solar system and remains the only spacecraft encounter with Uranus and its bluish atmosphere, icy rings, and moons. Discovered in 1781 by English astronomer William Herschel, Uranus is tilted on its side. The planet rolls rather than spins around the Sun. Voyager 2 mission planners had to guide the spacecraft within about 50,000 miles, 81,000 kilometers, of the upper cloud layers of Uranus to gain the precise gravity assistance needed to propel the spacecraft onto Neptune. The trajectory allowed a close flyby of the small inner moon Miranda and more distant views of the geology of the four other large moons, Ariel, Umbriel, Titania, and Oberon. The encounter was incredibly successful and yielded many new and enigmatic discoveries about the Uranian system. Planetary scientists discovered that Uranus has a strong magnetic field, comparable to Saturn's but weaker than Jupiter's, and is strangely tilted relative to the planet's sideways spin axis. The imaging data revealed 11 new moons and provided detailed images of the 9 dark rings previously identified from Earth-based telescopic measurements. Small amounts of methane caused the aquamarine color of the Uranian cloud tops, according to Voyager 2 data. Analysis of density and other data indicates that beneath the hydrogen and helium-dominated atmosphere, the planet has an icy mantle and an Earth-sized rocky metallic core. A lasting legacy of the Voyager 2 encounters is the discovery that Uranus and Neptune are ice giants, not gas giants. For many, though, the highlight of the encounter was the spacecraft's close pass by the tiny moon Miranda, which is only 300 miles, 480 kilometers, wide. The images revealed a patchwork quilt pattern of giant fractures, ridges, and cliffs interspersed with bland, cratered, icy terrain, a landscape like no other seen before or since in our solar system. The same massive impact event that may have toppled Uranus appears to have ripped Miranda apart and reassembled it out of order. Supernova 1987A. If a star is massive enough, perhaps 8 to 10 times the Sun's mass, stellar evolution models indicate that once it converts all of its hydrogen to helium, it will eventually end its life in a gigantic explosion called a supernova. Astronomers believe a supernova explosion goes off in the Milky Way galaxy about once every 50 years. Most are too distant to notice or obscured by galactic plane A dust. Over the centuries, Chinese astronomers recorded several guest stars, including one in 185 and a daytime star supernova in 1054, eventually forming the Crab Nebula. In 1572, Tycho Brahe obtained detailed observations of a supernova in the constellation Cassiopeia, and in 1606, Johannes Kepler wrote an entire book about a bright supernova in Ophiuchus that had occurred 2 years earlier. Kepler's supernova of 1604 is still the most recent known stellar explosion in our galaxy. Modern astronomers finally got to study a supernova up close when the blue supergiant star Sanduleak, 69°2'2", suddenly exploded on February 23, 1987, becoming supernova 1987A. The explosion occurred 168,000 years earlier in the Large Magellanic Cloud, one of the Milky Way's dwarf satellite galaxies, but it took that long for the light to arrive at Earth. The star increased in brightness by about 4,000, becoming a naked-eye object to observers worldwide for more than 6 months before it faded. Astronomers used supernova 1987A as a grand cosmic experiment to understand stellar evolution and high-energy processes. Optical and infrared telescopes worldwide and ultraviolet, X-ray, optical, and infrared telescopes in space observed the event and its aftermath. Multiple observatories detected neutrinos 3 hours before the visible explosion, confirming the core collapse model for supernova explosions. Astronomers have watched the shock waves from the main explosion crash into a shell of previously ejected gas from the dying progenitor star in the past few years. Some stars die spectacular, violent deaths. One wonders if these cataclysmic events have also destroyed planets and their inhabitants, and when the next supernova in our galaxy might occur. We seem overdue. Light pollution. The night sky was a source of reverence, inspiration, and wonder for our ancestors. On a clear, moonless night, even from the cities, it was possible to see thousands of stars with the unaided eye, including the grand, sweeping arch of the Milky Way. However, the advent of modern civilization, particularly the growth of major cities and urban centers and their widespread use of electricity for artificial illumination, has significantly changed our relationship with the night sky. Rather than thousands of stars, most people in industrialized countries can now usually see only hundreds of stars on a clear night. Residents of major cities might be lucky to see just 10 or 20 stars and a slew of airplanes, but certainly not the Milky Way. For most people, the night sky has lost its wonder, becoming a dull, faintly glowing, and featureless background part. The culprit in this nocturnal cosmic dulling is light pollution, which alters natural outdoor light levels through artificial light sources. For people living in cities or suburbs, light pollution obscures fainter stars, interferes with astronomical observations of faint sources, and can even hurt the health of nocturnal ecosystems. It's also economically inefficient. Lighting a home or building at night is to light the home or building, not to spend money and kilowatts lighting up the night sky. In 1988, in recognition of the growing global problem of light pollution, a group of concerned citizens formed an organization known as the International Dark Sky Association, IDA, with the mission to preserve and protect the nighttime environment and our heritage of dark skies through quality outdoor lighting. IDA now has about 5,000 members worldwide who work with city and local governments, businesses and astronomers to raise awareness about the value of dark skies and help implement lighting solutions that are more energy efficient and economical, leading to less light pollution. Despite some notable successes in establishing ordinances and building codes that decrease light pollution, the effect on astronomy continues to limit the utility of major observatories near large cities, such as the Mount Wilson Observatory, perched above Los Angeles. Nowadays, people build new telescopes in remote deserts or on isolated dark mountaintops to escape the growing glow of the night sky. Voyager 2 is at Neptune. The launch of the Voyager 1 and 2 missions in 1977 fortuitously occurred at a time when a rare alignment of Jupiter, Saturn, Uranus, Neptune, and Pluto could allow a space probe to gravitationally slingshot from one to the next, and enable flybys of all 5 planets with little extra propulsion needed. Advocates for this grand tour of the outer solar system realized that such an opportunity would not occur again for 176 years. Though Voyager 1 gave up the Pluto flyby option in favor of a closer flyby of Saturn's moon Titan, the Voyager 2 probe completed the initial reconnaissance of all 4 giant planets. Its last stop on the Grand Tour was in August 1989 at Neptune, where the spacecraft bent its path downward to a 24,000-mile, 38,000-kilometer flyby of the large icy moon Triton. The encounter between Voyager 2 and Neptune revealed much beauty and mystery in the Neptune system. The planet's hydrogen, helium, and methane-bearing atmosphere was much more dynamic than Uranus's had been in 1986, with dark and light blue belts and white clouds circling a giant cyclonic storm called the Great Dark Spot, analogous to Jupiter's Great Red Spot. Planetary scientists discovered that Triton's relatively youthful surface contains active geysers of icy nitrogen, water, and carbon dioxide, erupting nitrogen into the moon's thin atmosphere of nitrogen, carbon monoxide, and methane. Scientists discovered a new large moon 250 miles, 400 kilometers, across close to the planet, and named it Proteus, after the shape-shifting Greek sea god. During the flyby, scientists discovered and characterized 5 other small moons. We are slowly formulating plans to send orbiters to Uranus and Neptune to expand on Voyager's initial discoveries. The walls of galaxies, advances in telescopes, spectrometers, and photographic plates allowed early 20th century astronomers, such as Vesto Slipher and Edwin Hubble, to determine the Doppler shifts of distant galaxies in our expanding universe. Hubble's law could estimate the distances to those red-shifted galaxies. It was slow going. By the 1950s, only around 600 galaxies had estimated distances. However, larger telescopes, advancements in digital detectors, such as charge-coupled devices or CCDs, and the advent of dedicated all-sky galaxy surveys enabled the measurement of redshifts for more than 30,000 galaxies by the 1970s and 1980s. Finally, we can start mapping the universe. A pioneer in galaxy mapping, along with fellow Harvard-Smithsonian Center for Astrophysics, CFA, astronomer John Hutra, has been using the results of several large-scale galaxy redshift surveys to discover the structure of the cosmos. The first CFA redshift survey ran from 1977 to 1982, and the second from 1985 to 1995. In 1989, Geller and Hutra reported that the distribution of galaxies was far from uniform. Instead, a structure now known as the cosmic web clusters galaxies into enormous filamentary structures surrounding giant voids containing a few galaxies. The Great Wall, named by Geller and Hutra, is one of the largest known structures in the universe, measuring over 500 million light-years long and 300 million light-years wide. Astrophysicists have a powerful working model for forming these vast patterns in the universe. Galaxies and larger patterns grow from very small irregularities in the matter distribution in the early universe. In some versions of this model, these irregularities can arise from a very early, during the first 1032 seconds after the Big Bang inflation epoch, smearing matter into web-like filaments that may have clumped into galaxies. The Hubble Space Telescope. The first astronomical telescopes, developed in the early 17th century, opened the skies to astronomers. They and subsequent larger and more advanced instruments enabled amazing discoveries about the solar system, galaxy, and universe. But astronomers have always known that even the largest telescopes on Earth are fundamentally limited in two important ways. First, the unavoidable shimmering and twinkling of our atmosphere limit the resolution to much less than a large telescope's theoretical limit. And second, our atmosphere blocks many parts of the spectrum, especially in the ultraviolet and infrared ranges, making ground-based observations difficult or impossible at key wavelengths. With the advent of space satellites in the 1960s, astronomers began advocating within NASA for a dedicated space-based telescope to overcome those limitations. An orbiting space telescope's chief champion was American astronomer Lyman Spitzer, who led a critical grassroots lobbying campaign for the project's necessary support and funding. The Hubble Space Telescope, HST, named after astronomer Edwin Hubble, received approval in 1978 after overcoming numerous bureaucratic hurdles and forging a partnership with the European Space Agency. The Space Shuttle Discovery launched HST into low Earth orbit, about 350 miles, 570 kilometers, above the surface, in April 1990. HST discovered a major flaw in its primary mirror design shortly after launch. Fortunately, Space Shuttle astronauts could service the telescope, and 5 shuttle missions between 1993 and 2009 fixed and upgraded key instruments and components. As a result, HST serves as a cosmic time machine that uses CCD imaging and spectroscopy to determine our universe's nature and even age. HST is only a medium-sized telescope by today's giant telescope standards. Still, its constant clear sky and full-spectrum view of the cosmos has enabled it to realize Spitzer's and other early supporters' dreams and fundamentally revolutionize modern astronomy and astrophysics. During a servicing mission in February 1997, the Space Shuttle Discovery released the Hubble Space Telescope, which now floats about 350 miles, 560 kilometers, above Earth's surface. The telescope is about 8.2 feet, 2.5 meters in diameter, and about 43 feet, 13.1 meters, long or slightly longer than an average school bus. Venus was mapped by Magellan. When Galileo peered through his early astronomical telescope in 1610, he was the first to realize that Venus has phases. In contrast to his studies of the Moon and Jupiter, Galileo's observation of Venus did not reveal any specific features or markings, unlike those of other astronomers. Recent telescopic observations and space missions, such as the Soviet Venera orbiters and landers, have revealed that a thick atmosphere of carbon dioxide and featureless sulfuric acid clouds and hazes obscure the surface of Venus, which is not surprising. Fortunately, radio waves can see through clouds and haze. Indeed, terrestrial meteorologists use radar weather mapping instruments to exploit radio waves passing through clouds and bouncing off raindrops and snowflakes. In the 1960s, astronomers figured out that radio waves could penetrate the clouds of Venus by bouncing radar signals off the planet using the Arecibo radio telescope. This allowed for the detection of some surface markings and the discovery of the planet's very slow, 243 Earth days, backward rotation. The Arecibo findings helped justify the development of orbital radar mapping missions to Venus. The first successful missions were the Soviet Venera 15 and 16 orbiters in 1983-1984, which mapped about 25% of Venus's northern hemisphere, revealing mountains, ridges, faults, volcanoes, and other landforms. Venera's results helped spur an even more ambitious Venus radar mapper, the NASA Magellan mission. Launched in 1989 by the space shuttle Atlantis, Magellan arrived in 1990 and systematically mapped 98% of the surface from pole to pole. Magellan data reveal the full scope of Venus's topography, from high mountains to deep valleys, and provide geologists with images of a spectacular variety of volcanic, tectonic, impact, and erosional landforms. Magellan scientists discovered vast lava plains, pancake-shaped volcanic domes, and large Hawaiian-style shield volcanoes. They also discovered channels, thousands of miles long, carved by very low viscosity molten rock. Vast networks of ridges and troughs, indicating tectonic activity, but not Earth-like plate tectonics. And a scarcity of impact craters, implying that massive lava outpourings resurfaced most of the planet some 500 to 750 million years ago. While certainly not Earth's twin, Venus turns out to have been, and still is, just as active over geologic time. Mapping the cosmic microwave background. The discovery of the cosmic microwave background in 1964 held significant implications, as it demonstrated the feasibility of testing theories such as the Big Bang through actual observations. A new generation of astronomers became interested in observational cosmology, the precise measurement of certain universe characteristics that could enable a detailed understanding of its origin and evolution. However, conducting these measurements from space is necessary to achieve the necessary precision. NASA's Continuing Explorer Small Satellite program, which began in 1958 with the Explorer 1 discovery of the Van Allen radiation belts, was a perfect platform. Astronomers developed the mission concepts in the 1970s, and NASA approved the Cosmic Background Explorer, COBE, mission in the 1980s, launching it into Earth orbit in 1989. COBE used very sensitive infrared and microwave radiation detectors to slowly and accurately build up a map of the variations in cosmic background radiation across the entire sky. In 1992, cosmologists announced that the initial map was complete, and the results were exciting. The main variation that COBE detected was a weak so-called dipole signature, which was only about 1/1000th of the sky's brightness due to the Doppler shift from our galaxy's motion relative to the rest of the universe. After eliminating that signal, our Milky Way galaxy's faint microwave emission caused the next largest COBE variation. Astronomers were delighted that there were still some small variations left, tiny fluctuations in background radiation at a few millionths of a degree. Cosmologists believe the universe's inflation in the first 10 to 32 seconds after the Big Bang formed those tiny variations, concentrating normal and dark matter into the seeds that would eventually form galaxies and stars. In 2003, the Wilkinson Microwave Anisotropy Probe, WMAP Explorer mission, confirmed and extended COBE's results, helping to provide new, accurate estimates of the universe's age. The first extrasolar planets. Are there planets around other stars? Throughout astronomy history, whether planets orbit other stars has been too heretical to pose, leading to Giordano Bruno's execution in 1600, or too technologically impractical to tackle. Recently, though, astronomers have discovered that the answer is a resounding yes. By the late 20th century, telescopes and observational technology had advanced to the point where astronomers could detect the presence of planets around other stars using various methods. One method exploits the fact that planets make their parent stars wobble in the sky. Jupiter's gravity, for example, makes our Sun's path appear to wobble slightly as it orbits the galaxy's center. In 1992, astronomers discovered that they could detect such small wobbles as very slight changes in the rotational speed of rapidly spinning neutron stars, known as pulsars. 1990 astronomers discovered a millisecond pulsar named PSR B1257+12 in the constellation Virgo using the Arecibo radio telescope. Every 622 milliseconds, MSEC, the pulses from this collapsed neutron star's supernova remnant were monitored, revealing small, regular variations in the pulse rate. In 1992, researchers explained that the gravitational pull of at least 3 planets orbiting the pulsar caused this. Mathematical modeling showed that 2 planets were likely around 4 times Earth's mass, and a third was around 2% of Earth's mass. All appear to orbit within 0.5 astronomical units of the pulsar. Most astronomers were surprised by this first confirmed evidence for the existence of extrasolar planets, as they had expected to find planets around other normal main sequence stars like the Sun, rather than around exotic objects like neutron stars. There is much speculation about the nature of these particular pulsar planets. They may be the rocky and metallic cores of previous gas or ice giants that had their outer volatile layers stripped away by the supernova explosion that created the pulsar. Alternatively, they could represent the results of a second round of solar nebula planet formation, using remnant materials ejected by the supernova explosion. Regardless of their origins, these worlds' detection is robust. Astronomers and planetary scientists are now discovering and characterizing planets around other suns, but they must also consider an even wider range of ways that extreme extrasolar planets can form and evolve in various environments. Kuiper Belt objects. After discovering Pluto in 1930, many astronomers wondered if the solar system ended just beyond Neptune's orbit. In 1943, the Irish astronomer Kenneth Edgeworth hypothesized that Pluto might be one of many small trans-Neptunian bodies that failed to grow very large because of the large separation between early-growing planetesimals, kilometer-sized clumps of dust and ice, and the resulting lower impact rate in the outer solar system. Gerard P. Kuiper, a Dutch-American planetary scientist, studied planet formation in the outer solar system in the 1950s, and similarly hypothesized the presence of a large disk of small bodies beyond Pluto. However, Kuiper speculated that Pluto's gravitational influence would have cleared out and scattered away this disk if Pluto were an Earth-sized body, as was thought at the time. The existence of what astronomers came to call the Edgeworth-Kuiper belt, or just the Kuiper belt, remained a subject of speculation for decades. However, the advent of giant telescopes and super-sensitive charge-coupled device (CCD) detectors in the 1990s made it possible to search for and ultimately detect small, faint, asteroid-like bodies at distances beyond Neptune's orbit. In 1992, scientists discovered the first member of the Kuiper belt, apart from Pluto, Charon, and possibly former members Triton and Phoebe. Named 1992 QB1, the object orbits between 40 and 46 astronomical units. AU, Neptune is at 30 AU, and is probably about 100 miles, 160 kilometers, in diameter. Since then, astronomers have discovered more than 1,000 Kuiper belt objects, KBOs. Some, such as 136199 Eris, 136472 Makemake, and 136108 Haumea, are comparable in size to Pluto. In fact, Eris may be larger than Pluto, partly precipitating the International Astronomical Union's decision in 1996 to demote Pluto from planet to dwarf planet status. Scientists have discovered satellites in about 10% of known Kuiper belt objects, including Pluto. KBOs are primitive bodies containing comet-like mixtures of water, methane, and ammonia ice. The New Horizons probe will give us our first look at KBOs, Pluto and Charon in 2015, and will go on to encounter more in the 2020s. Asteroids can have moons. Galileo Galilei discovered the first planetary satellites beyond our own moon around Jupiter in 1610. Since then, scientists have discovered dozens more natural satellites around all planets, except Mercury and Venus. In 1978, the discovery of a moon around the small dwarf planet Pluto prompted many astronomers to question an object's size limit for moon formation. Could asteroids have moons? Telescopic searches in the 1970s and 1980s provided possible evidence for their existence. However, definitive proof didn't come until 1992, when the NASA Galileo spacecraft flew past main belt asteroid 243 Ida en route to Jupiter. Galileo's images revealed a small moon orbiting the asteroid, to everyone's surprise and delight. Mission scientists named the moon Dactyl, 1 mile, 1.6 kilometers wide, after creatures that inhabited Mount Ida on the island of Crete in Greek mythology. Buoyed by the certainty that even small bodies can have moons, planetary astronomers redoubled their efforts to find more. Using advances such as adaptive optics to increase the effective resolution of ground-based telescopes, as well as assets such as the Arecibo Radio Telescope and the Hubble Space Telescope, scientists have since discovered moons around more than 200 small bodies, including Trojan asteroids of Jupiter and Kuiper belt objects. Scientists have discovered more than 220 minor planet moons, with some small bodies boasting 2 or 3 moons and Pluto boasting 5. Planetary scientists have several leading theories about how asteroid-size or dwarf planet-sized bodies can have moons. Impacts on the primary asteroid knock off debris that stays and accumulates in orbit to form a satellite. The huge numbers of impact craters seen on the surfaces of asteroids, such as 243 Ida and 433 Eros, the target of the NASA Near-Earth Asteroid Rendezvous (NEAR) mission, support this idea. Alternatively, asteroids may capture other asteroids during close encounters. Computer models show this is possible for binary asteroids comparable in size and relatively close to each other, but less likely in situations like the Ida Dactyl system, where one body is very large compared to the other. In 1992, the NASA Galileo spacecraft flew past the asteroid 243 Ida while traveling through the main asteroid belt en route to its orbital mission at Jupiter. Images of the asteroid, 33 miles, 53 kilometers long, also revealed a tiny 1 mile, 1.6 kilometer companion moon named Dactyl. Giant telescopes. The frontier of modern astronomy has been defined during the last few centuries by the limits of telescope and instrument technology. The need to observe extremely faint sources, often adjacent to much brighter sources, at extremely fine resolutions, to acquire spectroscopic observations over a wide range of the electromagnetic spectrum, and to accurately record observations for later detailed analysis have all pushed astronomy and astronomers to the cutting edge of optics, engineering, electronics, and software design. This is more noticeable than the recent proliferation of enormous optical telescopes at premier observing sites worldwide. The late 1940s casting of the 200-inch, 5-meter telescope mirror for the Hale telescope at Mount Palomar was a marvel of then-modern engineering. In the decades since materials and mechanical engineering methods have improved dramatically, the largest practical single-mirror telescope size has only grown to about 320 inches, 8 meters, because of gravity and material strength limitations. Substantially increasing the light collecting area has required engineers and opticians to innovate, and a key innovation has been the development of segmented mirrors, smaller, more practical mirrors that, when assembled together, simulate a single mirror of much larger size. The first large-scale experiment in segmented mirror telescopes was the twin 400-inch, 10-meter telescopes of the W.M. Keck Observatory atop Mauna Kea, Hawaii. Each telescope's mirror consists of 36 hexagonal 70-inch, 1.8-meter segments that are individually and dynamically computer-controlled to form a near-perfect giant parabolic reflector. Keck-I went online in 1993, Keck-2 in 1996. Since then, both have enabled incredible scientific discoveries. We built 2 Keck telescopes to try to exploit another innovation in giant telescope design, combining data from 2 or more telescopes, electronics, and software to yield angular resolutions equivalent to a single enormous telescope the size of an individual's separation. This process is known as interferometry. The Keck telescopes are just one example of a growing number of large optical interferometer telescopes now defining the newest frontier in ground-based astronomy. Comet Shoemaker 9 slams into Jupiter. Impacts have been a fundamental force in shaping the surfaces and atmospheres of the planets, as well as influencing the history of climate and life in our own world. Impacts, on the other hand, are rare and unpredictable events in the solar system and have therefore been impossible to study directly. Or at least they were, until a group of astronomers discovered a year in advance exactly when a comet would smash into the planet Jupiter. The American astronomers Eugene Shoemaker and Carolyn Shoemaker, along with the Canadian astronomer David Levy, reported discovering a strange string of pearls comet in the summer of 1993. Their observations revealed that the comet had recently passed so close to Jupiter that it had broken into dozens of fragments. Their data showed that the fragments, now collectively known as Comet Shoemaker-Levy 9, SL9, were on return trajectories to Jupiter and would crash into the planet in July 1994. This was the first time an impact event was known in advance, and astronomers worldwide mobilized telescopes and space observatories to monitor the events. As predicted, 21 cometary fragments 0.61.2 miles, 1 to 2 kilometers, across slammed into Jupiter at 134,000 miles per hour, 60 kilometers per second, between July 16th and July 27th. The results were spectacular and surprising, defying widespread predictions that such small, icy objects could produce huge fireballs, plumes, and Earth-sized blemishes lasting for months. Indeed, some astronomers had predicted that Jupiter would swallow up the tiny fragments without any noticeable effect. How wrong they were. The SL9 impacts on Jupiter were a humbling reminder of the destructive power of small bodies traveling at very high speeds. They were also a public and media sensation, shared worldwide in near real time via a relatively new communication medium known as the Internet. Brown dwarfs. Stars in the main sequence come in many colors and sizes, but they all share the common attribute of central core temperatures and pressures high enough to enable the nuclear fusion of hydrogen into helium. Indeed, the lowest possible stellar mass that enables nuclear fusion is about 7 to 9% of the mass of the Sun, or about 75 to 80 times the mass of Jupiter. In the 1970s, astronomers hypothesized that a population of substellar objects might be too large to be considered giant planets, but too small to be considered stars. Scientists dubbed these objects brown dwarfs because they would be smaller than stars and emit infrared heat from gravitational contraction, but not their visible light from nuclear fusion. The hunt aimed to find and characterize these potentially important links between giant planets and small stars. In the late 1980s and early 1990s, researchers found potential candidates, but it was challenging to pinpoint the boundary between small stars and brown dwarfs. Only in 1994 did scientists identify a faint infrared source near Gliese 229, a small red dwarf star about 19 light-years from our solar system, as a possible brown dwarf. Follow-on observations from the Hubble Space Telescope and other observatories revealed that the fainter object is orbiting around the star, earning it Gliese 229b, GL229b. GL229b's luminosity and temperature, 950 kelvins, are well below those of even the smallest main sequence stars, but much higher than those of a gas giant planet, orbiting some 30 astronomical units, AU, from a red dwarf star. The telltale proof that GL229b is not a low-mass star came with the discovery of methane, a gas not stable in stellar atmospheres, in its spectrum. Current estimates are that GL229b is a brown dwarf of about 20 to 50 Jupiter masses. Some of the largest newly discovered planets around other stars have masses around 20-50 times Jupiter's mass. Does this imply that they are brown dwarfs rather than planets? The low mass line between a giant megaplanet and a low mass star appears fuzzy. Astronomers often use density, infrared luminosity, or the presence of X-rays to decide, but when in doubt, they fall back on the official definition that a brown dwarf is above 13 Jupiter masses. Planets around other suns. The discovery of the first extrasolar planets around pulsar B11257+12 in 1992 compelled astronomers to search even harder for evidence of extrasolar planets around normal main sequence or sun-like stars. For decades, it has been known that stars in binary systems can show wobbles in their proper motion across the sky, because both stars are actually orbiting the system's center of mass. Theoretically, a giant Jupiter-like or larger planet in orbit around a single star should exhibit the same kinds of wobbles, albeit much smaller. A breakthrough came when astronomers realized that they didn't need to measure the precise position of the star over time. Instead, they could use the Doppler shift of the star's spectrum to deduce its wobbling motion from the star's radial velocity, the part of that wobble directed toward or away from Earth. This method found the first extrasolar planet orbiting the nearby Sun-like star 51 Pegasus, 51 Peg, in 1995. We inferred planet 51 Peg b to be a gas giant, many times the size of Jupiter, orbiting very close, just 0.05 astronomical units from its star, based on the amount of wobble it induced in 51 Peg and the timing of the Doppler-shifted spectral variations. Since then, the radial velocity method has discovered more than 500 other planets around nearby stars. Most of these planets are known as hot Jupiters because they are large and orbit extremely close to their parent stars. Big planets close in are the easiest to find using the radial velocity method, so hot Jupiters may not be typical. Other ways to find extrasolar planets, besides radial velocity and pulsar timing, are to watch for them passing in front of, transiting their parent stars, the goal of NASA's Kepler mission, to detect them by gravitational lensing, or to directly image them through the glare of their parent stars. The most known extrasolar planets are still gas or ice giants. Nevertheless, astronomers are now finding and cataloging many Earth-size or super-Earth-size worlds around nearby sun-like stars using these methods. The discoveries of extrasolar planets are just beginning. Galileo orbits Jupiter. The Pioneer 10 and 11 and Voyager 1 and 2 flybys of Jupiter revealed a beautiful, complex and enigmatic mini-solar system on the giant planet, including a dynamic atmosphere of zones, belts and long-lived cyclonic storm systems, such as the Great Red Spot. A veritable zoo of icy and rocky satellites, including 4 that are essentially planets in their own right: Io, Europa, Ganymede and Callisto. A dusty system of narrow rings, and an enormous magnetosphere that bathes much of the system in high-energy radiation. The discoveries during those brief flybys convinced planetary scientists that the next logical step would be to send a spacecraft to orbit Jupiter and stay for a while. In late 1977, Congress and international support approved funding for the Jupiter Orbiter and Probe mission, renamed Galileo in honor of the astronomer who first studied Jupiter and its moons through a telescope. After overcoming several technical and financial challenges, the Space Shuttle Atlantis launched Galileo in late 1989. Using gravity-assist flybys of Venus and Earth, it slingshot out to Jupiter, where it arrived and entered orbit in December 1995. Along the way, Galileo performed the first close asteroid flybys, 952 Gaspra and 243 Ida, while passing through the main asteroid belt. The main communications antenna's failure to open properly handicapped the mission, but mission engineers and scientists designed a new mission using the backup low data rate antenna. Using the spacecraft's cameras, spectrometers, fields, and particle instruments, the Galileo team directed the spacecraft through 34 elliptical orbits of Jupiter over nearly 8 years, flying past large and small moons to determine their composition and internal structure, studying the rings and magnetic field in detail, and releasing a probe into the atmosphere that relayed direct measurements of composition, temperature, and pressure. At the end of its mission, Jupiter's deep atmosphere crushed and vaporized the Galileo spacecraft, but its scientific legacy will endure, upholding the larger legacy of the name Galileo. Life on Mars. Telescopic observers like the American businessman and astronomer Percival Lowell, who claimed to see evidence for vast networks of linear canals crisscrossing the parched Martian plains, popularized the idea of Mars as a potential abode of life in the late 19th and early 20th centuries. The media picked up on the notion, exploiting the idea of Martian inhabitants through fantastic and highly rated science fiction stories, such as the 1938 radio adaptation of H.G. Wells's The War of the Worlds. The search for evidence of life on Mars also permeated much of the 20th century exploration of the Red Planet, culminating in the design and operation of several highly sensitive organic and biologic detection experiments on the two NASA Viking landers in 1976. It is still not clear if the uppermost surface materials, which have been exposed to harsh solar UV radiation for billions of years, should contain any organic molecules, even though the negative results of those tests were generally accepted. There was no evidence of organic molecules at either landing site, not even at the parts per billion level. The experiments were limited. In 1996, a team of NASA scientists made an extraordinary claim while studying samples from a meteorite named ALH-84001, which blasted off Mars and eventually fell into Antarctica. Inside that piece of ancient Martian rock, they claimed, was chemical, mineral, and geologic evidence for fossilized microbes. There had been life on Mars. The astronomer Carl Sagan was fond of saying that extraordinary claims require extraordinary evidence. In the case of ALH-84001, most scientific communities do not believe that the evidence supporting life is extraordinary. Instead, NASA researchers present non-biologic explanations for each piece of evidence. Still, the original team remains convinced. Ultimately, whether there is convincing evidence of life inside ALH-84001 may be irrelevant. It may be more important to note that most scientists agree that the requirements for life, liquid water, heat, energy sources, and organic molecules, were all present in the environment when this rock was on Mars. That is, ALH-84001 helps us know that it was at least habitable. Great Comet Hale-Bopp. Comets, small, rocky, and icy bodies that evaporate spectacularly when they get close to the Sun, have excited and even alarmed people for ages. Some are visible in the sky at predictable times, like Halley's Comet, which returns every 76 years. Many others, however, appear suddenly and at unpredictable times. Perhaps the most spectacular of these unexpected comets was Hale-Bopp, which was visible to most of the world for many months in the early evening skies during the spring of 1997. Alan Hale and Thomas Bopp, two American amateur astronomers, discovered Comet Hale-Bopp in July 1995, as it was heading toward the Sun, but still far out past Jupiter's orbit. Tracking the comet's orbit revealed that it is on a long elliptical path that takes more than 2,500 years to circle the Sun. At its farthest distance, the comet is more than 370 times farther from the Sun than the Earth is. Astronomers calculated that before 1997, the last time Hale-Bopp had passed by the Earth was in the summer of 2215 BCE. They classify this comet as young because its complement of highly volatile ices shows that it has spent most of its time in the cold outer solar system rather than in the warm environs closer to the Sun. Several years advance warning of the comet's passing by Earth gave astronomers a rare opportunity to study such a young comet up close for the first time. Using spectroscopy and other methods, astronomers discovered rocky dust, water ice, sodium, and other molecules in the comet's ion and dust tails, including some complex organic molecules never before detected in comets. Hale-Bopp's bright head, or coma, implied that the rocky and icy nucleus must be large for a comet, about 37 miles, 60 kilometers in diameter, or about 6 times the size of Halley's Comet. While Hale-Bopp is not a direct threat to us, a comet that size, impacting Earth at a velocity of more than 50 kilometers per second, would wipe out civilization and potentially kill most life on our planet. Billions of people saw Hale-Bopp because for several months it was bright enough to see with the naked eye just after sunset. There was a lot of media coverage about the Great Comet of 1997, as well as some unfounded speculation and hype about the potential contamination of Earth by comet debris. Beautiful heavenly bodies, or possible portents of doom? Comets have always been a bit of both. 253 Matilda. The NASA Galileo missions' flybys of the main belt asteroids, 951 Gaspra and 243 Ida in 1991 and 1993, revealed that even small planetary bodies can have interesting surface features and moons of their own, spurring interest in a dedicated space mission to study asteroids up close. NASA launched the first project, the Near-Earth Asteroid Rendezvous (NEAR) mission, in 1996 to study the Earth-approaching asteroid 433 Eros. Along the orbital path toward its encounter with Eros, NEAR acquired some bonus science in 1997 by flying past the large main belt asteroid 253 Matilda. Matilda, discovered in 1885 by the prolific Austrian astronomer and asteroid hunter Johann Palisa, orbits along an elliptical path between Mars and Jupiter. More recent telescopic observations show that Matilda is quite dark, almost black as coal, reflecting only about 4% of the incident sunlight. Astronomers put Matilda in a different class than Gaspra and Ida, which are S-type asteroids, more like stony meteorites, because it has a low albedo, ratio of reflected light to incident sunlight, a gray color, and a spectrum with few features. This is because Matilda is more like a carbon-bearing meteorite. Matilda's different spectral class, as well as the fact that it rotates very slowly, taking more than 17 days to spin once on its axis, created some excitement about what NEAR might see. The NEAR flyby of 253. Matilda confirmed the asteroid's low albedo and revealed several surprises. Scientists estimated Matilda's density at about 1.3 grams per cubic centimeter, despite only photographing about 60% of the asteroid. This surprisingly low value is much smaller than typical rock densities. Since the asteroid is likely too close to the Sun, too warm, to contain ice, the best alternative was to deduce that there is up to 50% empty space inside Matilda between large chunks of rocky material. Matilda is a porous, rubble pile asteroid. NEAR's discovery of half a dozen giant impact craters on Matilda supports this idea. If the asteroid were a coherent rocky body, then any of those impacts should have destroyed it. However, interior pore space absorbs impact energy, enabling the asteroid to remain intact in the face of otherwise devastating blows. First, rover on Mars. The NASA Viking lander missions were unquestionable successes in the exploration of Mars, but they provided at least two important lessons for the future. First, it would be scientifically better to have mobility on the planet's surface, rather than having to stay at one fixed landing site. And second, it would be better economically to be able to explore a planetary surface for much less than the multi-billion-dollar cost of a flagship-class mission such as Viking. NASA incorporated these lessons into its third attempt at a Mars landing mission, the Mars Pathfinder. Launched in 1996, Mars Pathfinder was one of the first of NASA's new, better, faster, cheaper Discovery-class missions, with a cost target of only 10–20% of the cost of the original Viking missions. In addition to landing a spacecraft on Mars at a lower cost, the team also had to accommodate and operate a small rover to showcase the benefits of mobility on the Red Planet. Using a novel and risky airbag-assisted landing system, Pathfinder landed on Mars on July 4, 1997, and deployed a small rover named Sojourner, after the 19th century African-American abolitionist and women's rights advocate Sojourner Truth. Shortly after that, for nearly 3 months, the Pathfinder lander and Sojourner rover obtained images and chemical data on rocks and soils at the mission's landing site in Ares Vallis, an ancient Martian outflow channel that is thought to have been the site of a catastrophic flood early in the planet's history. Various geologic and geochemical clues obtained during the mission provided evidence for the region's watery past. The Sojourner rover, moving at a top speed of about 0.022 miles per hour, 1 centimeter per second, only traveled about 330 feet, 100 meters, along a circuitous path around the lander during the mission's 83 Martian day duration. Still, it was a remarkable demonstration of the value of mobility in robotic exploration, as the rover could photograph and chemically sample a much wider variety of rocks and soils at the site than the lander alone could have. The next-generation Mars exploration rovers Spirit and Opportunity, which landed on Mars in 2004, scaled up the successful basic design and operation principles for Mars roving, demonstrated by Sojourner by about a factor of 3. Mars Global Surveyor. Observations from the first Mars and Viking orbiters in the late 1970s and early 1980s provided tantalizing evidence that ancient Mars was significantly different, and perhaps more Earth-like, than current Mars. NASA launched the Mars Observer Orbiter in 1992 to conduct more extensive observations. Regrettably, a fuel line rupture likely caused the loss of communications with the Mars Observer just 3 days before it arrived at Mars. The successful arrival of NASA's Mars Global Surveyor (MGS) orbiter in 1997 restored much of the science lost from the Mars Observer in 1993. MGS carried cameras, an infrared spectrometer, a laser altimeter, and a magnetometer to map the planet's geology, mineralogy, topography, and magnetic properties from pole to pole over 9 Earth years, about 4 Mars years. MGS measurements revolutionized our understanding of the surface and atmosphere of Mars, much as Viking measurements had done more than a decade earlier. For example, high-resolution, meter-scale images revealed fine details of channels, gullies, and even deltas formed by the persistent flow of liquid water during early Mars history, when the climate must have been warmer and wetter. We mapped volcanic and potentially water-formed minerals globally and measured the topography more accurately than we had for our planet. We found evidence of a strong global magnetic field on Mars, possibly when the core was partially molten and the interior was more geologically active. MGS images, topography data, and mineral discoveries provided the primary means to select the most compelling potential landing sites for the 2004 Mars exploration rovers Spirit and Opportunity. They helped guide the selection of next-generation cameras and spectrometers for the 2003 European Space Agency Mars Express Orbiter and the 2006 NASA Mars Reconnaissance Orbiter. MGS lost contact in late 2006, but its legacy continues with other orbiters and rovers. The International Space Station. Early 20th century rocket pioneers such as Konstantin Tsiolkovsky and Robert Goddard were among the first to work out the technical details of orbiting stations and habitats in space. However, for most of the century, only science fiction books, magazines, TV shows, and movies realized the idea of a human outpost in Earth's orbit. The Soviet Union launched the first of 9 long-duration Salyut space research modules in the 1970s, followed by the orbital assembly of their Mir space station, the first long-duration multi-crew outpost in space, in the 1980s. Due to cost overruns and technical delays, NASA's plans to launch a US space station, Freedom, in the 1980s have yet to materialize. The fall of the Soviet Union in 1991, technical problems with the Mir station, and the high cost of launching and operating space vehicles in general all compelled NASA, Russia, and other spacefaring nations to pool resources toward the design and operation of a joint International Space Station, ISS, beginning in 1993. The first component of the new ISS was a Russian electrical power, propulsion, and storage module called Zarya, launched into low Earth orbit about 230 miles, 370 kilometers, above the surface, on a Russian Proton rocket in November 1998. The crew of the Space Shuttle Endeavour launched and connected the second component, a US docking, airlock, and research module named Unity, to Zarya a few weeks later. Over the next 13 years, 15 more shuttle launches and Russian Proton and Progress rockets added additional solar panels, living quarters, laboratories, airlocks, and docking ports. Completed in 2011, the ISS now spans the area of a US football field, with a total mass of more than 920,000 pounds, 420,000 kilograms, making it the largest artificial satellite ever constructed. In addition to the United States and Russia, the European, Japanese, and Canadian space agencies are also key partners. The International Space Station, ISS, is an international research laboratory that leverages its unique microgravity orbital environment to facilitate space-related medical, engineering, and astrophysical research. However, it also serves an important role as an outpost for a permanent human presence in space, where we can learn how to live and work and how best to prepare to venture further beyond low Earth orbit for deep space voyages of exploration. Dark energy. When physicist Albert Einstein developed his theory of general relativity early in the 20th century to explain the relationship between space, time, and matter in the presence of gravitational fields, it was in the context of what astronomers believed at the time to be a static or unchanging universe. To make his theory work, Einstein had to invent an as-yet unseen force, which he called the cosmological constant, to counteract the attractive force of gravity and enable the universe to remain static. In 1929, Edwin Hubble's discovery of space expansion led Einstein to conclude that his cosmological constant was no longer necessary. Everything fit nicely. But astronomers' detailed study of spiral galaxies and galactic cluster motions over subsequent decades led to the surprising discovery of an unseen but gravitationally attractive material known as dark matter, as well as the humbling realization that most of the universe consists of matter that we cannot observe directly. Even more surprising was the discovery by astronomers in 1998 that the universe's expansion appears to be accelerating with time. That is, galaxies nearer to us, which we observe in the relatively modern era of the universe, are moving away from each other faster than extremely distant galaxies, which we observe from much earlier in the universe's history. One possible explanation is that some unseen energy force or pressure permeates the vacuum of space and acts opposite to gravity, helping to accelerate the normal expansion of space since the Big Bang. Cosmologists call this hypothesized force dark energy. Maybe Einstein was right about his cosmological constant after all. Dark energy's true nature, or existence, is impossible to study directly with traditional telescopic observations. Similar to dark matter, we can only indirectly infer its presence by studying its gravitational effects on normal matter. If dark energy proves to be real, however, it would lead to an even more stunning and humbling realization about our universe. Dark energy and dark matter, things we currently have no way to measure or characterize, comprise 96% of the energy in our universe, while ordinary matter, galaxies, stars, planets, and us, account for only 4% of the cosmos. Torino Impact Hazard Scale. Our planet's dynamic geology and hydrology have erased the evidence for all but a few hundred terrestrial impact craters. But the ancient, heavily scarred surface of our planetary neighbor, the Moon, tells us that significant numbers of asteroids and comets have struck Earth in the past. These high-speed impact events released huge amounts of energy, and geologic evidence and the fossil records suggest that they occasionally significantly altered the planet's climate and biosphere. Throughout Earth's history, the impact rate has decreased exponentially. Still, even in modern times, that rate is not zero. Consider, for example, the 1908 explosion of a comet or asteroid in the atmosphere above Siberia, the Tunguska event, and the observation of several large atmospheric fireball explosions every year by military and civilian planetary monitoring satellites. Fueled by public and political interest in understanding the risks associated with cosmic impacts, the discovery rate of small asteroids and comets, especially within the population known as near-Earth objects, NEOs, has increased over the past few decades. Dedicated telescopic surveys have identified over 500,000 main belt asteroids and nearly 1,000 NEOs. The few hundred NEOs that could threaten life on our planet get a special acronym, PHAs, for potentially hazardous asteroids. As PHA discovery rates increased, it became clear that there was no systematic or simple way to understand and communicate the risk of PHA impacts. Indeed, there was much potential for confusion or even unfounded panic about this issue. So, in 1999, a group of planetary astronomers developed an index called the Torino Impact Hazard Scale to quantify the risks. For newly discovered PHAs, Torino values range from 0, no chance of impact, to 10, certain impact with likely catastrophic consequences. Most PHAs have Torino values of 0. Follow-on observations downgraded most of the non-zero values to 0. The record so far is an original value of 4, a 1% or greater chance of collision, for the asteroid 99942 Apophis, which will pass very close to the Earth on April 13, 2029. Astronomers have since downgraded the Apophis risk to 0, but they continue to monitor it closely. The Chandra X-ray Observatory. In 1895, German physicist Wilhelm Röntgen discovered a mysterious form of radiation in high-voltage cathode ray tube experiments. He referred to X-rays as an unknown type of radiation. Eventually, 20th century physicists discovered that electrons accelerated to high velocities in laboratory experiments or high-energy astrophysical events like supernova explosions can create X-rays. However, the astronomical study of X-ray sources was severely limited because the Earth's atmosphere absorbs most X-rays generated by cosmic events. A space-based platform was needed. In 1978, NASA launched the Einstein X-ray imaging satellite to conduct the first space-based observations of high-energy cosmic X-ray sources. For nearly 3 years, Einstein surveyed the sky, studying the details of supernova explosions and identifying new X-ray sources. Einstein's success prompted astronomers to propose a more sensitive, higher-resolution X-ray space telescope mission as part of NASA's Great Observatories program. 4 space telescopes designed to allow scientists to make impossible measurements from Earth-based telescopes. NASA launched the Advanced X-ray Astrophysics Facility Space Telescope, named Chandra after the Indian-American astrophysicist Subramanian Chandrasekhar in 1999, after more than 20 years of development. Expected to last only 5 years, Chandra has operated for over a dozen years, collecting data on supernovae, pulsars, gamma-ray bursts, supermassive black holes, brown dwarfs, and dark matter. An ocean on Ganymede? Between 1995 and 2003, NASA's Galileo Jupiter orbiter conducted a grand orbital investigation of the giant planet's atmosphere, magnetic field, moons, and rings. We designed the spacecraft's trajectory to make close flybys of the Galilean satellites, Io, Europa, Ganymede, and Callisto, allowing us to study their surface features up close and measure their masses and gravity fields while monitoring their slight orbital deflections. Throughout the mission, Galileo made 6 close flybys of Ganymede, the solar system's largest moon. Gravity data revealed a differentiated interior of Ganymede, segregated into a dense core of rock and iron, a lower density, presumably icy mantle, and an outer icy crust. The biggest surprise from the flybys, however, was the discovery that Ganymede has its own magnetic field embedded within the strong magnetosphere of Jupiter. Ganymede is the only moon in the solar system with its own magnetosphere. The same process that generates Earth's magnetic field is believed to generate Ganymede's magnetic field, a spinning, partially molten core of conductive iron. The decay of radioactive elements in the satellite's interior, as well as some tidal heating from gravitational interactions with Europa and Io, provide the heat needed to keep the core molten. By studying Ganymede's magnetic field, Galileo scientists determined that the satellite's mantle is also electrically conductive. Given the likely icy composition of the mantle and strong internal heat sources, the simplest explanation is that Ganymede has a deep layer of salty, liquid water, a subsurface ocean, about 125 miles, 200 kilometers, beneath the icy crust. Similar Galileo observations of Callisto revealed tentative evidence for a subsurface liquid water ocean, though less deep, on that moon. Could these oceans, or Europa's subsurface ocean, harbor life? While compelling, the Galileo results don't prove that there is an ocean on Ganymede or Callisto. Future missions, possibly including orbiters and landers, will need to utilize radar sounding and deep drills to establish the existence of an ocean on Europa. Near at Eros. 2 centuries of observations since the discovery of Ceres, the first known asteroid, have led to the discovery of more than 500,000 minor planets orbiting throughout the solar system. Many orbits in the main asteroid belt between Mars and Jupiter, many orbits in the Trojan asteroid clouds ahead of and behind Jupiter's orbit, and many in orbits that approach or cross that of our own planet, orbit much closer in. We refer to the individuals in this latter class. Approximately 9,000 near-Earth asteroids, NEAs, are 10% larger than 0.6 miles, 1 kilometer. In 1898, German astronomer Gustav Witt and French astronomer Auguste Charlois discovered the first NEA, 433 Eros. Eros occasionally comes close to Earth. In fact, its proximity enabled the use of parallax to make some of the first direct estimates of the astronomical unit, AU, the average distance between the Earth and the Sun. It is also one of the largest known NEAs, and while it is not currently a threat to impact the Earth, future perturbations in its orbit could make it a threatening object. To learn more about Eros and NEAs in general, NASA launched a robotic mission in 1996 called NEAR, the Near-Earth Asteroid Rendezvous, to fly by and then spend a year in orbit around Eros, studying the asteroid closely with CCD imaging and spectroscopy. The spacecraft, named NEAR Shoemaker in honor of planetary geologist and asteroid and comet hunter Eugene M. Shoemaker, entered Eros orbit in 2000 after a flyby of 253 Matilda. Eros is a big NEA, about the size of Manhattan Island, and has a rocky density of about 2.7 grams per cubic centimeter. Its heavily cratered ancient surface, along with its color and spectrum, indicate that it possesses the same primitive material as ordinary chondrite meteorites, which are the building blocks of Earth and other planets. NEAR Shoemaker's year-long mapping mission culminated in a gentle, low-gravity landing on the surface of Eros, where it now stands as a monument and testament to early 21st century planetary exploration. The solar neutrino problem. The so-called standard model of 20th century physics provides a theory that connects matter and energy through the interactions of elementary particles and forces. Familiar elements of the standard model include the electron, a fundamental particle of charge, and the photon, a fundamental particle of light. The neutron's discovery in 1933 led to the neutrino's prediction and discovery in 1956. This led to the hypothesis that neutrinos, like photons, are massless elementary particles that travel at the speed of light, creating 3 flavors: electron, muon, and tau neutrinos, depending on the process and environment. Neutrino astronomy became an active way to probe high-energy processes in inaccessible places, like the Sun's interior. Large neutrino detectors started coming online in the 1960s to detect elusive neutrino particles generated in the Sun or during high-energy cosmic events such as supernova explosions. According to the Standard Model, hydrogen fusion with helium inside the Sun should create electron neutrinos that these detectors could find. In fact, these detectors discovered the predicted solar neutrinos, but at a rate only about 1/3 of what the model predicted. The missing neutrinos created what particle physicists called the solar neutrino problem. Physicists made solving the solar neutrino problem a top priority because the Standard Model might only be accurate if they could. Theorists wondered if neutrinos could change flavors or oscillate between their different types. In the 1990s, researchers built new higher-resolution detector experiments to improve measurement fidelity. And in 2001, the new data revealed a surprising revelation. Neutrinos are not massless particles. They possess extremely small masses and move marginally slower than light. Most importantly, experiments showed that they can oscillate between electron, muon, and tau flavors, and about 2/3 of the electron neutrinos created inside the Sun eventually convert to other flavors. Solving the solar neutrino problem led to Raymond Davis Jr. and Masatoshi Koshiba's 2002 Nobel Prize in Physics. More importantly, it led to critical revisions of the Standard Model, which now accounts for oscillations by neutrons and other particles. Age of the universe. We built the Hubble Space Telescope, HST, as a time machine. By gazing deeper into space, it also peers farther back in time, detecting light emitted by stars and galaxies billions of years ago. Using standard candles, such as Cepheid variable stars or certain types of supernova explosions in far-distant galaxies, astronomers have been able to use HST to refine Hubble's law and to determine the rate of the expansion of the cosmos. After a decade of observations, in 2001, HST scientists announced that by turning the clock backward on their derived expansion rate, they could deduce that the Big Bang had occurred approximately 13.7 billion years ago. At the same time, scientists launched a new space satellite to measure the details of the cosmic microwave background radiation from the early universe's initial expansion. The American cosmologist David Wilkinson inspired the daunting name of the Wilkinson Microwave Anisotropy Probe, WMAP. The satellite T. Wilkinson took high-resolution images of variations, anisotropies, in the 3 Kelvin background radiation, which is the remnant of the universe's expansion following the first few 100,000 years after the Big Bang, at the beginning of the so-called Dark Ages, but before the birth of the first stars. Amazingly, independent of HST or other methods, the WMAP data led to an estimate of the universe's age of 13.7 billion years. By combining data from HST, WMAP, and other studies, cosmologists claim that the Big Bang happened 13.75 plus 0.11 billion years ago, a stunning level of precision. The Big Bang frames the Standard Model of cosmology, with hydrogen, helium, and a few other light elements created in the Big Bang, as well as heavier elements, the eventual building blocks of life, subsequently created in stars and supernova explosions. Explosion, rapid inflation, deionization, reionization, slow expansion, and accelerating expansion are all now key milestones in cosmologists' understanding of the universe. Knowing when the Big Bang occurred raises more questions, though. Why did it occur? What existed before the creation of space and time? How will it end? Such deep questions push the boundaries of what modern science can study. Genesis catches solar wind. The Sun, like all stars, is powered by the dynamic balance between the gravitational contraction of an enormous mass concentration and the outward pressure of intense nuclear fusion reactions occurring in its deep interior. The Sun emits radiation that provides heat and light to the planets, but its photosphere and chromosphere also release highly energetic particles into interplanetary space at high speeds. We refer to this stream of particles as the solar wind. In 1995, the European Space Agency, ESA, and NASA teamed up to launch a satellite called the Solar and Heliospheric Observatory, SOHO. We specifically designed this satellite to study the Sun's dynamic environment, including the solar wind, using high-resolution ultraviolet images and spectroscopy. SOHO continues to provide spectacular time-lapse views of our dynamic star. Solar astronomers' discoveries about the solar wind from SOHO and other studies generated substantial interest in a dedicated space mission to collect some of these far-flung pieces of the Sun. Planetary scientists, too, are keenly interested in the Sun's composition, as it represents about 99.9% of the solar system's mass and is the starting composition from which the planets formed. NASA designed the Genesis mission to collect and return solar wind samples in response to this interest. Launched in 2001, the mission maintained a looping orbit around one of Earth's gravitational Lagrange points, L1, exposing a specially designed sample return canister to solar wind particles until early 2004. Geochemists and solar astronomers have intensely studied many Genesis samples that survived the 2004 crash of the canister in the Utah desert due to a failed re-entry parachute. We collected and analyzed particles from the three types of solar wind: fast, slow, and coronal mass ejections. And the results are providing important new data, some of it surprising, about the Sun's composition, helping to refine our understanding of processes at work inside the Sun and other stars. Spitzer Space Telescope. Galaxies, stars, planets, moons, asteroids, comets, and even cosmic dust grains emit thermal infrared energy dependent on temperature, composition, and environment. In recent decades, astronomers have used new, sensitive infrared detectors to study the thermal energy of these objects. Major advances came in 1983 with the launch of the Infrared Astronomical Satellite, IRAS, which conducted the first all-sky survey of infrared heat energy emitted by cosmic objects. And then in 1995 with the launch of the Infrared Space Observatory, ISO satellite, which followed up IRAS discoveries with higher resolution imaging and spectroscopy observations until early 1998. IRAS and ISO made important discoveries about circumstellar disks, planet formation processes, star formation, and galaxy evolution. Motivated by these discoveries, NASA dedicated its fourth and final Great Observatory satellite to an IRAS-ISO follow-up mission, initially called the Space Infrared Telescope Facility, and later renamed the Spitzer Space Telescope after the American astronomer and longtime space telescope advocate Lyman Spitzer. Launched in 2003, Spitzer parked in a heliocentric orbit, close enough to Earth to enable frequent, high-bandwidth communications, yet far enough away to prevent interference from Earth's thermal background signature. Spitzer used liquid helium to cool its instruments below 4 kelvins, making them supersensitive to extremely faint cosmic thermal energy sources. Astronomers used the infrared field's ability to see through optically thick dust to study star-forming regions such as the Orion Nebula. They also made major discoveries studying quasars, galaxies, protoplanetary disks, hot young stars, extrasolar planets, and our solar system. The telescope's helium supply ran out in 2009, but Spitzer continues to make less sensitive but still unique measurements of many infrared sources and is expected to operate for many more years. Spirit and opportunity on Mars. More than 3 decades of successful Mars orbital and land investigations by scientists involved in the Mariner and Viking missions painted a compelling picture of major past climate changes on the red planet. Today's Martian surface is extremely cold, bone dry, and inhospitable to life as we know it. But ancient Mars, as revealed by these missions, appears to have been a warmer, wetter, and potentially more Earth-like place. If so, early Mars, during the first billion years or so after its formation, may have been a habitable environment where life could have thrived, like on our own planet. However, planetary scientists wanted to move beyond photographic evidence of a potentially habitable early Mars and make quantitative geologic, geochemical, and mineralogic measurements that could provide smoking gun proof. Experience gained from the 1997 Mars Pathfinder mission proved the value of mobility in doing geologic fieldwork with robots in distant locations, leading to the choice to embark on an even longer-range rover mission. Because of 2 Mars mission failures in 1999, NASA decided to reduce its risk. Instead of just 1 rover, it would launch twin rovers, named Spirit and Opportunity, in 2003. Both rovers landed safely in early 2004 and began their separate adventures on opposite sides of the planet. Spirit in an ancient crater named Gusev, which may once have hosted a lake, and Opportunity in the cratered area Meridiani Plenum, where Mars Global Surveyor data showed evidence for water-formed minerals. After several years of virtually roving around Gusev with Spirit, mission scientists discovered water-bearing minerals in an ancient hydrothermal system that provided smoking gun evidence for Gusev's past habitability. At Meridiani, the team immediately found other water-formed minerals like hematite, clays, and sulfates, which also provided smoking gun evidence for past habitability. Despite their expected lifetimes of just 90 days, Spirit operated until early 2010, and as of mid-2018, Opportunity continues to roll on and make new discoveries. Cassini explores Saturn. Centuries of telescopic observations and the successful flybys of Pioneer 11 and Voyagers 1 and 2 revealed Saturn to be stunningly beautiful and scientifically interesting, with important similarities and differences from the other giant planets. Following its planetary exploration strategy of flyby, orbit, land, rove, and sample return, NASA began planning for a dedicated Saturn orbiter mission in the 1980s. The agency finally gained congressional approval and funding in the 1990s. In 1997, it launched a joint US-European spacecraft named Cassini, after the Italian-French astronomer Giovanni Cassini, who had made some of the earliest scientific observations of Saturn, its rings and moons. After gravity-assist flybys of Venus, Earth, and Jupiter, Cassini finally went into orbit around Saturn in 2004. The orbiter returned incredible images, visible, infrared, and radar, and spectroscopic measurements until its dwindling fuel supply forced mission controllers to intentionally plummet the spacecraft into the clouds of Saturn, ending the mission in 2017. Mission scientists have made many important discoveries from Cassini's more than 13-year exploration of the Saturn system. We have found 7 new moons, some of which leave strange 3-dimensional weights and other structures in Saturn's thousands of rings. We've also discovered active geysers spewing water vapor and organic molecules from the subsurface of the tiny moon Enceladus. We have also taken the first close-up pictures of the moon Phoebe, which may be a captured Centaur object. We have done detailed infrared and radar imaging and mapping of Titan's hazy surface, showing lakes of liquid methane, ethane, or propane. And we have done the most detailed studies yet of Saturn's atmosphere and magnetic field. Mission controllers worried that as the spacecraft ran out of fuel to properly control its orientation and trajectory, it might accidentally crash into Enceladus or Titan, potentially contaminating those astrologically important worlds. Thus, at the end of the mission in 2017, they intentionally steered Cassini into Saturn's atmosphere, where it burned up in a blaze of glory. Stardust encounters. Comets can be spectacular events in the night sky, as evidenced by the numerous appearances of Halley's Comet over recorded history and the singularly dramatic occurrences of great one-time comets, including Hyakutake in 1996 and Hale-Bopp in 1997. However, most of the comet's spectacular displays come from reflected sunlight or gaseous emissions from their tails. Little was known about the icy, rocky, solid nucleus of comets until the 1986 flyby of Halley's Comet by the European Giotto spacecraft, which helped to support the American astronomer Fred Whipple's idea of comet nuclei as small, irregular, dirty snowballs. Planetary scientists proposed more robotic missions to study the diversity of comet orbits and origins, some from the Kuiper Belt, others from the Oort cloud, and still others with orbits that interact with and occasionally impact the planets, such as Shoemaker-Levy 9 in 1999. This mission, named Stardust, not only flew closely past the nucleus of Comet Wild 2, pronounced Wild 2, but also collected tiny samples of dust and gas from the comet's tail and returned them to Earth in a special capsule. Stardust was a great success. Images of Wild 2 from the January 2004 flyby revealed a small, fluffy, icy, with a density of less than 0.6 grams per cubic centimeter, round nucleus spewing out jets of gas and dust and covered by puzzling circular pits and ridges. In 2006, the sample canister safely landed on Earth, revealing millions of micron to millimeter-sized cometary dust grains and some interstellar dust grains collected in a separate part of the experiment. The comet dust analysis has revealed not only the expected water ice and silicate minerals, but also a variety of organic molecules, some similar to the simple organics found in the primitive Murchison meteorite, others with much more complex hydrocarbon chains, comparable to those found in organic molecules. It would seem that comets are important potential contributors to life's chemistry. Deep Impact, Tempel 1. Missions like the Giotto flyby of Halley's Comet in 1986, or the Stardust flyby of Wild 2 in 2004, revealed comet nuclei to be small, icy bodies. They are also very dark bodies, typically reflecting only about 3 to 5% of the sunlight that strikes them, about as dark as charcoal. The sun's heat evaporates ice, leaving behind a lag of rocky and organic grains that darken the surface. Tidal forces impacts can crack this surface lag, allowing fresh ice to escape from cracks and into the interior. If this model of a comet's surface is correct, explained some scientists in a mission proposal to NASA in 1999, then it should be possible, with a powerful enough impact, to design a mission to punch a hole in the surface lag and expose a comet's pristine icy materials for study. In early 2005, NASA accepted the bold mission idea and launched the Deep Impact mission, carrying an 815-pound, 370-kilogram copper projectile probe toward Comet Tempel 1. As Deep Impact got close to Tempel 1, imaging of the comet's nucleus revealed it to indeed be a dark, irregular body, about 5x3 miles, or 8x5 kilometers, in size, with surprisingly complex geologic landforms, including possible impact craters and lobes of strangely layered terrain. The spacecraft released the impactor for its July 4, 2005, crash landing, and the resulting impact generated some impressive cosmic fireworks. The projectile penetrated below the lag crust and into the comet's subsurface, releasing a huge spray of ice and dust, including clays, carbonates, and silicates. Images from the Deep Impact flyby spacecraft revealed a spectacular flash and a giant debris cloud that obscured the impact crater. Later analysis of the flyby data showed Tempel 1 to have a low density, 0.6 grams per cubic centimeter, indicating a rather porous, icy interior composition. In 2006, NASA's Stardust spacecraft successfully completed its sample return mission from Comet Wild 2. In February 2011, it made a close flyby past Tempel 1. Stardust successfully imaged the 500-foot diameter, 150-meter impact crater made by the Deep Impact probe's encounter 6 years earlier. Huygens land on Titan. Saturn's moon, Titan, is the second largest satellite in the solar system, larger than Mercury, and the only satellite with a substantial atmosphere. During the Voyager flybys of Saturn in 1980 and 1981, there were high hopes that the surface would reveal interesting landforms and processes. However, a thick layer of haze shrouded Titan, obscuring the surface from view at the visible wavelengths of the Voyager cameras. As revealed by spectroscopic data, Titan's atmosphere primarily consists of nitrogen, N2. The amount of methane, CH4, has a surface pressure of 50% higher than Earth's pressure at sea level, but its temperature is only about 90 degrees above absolute zero. Voyager data and subsequent telescopic observations revealed much about Titan, but much remained unknown, leading to the addition of a dedicated Titan exploration payload to the Cassini-Saturn orbiter. When Cassini launched in 1997, it carried a Titan lander called Huygens, named after Titan's discoverer, the Danish astronomer Christian Huygens. On January 14, 2005, Huygens completed successful aerobraking, using friction from the upper atmosphere to gradually lower its orbit, and parachute-assisted landing, becoming the first lander on an outer planetary surface. During the descent, the probe obtained spectacular photographs of river-like channel systems, shorelines, and dark, flat-floored plains, interpreted as lakes of liquid ethane, methane, or propane. The lander survived on the surface for about 90 minutes, taking photographs of the strange alien landscape and measuring the pressure, temperature, and chemistry. The 4 to 8 inch, 10 to 20 centimeter rocks in this artist's rendering of the Huygens probe on Titan are pebbles of water and hydrocarbon ices, rounded by transport in streams or lakes of liquid hydrocarbons. Images of Titan's surface from Huygens resemble the Martian surface in some ways and Earth's surface in others. But there are substantial differences. For example, liquid hydrocarbons, not liquid water, carve Titan's river channels and shorelines, despite the surprisingly similar landforms. The rocks in the images are likely chunks of water or hydrocarbon ice, which act like rock at very low temperatures. Hayabusa at Itokawa. Possible future impacts on Earth by asteroids or comets represent a threat to the entire human species. Studying small bodies and learning about their orbits and properties is an international endeavor. During the late 20th and early 21st centuries, space missions by the US, European, and Russian space agencies to comets Halley, Borrelly, Wild 2, and Tempel 1, as well as the asteroids Gaspra, Ida, Matilda, Eros, and Lutetia, dramatically increased our understanding of kilometer-size, or tens of kilometer-size bodies. However, the Japanese Hayabusa spacecraft's mission was the first to study a tiny asteroid in detail. Hayabusa, Japanese for Falcon, was the Japanese Aerospace Exploration Agency's, JAXA's, first asteroid mission, and the first attempt at a robotic sample return from an asteroid. Launched in 2003, Hayabusa used novel ion propulsion engines to slowly and gently match its trajectory to a small, recently discovered near-Earth asteroid named 25143 Itokawa. In September 2005, the spacecraft began its rendezvous alongside Itokawa. The asteroid's gravity was too low to allow the spacecraft to truly orbit, which turned out to be a grey, elongated, rocky object only about 1,750 feet, 535 meters long. The lumpy little world's surface revealed large boulders and strangely smooth areas. 2 months later, they directed Hayabusa to approach the asteroid even closer, gently touch down, release a small rover, collect some surface soil and rock samples, and then return a sample capsule to Earth. No problem, right? Indeed, numerous issues arose. Despite briefly landing on the asteroid, Hayabusa's rover deployment failed, causing the spacecraft to ascend out of control from the surface before it could confirm its sample collection. By the time they regained control, it was too late to attempt a second attempt. They had to launch the sample capsule back to Earth without knowing whether it was empty. The sample capsule made a safe parachute landing in Australia in June 2010, and after some tense weeks of careful unpacking and testing, scientists were delighted to find about 1,500 small dusty grains of Itokawa inside, with chemistry matching that of some primitive meteorites. Hayabusa was a success. Demotion of Pluto. When Pluto was discovered in 1930, It was hailed as the solar system's ninth planet, partially because it was estimated to be about the size of the Earth. Follow-up observations over the decades and the discovery of Pluto's moon, Charon, eventually led to the realization that Pluto is a small world, only about 20% of the diameter and less than 1% of the mass of Earth. Despite decades of inertia and countless textbooks touting Pluto as a cold and lonely outpost at the solar system's edge, Pluto maintained its status and popularity as a full-fledged planet. However, in the 1990s, it became clear that the solar system does not end at Pluto. We have discovered more than 1,000 Kuiper Belt objects, KBOs, orbiting well beyond Neptune, in addition to the long-known population of long-period comets that likely originate from the Oort cloud, and we expect to discover many tens to hundreds of thousands more. Many of them are comparable in size to Pluto, or even larger. If Pluto is a planet, then the potential proliferation of Pluto-sized worlds would dramatically increase the number of planets in the solar system. This possibility caused consternation among some astronomers and compelled the world's relevant governing agency, the International Astronomical Union, IAU, to reconsider the classification of Pluto-sized worlds. In 2006, the IAU decided to formally demote Pluto and other large KBOs from planethood to a new class of object, a dwarf planet, created to recognize the importance of this newly discovered class of small worlds, but to distinguish them from the classical planets, which have significantly larger influences on their surroundings. The demotion of Pluto caused a significant public outcry, and even many astronomers and planetary scientists need clarification and are deeply divided about the new formal definition of what it takes to be a planet. According to many, any object large enough to have become roughly spherical under its own self-gravity, or that has had active internal processes that have differentiated it into a core, mantle, and crust, could be considered a planet. Why not reclassify giant satellites such as Ganymede, Titan, and Europa, comparable to or larger than Mercury, as planets? Whether our solar system has 8 known planets, or perhaps 40 or more, the debate continues. Habitable super-Earths? The discovery of planets around other stars has naturally led to excitement and anticipation about potentially discovering other Earth-like worlds in our celestial neighborhood. However, the prospects have been daunting. With the discovery of the first extrasolar planets around an exotic, high-energy pulsar supernova remnant, and the majority of subsequent planet discoveries around main sequence stars being hot Jupiters, massive gas giant worlds orbiting extremely close to their parent stars. Recently, scientists have discovered some so-called super-Earth planets, which range in size from a few to 10 to 15 times that of our world, but most are extremely close to their parent stars. However, in 2007, at least 6 planets orbiting the star Gliese 581 revealed 2 members of a new planet class, potentially habitable super-Earths. Based on radial velocity variations of the host star, we now infer the newly discovered planets, known as Gliese 581c and d, to be around 5 to 10 Earth masses. Most importantly, these 2 planets orbit within Gliese 581's habitable zone, the distance from a star where an Earth-like planet could maintain liquid water on its surface. In our solar system, the habitable zone extends from about Venus to Mars. Planets like Gliese 581c and d, or others discovered to orbit within their star's habitable zone, are not necessarily habitable or inhabited. The concept of a habitable zone acknowledges that life as we know it requires liquid water for its formation and sustainability. If these worlds are bathed in harmful radiation from intense solar flares, are heated to the melting point by tidal interactions with their stars or other planets, or have all their water tied up as frozen ice, they might not truly be habitable. In addition, examples from our own solar system, such as Europa, Titan, and Enceladus, show that it can be possible for habitable worlds to exist outside the traditional habitable zone if other energy sources are present that can help to keep liquid water stable on or under their surfaces. So far, we know of only one perfect Goldilocks planet for life as we know it, Earth. However, many astronomers anticipate the discovery of Earth 2.0 and other similar planets soon. Kepler mission. Around the turn of the 21st century, astronomers began perfecting and testing various techniques for detecting extrasolar planets. The most common search method, radial velocity surveys, is most sensitive to giant, Jupiter-sized planets orbiting close to their parent stars. Indeed, the majority of the first discoveries have been those kinds of likely inhospitable extrasolar planets. Other methods can identify smaller, even Earth-sized planets around other stars. However, some methods, such as pulsar measurements and gravitational lensing, necessitate exotic environments that are likely inhospitable to life, or one-time events that hinder the further characterization of the detected planets. Perhaps the most promising way to detect Earth-sized planets in the neighborhood around their stars is to rely on luck. If the geometry is just right, such planets will occasionally pass in front of or transit their parent stars, dimming those stars' light by a tiny but detectable amount in a predictable, periodic way. Finding Earth-sized worlds that way is the goal of NASA's Kepler mission, named in honor of the Renaissance astronomer Johannes Kepler, discoverer of the fundamental laws of planetary motion. In 2009, NASA launched the Kepler satellite into an Earth-trailing solar orbit with the simple mission of staring at 145,000 nearby main sequence stars for 3.5 years, monitoring their light to search for periodic planetary transits. Kepler's 42 charge-coupled device, CCD detectors, form the largest camera, 95 megapixels, ever launched into space, sensitive enough to detect changes in starlight as small as 0.004%, or 1 part in 25,000. Kepler's 2009-2013 prime mission yielded stunning results. It confirmed more than 2,500 planets around nearby sun-like stars, and other astronomical methods await confirmation of nearly 5,000 more. Many of those are hot Jupiters in rapid, close-in orbits. However, over 50 could be Earth-sized planets in the habitable zone around their host stars. In late 2013, Kepler began an extended mission called K2, designed to find extrasolar planets in more sky regions and study other astronomical objects. Sophia. Astronomers like to build telescopes on high, isolated mountain peaks to get away from the city lights and to get above as much of Earth's atmosphere as possible. Smoke, smog, haze, water vapor, and other gases and aerosols that block light from reaching the surface or contaminate the universe's spectroscopic measurements limit the quality of scientific observations that can be made from the ground. Putting telescopes in space, such as the Hubble Space Telescope or the Spitzer Infrared Observatory, is a great alternative. But those projects take decades to complete and cost hundreds of millions or several billion dollars to build. As a way to gain some of the advantages of space-based observing platforms without incurring as many costs or technical hurdles, NASA developed an airborne astronomy program around 1965. At first, they used Convair and Learjet aircraft to carry small telescopes to commercial aircraft altitudes. Then, starting in 1975, they used the Kuiper Airborne Observatory, KAO, a modified C-141A jet carrying a 36-inch, 91-centimeter optical telescope to observe astronomical objects from altitudes up to 48,000 feet. KAO has made significant scientific advances, including discovering the rings of Uranus and a thin atmosphere on Pluto. NASA decommissioned the KAO in 1995 to build the larger, more powerful stratospheric observatory for airborne astronomy, or SOFIA, a modified 747 aircraft carrying a powerful 100-inch, 2.5-meter reflecting telescope. Initially plagued by technical and cost overrun problems, flying a 747 with a hole cut out of it is not simple. SOFIA finally began initial scientific flights in 2010. Flying at a nominal altitude of 41,000 feet, 12,500 meters, SOFIA, like CAO, can get above almost all the water vapor in Earth's atmosphere, enabling a much wider range of infrared observations than is possible from ground-based telescopes. Initial science checkout observations in 2010 and 2011 acquired data on Jupiter's atmosphere, the Orion Nebula, and the galaxy M82, where infrared observations can penetrate much of the galaxy's dust to directly observe the formation of young stars. Now that routine science observations are beginning, future SOFIA observations will include studies of other star-forming regions, protoplanetary disks, exoplanets, and comets. Rosetta flies by 21 Lutetia. During the second half of the 20th century, spectroscopy and color measurements from telescopic observations revealed that we could group the main belt and near-Earth asteroids into a small alphabet soup of compositional classes. For example, asteroids that show colors and spectra indicating the presence of typical planet-forming volcanic minerals, like those found in stony meteorites, are known as S-type asteroids. Darker objects with grayer colors and spectra that are more like those of carbonaceous, carbon-bearing meteorites are known as C-type asteroids. Objects with spectra similar to metallic meteorites are known as M-types, and so on. Research groups and classification schemes have proposed dozens of different asteroid types. Before 2010, spacecraft had encountered S-type, for example, Eros, Gaspra, Ida, and Itokawa, and C-type, 253 Matilda asteroids, but no others. Thus, it was especially exciting when the European Space Agency's Rosetta spacecraft made a close flyby past the M-type asteroid 21 Lutetia on July 10, 2010. Launched in 2004, Rosetta is a comet rendezvous mission. It will rendezvous and deploy a lander onto the surface of the periodic comet Churyumov-Gerasimenko in 2014. In addition, the Rosetta team, like many other space mission teams, has been able to do some excellent bonus science by flying past other objects on the way. The Rosetta images of Lutetia revealed it to be the largest asteroid then encountered by spacecraft, at 82 x 63 x 48 miles, 132 x 111 x 76 kilometers in size. It is also one of the densest, at 3.4 grams per cubic centimeter, suggesting a possible rocky metallic composition consistent with its M-type classification. Regarding its visual appearance and geology, Lutetia shares many similarities with the other asteroids photographed up close. A lumpy, irregular surface heavily covered by relatively fresh and relatively degraded impact craters of various sizes. Lutetia also shows evidence of a surface layer of fine-grained, mobile, impact-generated debris planetary scientists call a regolith. Rosetta's flyby measurements motivate active research and debate on why Lutetia's spectrum resembles metallic meteorites, and how small objects with such low gravity, less than 0.3% of Earth's, can retain fine-grained regolith materials. Comet Hartley 2. After completing the successful 2005 mission to crash a projectile into Comet Tempel 1, engineers responsible for NASA's Deep Impact spacecraft realized that there was enough fuel left on board to operate the probe as a remote observatory for characterizing extrasolar planets using the transit method, which was also being used by the Kepler mission, and potentially encountering a second comet nucleus as well. Thus, NASA recast Deep Impact as a new mission, EPOXI, which stands for Extrasolar Planet Observation and Deep Impact Extended Investigation. In November 2010, we targeted EPOXI to fly closely past the nucleus of the Earth-approaching comet Hartley 2, following 3 Earth flybys to provide gravity-assist trajectory adjustments. Discovered in 1986 by Australian astronomer Malcolm Hartley, Hartley 2 is a short-period comet that travels in an orbit between about 1.1 astronomical units, AU, and 5.9 AU every 6.5 years. We further divide short-period comets into Jupiter family comets, like Hartley 2, with periods less than 20 years, and Halley family comets, named after their most famous member, with periods ranging from about 20 to 200 years. We suspect that many short-period comets were once long-period comets, their orbits dramatically altered by a close encounter with one of the giant planets. Hartley 2, for example, may be a relatively primitive object from the Pic-Oort cloud that recently encountered Jupiter. The epoxy data from the flyby support the idea of a primitive outer solar system origin for Hartley 2. The dramatic epoxy images revealed powerful jets of ice, gas, and dust spewing from the comet's 1.4-mile, 2.3-kilometer peanut-shaped nucleus, and spectroscopic measurements revealed that carbon dioxide, dry ice, not water, dominates the ice. Initial studies also point to the possible presence of some organic molecules, such as methanol, in Hartley 2's jets and extended atmosphere. At the rate that the comet is currently losing mass from the jets, as well as from the sublimation, evaporation of ice, of the surface in general, scientists predict that it might only survive for about another 100 orbits, 700 years or so, before breaking up into smaller pieces. Thus, it is likely that this little lump of primitive ice from the original solar nebula is indeed a recent interloper in the inner solar system. Messenger at Mercury. Mercury is the most difficult of the classical planets to observe because it is always close to the Sun. The planet has also been stubbornly resistant to spacecraft exploration, partly because of its challengingly hot thermal environment, where sunlight can be 5 to 10 times more intense than on Earth. During the 20th century, only one space mission explored the innermost planet. Mariner 10, launched in 1973, performed 3 close flybys past Mercury in 1974-1975. Photographs of about half the planet revealed a lunar-like cratered surface and large-scale tectonic features, suggesting an early molten surface that cooled and contracted over time. Mariner 10 also discovered that Mercury has a strong magnetic field, likely related to the planet's large, partially molten core. These intriguing discoveries compelled planetary scientists to propose a dedicated Mercury orbiter mission, which NASA selected for launch in 2004. After gravity-assist flybys of Earth and Venus, and 3 flybys of Mercury itself, the Mercury surface, space environment, geochemistry, and ranging mission, Messenger, a contrived acronym in honor of Mercury's mythologic role as the messenger of the gods, finally braked into a successful elliptical orbit around Mercury in March 2011. Messenger completed mapping the entire planet and made exciting discoveries about ancient Mercurian volcanoes, craters, and tectonic landforms before running out of maneuvering fuel and crashing into the planet in 2015. Mission scientists determined that bright spots seen at Mercury's poles in Arecibo radar images are permanently shadowed, ice-filled impact craters rather than some strange geochemical anomaly. Indeed, the poles are icier than originally thought, because ice also fills many small, previously unresolved, shadowed craters. The European Space Agency's Bepi-Colombo orbiter, slated to launch in 2018 and enter Mercury orbit in 2025, will benefit from Messenger's discoveries in its planning and operation.